site communication to this CubeSat, and the CubeSat deploying in space and transmitting the data back to Earth. Oh, okay. Give me 1 second. I might be able to fix this. Oh. 1 second. Okay, we'll do without the video. Unfortunately, it's not working. Should have checked before. Okay, so can you guys see the slides? Yes? Okay, so like I was saying, the main challenge was actually the storage volume, since we didn't have any volume inside of the CubeSat. So the obvious solution was to come up with a reflector antenna that actually falls atop of the surface of the CubeSat. You can actually see how it falls, and there is a burn wire that we apply a current into, and then it cuts the wire and the panel deploys thanks to the hinges, spring-loaded hinges that you can see here on this picture. We designed some custom-made hinges so that this panel can fold and deploy without having any gap in between the panels. So as a result, the gain efficiency, the gain is higher and the efficiency is also higher. And also, if you have a gap between panels, your side lobe level will increase quite significantly. So that's the reason why we actually come up with this hinge design, to avoid having any performance degradation. So we achieved a gain of more than 28 dBi. We did not use any internal storage volume. And this way, we've been able to close the link with limited RF power coming from the SSPA, and the power is roughly about 4 watts. So you can actually see some important design features here. So the first thing is the panel. So how do we get the surface flatness that we want to survive the trip to Mars, and also not to have the surface bending and because of thermal gradients. And what we did is that we used a stable core in between, and on each side of it, we used a Roger board 4003. And the reason why we use 2 of them is to actually have perfect symmetry. So we even have the reflector layout on each side. And the reason why we did that was to reduce the thermal gradient. By doing that, you reduce the thermal gradient across the surface of the reflector itself. So then the optics was another critical thing to come up with. If you design a reflector without any storage constraints, then it's very straightforward. You can achieve quite good efficiency. But when you have storage constraints, which is what happens when you are actually designed for commercial products, or for an actual application like that, then you need to live with a constraint that do not necessarily allow you to come up with the best design, the best RF design. So the feed was located as far away from the reflector array to have the highest F over D in order to achieve a decent efficiency out of this reflector array. And with these optics, we actually, without changing the pointing of the reflector itself, of course, you can correct with that by designing the reflector properly. But here, without doing any of that, we got a pointing of 22.7 degrees, which was very convenient, taking into account the constraint of the UHF antenna, which is located on the other side. And I'm going to talk about that at the same time. So you have the constraint of being able to receive while inside is landing from the UHF antenna, but at the same time, you need to be able to point toward Earth. And that's the reason why this optic worked out fairly well. And but if we needed to change the pointing, that's also very straightforward to do. As you can see here, this shows you the gain losses. So the computed directivity from this reflector array was around 30.5, and the achieved gain was about 29.4, which gives you about 1.3 dB of loss. And the main contribution is shown here. So obviously you have the feed loss, which is about 0.7 dB at X band, which is pretty decent from a patch array, which is a 2x4 elements, circularly polarized. Then you have the dielectric losses from the reflector itself. You also have the ohmic losses, the mismatch loss from the feed, and the losses that are coming from the hinges because they're taking away some of the area of the reflector, of the aperture of your antenna. And on the bottom, you can actually see the radiation pattern calculated and measured, and we obtained fairly good agreement between the two. You can see a disagreement in the cross polarization, which does not drive. Oh, what just happened? What just happened? Can you guys still hear me? I think my computer shut down.
But your screen is not there.
Oh, okay. I need to try to restart. I don't know what happened. I'm trying to restart the computer. It just decided to shut off. Okay, while the computer is trying to restart, I will continue talking about the mission. So we launched this mission about 2 years ago successfully. The reflector array was deployed right after deploying very near Earth. And from then he did the entire trip with the reflector array and the UHF antenna deployed and the solar arrays. We have characterized the radiation pattern of the antenna near Earth to verify that everything was nominal, which it was. We actually got a gain within 0.4 dB from what we predicted. And then 9 months after, when reaching Mars, we communicated and did achieve bandpipe communication from the 2 CubeSats successfully. So that was quite an achievement since it was the first time ever. And so we were very, very, very excited with these results, not only because it was the first time, but also because it's going to pave the way for future CubeSat missions that will come in the near future. So we have about 12 missions that are on the wait list, NASA missions, led by NASA and in collaboration with universities, where we are going to try demonstrate new instruments as well. So we're very, very excited about all of these achievements. So on the back of the CubeSat, we also have a UHF antenna. The UHF antenna is circularly polarized. It's circularly polarized. We're using a loop antenna where we're excited at the 2 corners to get, so to get circular polarization, you need 2 orthogonally polarized antenna, two orthogonally polarization. You need a 90-degree out of phase, and you also need the same amplitude. And so to do that, we excited 2 of the nearby corner of the loop with the same amplitude, 90-degree out of phase, to obtain circular polarization. So that was a very, very clever design that my colleague Emmanuel Descrossas come up with. Okay, the computer restarted. Let me. Share again. And to test the UHF antenna, you need to do that in free space, in outdoor range, which is a capability that we have at the Jet Propulsion Laboratory. Okay. Sorry, I need to log in again. I'm very sorry for the inconvenience.
No issues, sir. No issues. Please continue.
So we did the measurement in outdoor. We obtained very good agreement between calculation and measurement. And I would like to show that to you right now. So I think you need to let me in again. Okay, you need to let me share so I can share the slide.
One second, let me. Okay, you will be able to share your slides now.
Yes. Okay, can you now see?
Yes. Yes, sir.
Okay, so this is how we actually achieve the circular polarization. So you have the loop. If you excite one corner of the loop, you get linearly polarization in this direction. Then if you excite on the other corner, you excite orthogonally to this polarization. If you put it on the CubeSat at the right lambda over 4 distance, then you can increase the gain by 3 dB. Then if you excite each of these two orthogonally polarized, you will, by 0 and minus 90 degrees, you will get the right-handed circular polarization like we wanted. This is how the antenna stow, and this is how it deploys. So it's fairly simple with jack in the box principle, where you have two hinges that deploy the whole thing. To excite with 90 degrees out of phase, we actually use a balloon. And what we do is we actually use the loop itself as a ground plane for the strip line. So that's actually another clever way to do that. So kudos to my colleague Emmanuel Descroissas for coming up with this solution. Then for the radiation pattern, this is how we actually measure that on a CubeSat mockup, and you can see the radiation pattern, the good agreement between calculation and measurement. So as you can see, there is a lot of error bar because at UHF, you need to be aware of the accuracy that you can achieve. So that's also, you need to invest time trying to understand that so you don't have any surprises. So this is a picture of Mars that was taken from the camera that's located on the side of the reflector array. So you can actually see the reflector array panel on the top, and you can also see the feed on the bottom. And this, what you see on this figure, is very interesting. So as I said, we had two CubeSats, so two twin CubeSats, Marco A and Marco B. And if you look at the receive power, we have about a minus 145.5 dBm for the first one, and we have about minus 147 for the second one. So you would think that one did not perform as well than the other when you look at that, but that's not quite that. The reason why we had a difference is because the deep space network is using a shared aperture to communicate with two different CubeSats. So one CubeSat was located at the peak of the antenna, and the second CubeSat was located off bore side. And that's the reason why we have a difference in receive power. As I said, we assessed the gain to be within plus minus 0.4 dB of what we actually measure on the ground, which was actually super impressive. So we were extremely excited with the result that we obtained, especially for such a challenging mission as Marco. So then, when you come up with a great solution, people usually ping you to come up with even better solutions for the future. So we looked at a larger deployable reflector array for earth science, but also for communication. This one was designed for earth science communication at 35.75 gigahertz, using the same principle, but much more reflector array panels to deploy. We achieved 47% of efficiency and a gain of more than 47 dBi out of this antenna that measures roughly 1 meter by 80 centimeters. This is the prototype of the antenna, and you can see the agreement between calculation and measurements. Again, this was a very interesting technology to develop that future missions could potentially use. Now I will talk about mesh reflectors. So the first mesh reflector that we developed from scratch at JPL was actually for the mission called RainCube. RainCube is the first active radar in a CubeSat for low Earth orbit operation, operates at 35.75 gigahertz. It needed about half a meter diameter with an efficiency of more than 50% to meet the mission requirements. The main driver is efficiency for an active radar as RainCube, because if you lose 1 dB, because it's around, it's two-way trip, you actually lose 2 dB in terms of SNR. So the efficiency was the main driver, and the second driver was the side lobe level. You do not want an antenna with very high side lobe levels, so you need to have a good control of the surface that you actually deploy. So we achieved 42.6 dBi out of this antenna and an efficiency of 56%, which is quite amazing at Ka-band. You can actually see a cross-section of the antenna when folded and when deployed, actually half deployed, not entirely deployed. You can see in the center the telescoping waveguide in blue, you can see the feed horn in the center, which is a multi-flare horn that gives you very similar performance as a corrugated horn. But in that case, they are very, very, very simple to fabricate and also very simple to design as well. It takes you, if you start with rough dimensions that are very near to the goal, you will not take more than 5 minutes to design an antenna like that. And here, one of the main challenges was to find a good trade-off between mechanical and RF. So you want to be able to fold reliably an antenna in the storage volume that was allocated. In this case, it was 10 by 10 by 10 by 15 centimeter, so 1.5 U. And you need to deploy it in a way that is as simple as possible. So you need to minimize the number of deployments. So we used a cassette grain antenna. Unfortunately, the video does not want to work. So you have a four screws driving system on 4 of the corners, so 2 here and 2 on the other side, that push the entire ribs and feed horn outside of the canister. Once all of that is out of the canister, you have this bottom hinge that deploys, and then you have the mid hinge that deploys. And you can actually see the mid hinges here in black, and the bottom hinges, you can see them, but they are around here. When this deployed, the feed is released and deployed, and you have the subreflector that deploys with this spring in the center. So we try to keep this deployment as simple as possible, and to minimize the number of deployments, we actually use a cassette grain design because the subreflector is below the focal distance, and that minimizes the number of deployment of the feed. The second thing that's important when you are an RF designer is to try to find a good balance between the complexity of the mechanical design and achieve the highest RF performance that you can. But you don't want to impose constraints that are too harsh on the mechanical design because otherwise the success, the likelihood of being successful is going down. So you need to have a very good trade-off between mechanical complexity and RF performance. So in this case, we actually minimize the number of ribs. So the maximum number of ribs that we accepted was 30 ribs. And knowing that, we compensated the surface aberration that comes from the fact that between these perfectly parabolic ribs, you have a flat surface. We compensated that by refocusing the subreflector. And you can actually see that very well illustrated in this picture. So what happened is that when you have a surface aberration like this, the focal point is no longer a single point, but it's a region. And you can actually re-optimize for the ideal focal location to get the highest gain out of this antenna. So this is what we did, and we compensated the loss close to almost 0 dB with this number of ribs. So a bad RF engineers would have imposed to the mechanical engineer to increase the number of ribs, and as a result, things would have probably jammed during the deployment. So you need to be aware of this trade-off because that's very important if you want to be successful. So here is a very nice video of the deployment of the antenna in space. So you can actually see the ribs deploying, the mid-hinge that you see here. They are actually constant force spring. And you can actually see a wire here that's located right below the hinges and the mid-hinges. The reason why we do that is because during the deployment of these hinges, you don't want one side to deploy before all of the others so that it would stretch the mesh itself. And if it stretches the mesh, then you will never achieve the surface accuracy that you need. At Ka band, we needed about 0.2 millimeter RMS surface. So you need to be aware of these things and make sure that your mechanical engineers are aware of the requirements that you need to meet from an RF point of view as well. So from this picture, you can actually see also the strut that holds the subreflector, and you can also see the mesh. The reason why we took these pictures that we put together to have this very, very nice video is to overlap with a picture that we took, before lunch in the lab. Then, as soon as we received that picture from space, we overlap both pictures to make sure that everything deployed properly. And that's what we did. We were extremely happy with the results since we didn't see any deviation. And here I would like to show you a very, very nice plot of the science. The vertical plot that you see is actually the absorption line provided by RainTube. And the 2D plot that you see is the result that we got from another CubeSat, which is a radiometer. The radiometer is looking at different absorption line as well. And the scientists, even though the CubeSat were only 5 minutes apart, they overlapped the result and they were extremely, extremely impressed by the accuracy obtained with these two CubeSats. So then, like I said, whenever you get a nice piece of technology, the scientists are always asking for more. So from a telecommunication point of view and also from an earth science point of view, people always ask for 1 meter to 3 meters. So we told them on a CubeSat, forget about 3 meters, it's too challenging, you will not be able to do that. However, we could, using a 12U CubeSat, deploy 1 meter reflector. So we collaborated with a small company, a startup, Tendeg, to develop and qualify this reflector that you can see the deployment on the bottom. So the storage case is shown on the first picture, and you can see the reflector fully deployed on the right. And we have a boom that deploys the reflector itself away from the CubeSat so that you have a fairly good F over D to achieve the mission requirements. So we actually used this reflector to achieve an X and Ka band antenna for telecommunication purpose. And we achieved more than 72% at X and Ka band. And I'll show you some of the results. Those are the feed at X band and Ka band. Below, you can actually see the model on TCRA grasp, where you can see the CubeSat bus, the boom, and the reflector. And those are the results at X band. You can see a very good accuracy between calculated and measurement. However, you can see that our cross polarization is actually fairly high. You could improve that. It's not too constraining, but for our case, we didn't really care because I think we have so much margin that we didn't want to spend time optimizing that. And you can see that the accuracy between calculated and measured in terms of directivity, gain, and efficiency is excellent. So that shows that these antennas are fairly very reliable after deployment. At X-band, the mesh opening per inch loss are actually very, very small, almost negligible. And the surface accuracy as well is less than 0.1 dB, so you don't need to worry about that at X-band. At Ka-band, that's another beast. At Ka-band, the OPI is about the surface mesh loss due to the opening per inch is about 0.25 dB, so you need to account for that. But the surface accuracy is much more significant. We had about 1.1 dB of loss due to the surface accuracy that was about 0.38 millimeter RMS. We think that for a flight version, we will be able to reduce that down to 0.25 millimeter, which will bring the loss to 0.6 dB only. And overall, we still achieve very good efficiency, about 62% efficiency at downlink and 57% efficiency at uplink. And the accuracy between calculating and measurement is excellent because in our calculation, in the TCRA grasp model, we included the surface mesh that we actually measured after deployment. So, like I said, I discussed about this very nice demonstration that we achieved using these two CubeSats, the radiometer and the RainTube active radar. And as a result, we are now considering launching a small sat that will fly these two instruments as such with no modification. We will have the radiometer and the RainCube instrument co-located on the small satellites, and we will deploy a much larger antenna for the active instruments for RainCube. This one will be about 1.6 meter, which will allow us to have a much smaller footprint on the ground and as a result, a much better resolution. The trick here is actually to use different feed arranged in a way so that you can have 3 dB of beam width overlap if you take into account for the spacecraft motion. So as you can see, if you look in this direction and move, you will have this 3 dB between this beam, this beam, this beam, this beam, and this beam, which is what you see on the right. And that's where the horn arrangement was critical to do that. And that will allow us to do a map Earth coverage much faster than what we would with a single horn. So that's the trick that the scientists wanted to use to do so. And with this design, we haven't built this antenna and tested it, but we're very confident because as you could see on the two other design, we always were spot on the prediction. So we think that we can achieve more than 70% efficiency at Ka-band, which each of these horn at Ka-band, 35.75 gigahertz. Okay, so then we looked at other design, and this one is a small satellite where we're considering flying a solid reflector and a mesh reflector not too far away from each other. And we also want to use a multi-feed to be able to have different beam overlap. In this case, again, using the motion, taking into advantage of the motion of the spacecraft, we can get 1.5 dB of beam overlap. And the trick here was to be able from two different antennas to get the same beam overlap on the ground, so the same footprint. And that's actually what you can see on the bottom here. That's what we managed to do. Despite the fact that we're using a Cassegrain solid reflector and deployable offset mesh reflector, we managed to obtain the same radiation pattern. And that's what you see here. This beam overlap, the solid line is the solid reflector and the dashed line is the deployable reflector. And the way we did that is that first we designed the solid reflector and then we designed the mesh reflector to match the beam of the solid reflector using an optimizer. Then I'm going to talk about metasurface antennas, which is fairly new in the world of space. As a matter of fact, to the best of my knowledge, no metasurface antenna has been flown up to date. And our goal is to launch the first metasurface antenna in the next 2-3 years. So this work has been funded by ESTO through an ACT program. We're very excited by this work because we think that it will open up new opportunities in future missions. So the first one is this flat antenna that has a 3 beam. So we're taking advantage of a quasi-optical feeder, which is called a pillbox, to achieve 3 beam pointing. And all we do is by offsetting 2 feeder horn, exciting a reflector, which is a flat reflector here, we can excite the top layer through these coupling slots. We can excite this top layer and then we can use any type of metasurface on the top layer to get the beam that we want. And so basically this pillbox allows you to get the same amplitude on the top surface, and it also allows you to convert a spherical wave into a planar wave on the top layer. And when you are changing the feed horn, you are actually changing the phase distribution across the top layer. And that's how you're getting this beam pointing change. And I'll show you that in more details. You can see a picture of the prototype on the left. And the metasurface is actually a slot with this pattern. And I invite you to read the paper. Oh, I did not put the reference. I have a reference at the end that I invite you to look at, where there is more details and where we explain how to design this metasurface to get the beam pointing that you want. So if you excite feed 1, you actually get a beam pointing at the center. And if you excite feed 2, you get a beam pointing at 45 degrees. And if you excite feed 3, you will get pointing at minus 45 degrees. And we demonstrated that successfully. As you can see, the agreement between calculate and measurement is good, but not that great, because the side lobe are getting a little bit high on this side, and that was due to misalignment between the two layers. The nice thing about this antenna is that everything was fabricated using micro machining. The bottom layer is made of silicon, and the top layer is made of gallium arsenide. The reason why we really wanted to use gallium arsenide on the top layer is that we could use Schottky diodes to get a full control, 2D control by changing the state of these diodes on the metasurface elements. And by doing that, you can control the beam on one direction. And here is the reference I was talking about that I invite you to read if you want more information about this. The second design was done by my friend David Gonzalez, who was a postdoc at JPL and who's now a CNRS researcher in France, in University of Rennes, where I actually did my PhD. So the reason why we worked on this design is because we wanted to get rid of all the drawbacks of this metasurface. So the first drawback, they are made of dielectric, so they are lossy and they are very narrow band. And also, if you go in an environment where the radiation levels are high, the IESD becomes a problem. And so that's the reason. So if you make it all in metal, you're no longer susceptible to thermal, which is a significant concern when you are made of dielectric and you're narrowband. And so this is the reason why we wanted to make an antenna, a metasurface antenna, entirely made of metal. The reason why this antenna is attractive is that it's completely flat and it doesn't require a polarizer. Polarizer are fairly bulky, take a lot of volume. In this case, we actually achieve the circular polarization with the metasurface itself. We can not only get circular polarization, we can also get linear polarization from these antennas. Everything is included in the reference that I provide in the bottom. Like I said, metasurface antennas have been put aside mainly because they are low efficiency. But with this design, we achieved 50% efficiency at the center frequency. So they are now becoming attractive, and you can find applications where they become extremely interesting, such as lander and rover, where you don't have a lot of storage volume, or even small sats. So this is where you need to come up with technologies, but also find the niche where they fit perfectly. If you can fly a reflector, you would not suggest to have a metasurface instead. You would just fly a reflector. But if you have to fly something that's completely flat, then the metasurface becomes interesting. And as you can see, the accuracy between calculation and measurement is fairly good. And it's not only fairly good because it agrees fairly good, but because of the technique that we use to fabricate it. And the video doesn't work either. But the point of this video was to show you that this antenna was fabricated using additive manufacturing, and it takes less than 5 minutes to fabricate an antenna like this. 5 minutes only. So imagine if you want to fly a very large constellation where you try to minimize the costs by fabricating hundreds of antennas, one after another, this is the perfect technology for this. So just keep that in mind, because those are the things that you need to be aware of. So following the first design that I showed you earlier, where the antenna is flat and we're using a pillbox and then on top a metasurface to get the pattern that you want, we come up with this design, which now is entirely made of metal, operate at 15.5 gigahertz, where we want to have 3 dB beam with overlap between the transmit and receive antenna. So you have 2 feed horn, one that transmits, one that receives, and it's combined to a CMOS system on chip radar that has a technique that in real time allows you to cancel this coupling between the two antennas. So even though the antenna provides about 20 dB of isolation between the feed horn, this technique that is implemented in the CMOS on-chip radar allows you to bring it down by more than 40 dB of isolation on top of that. So it will be 60 dB of isolation. So this is a technology that we've been developing. The antenna has been designed. We still need to fabricate it and test it, and then try it with the actual system on chip radar. And this will fly on a UAV for demonstration. So we're very excited about this, and I hope that we'll be able to share more results in the future. Then I'm going to talk about Europa Lander. Europa Lander is one of the most exciting missions that JPL has been working on, which is a mission concept. We are still in pre-phase A. We have a lot of technology development ongoing to make this mission possible. The enabling technology for this mission was the antenna, because this antenna enables direct link to Earth from the surface of Europa. Why was this enabling? Because initially we were considering sending an orbiter to provide telecommunication capabilities, but the cost of the mission was just prohibitive. So we were asked to look at reducing the cost of this mission by more than twice to be able to make this mission possible someday. And the first answer was, well, the only way we can do that is to do DTE, but everyone thought it was impossible because the requirement to do DTE from the surface of Europa was to design a very large antenna, more than 80 centimeter by 80 centimeter, with more than 80% of efficiency, preferably that does not deploy, because it would be very challenging to deploy in a cryogenic environment. It needs to survive the cryogenic temperature. It also needs to survive the high radiation levels on the surface of Europa, which are something that we've never seen before or never designed against before. And finally, it needs to be entirely flat, because we don't have any storage volume. We only can store on the surface of the lander itself because of the landing space. I don't know how to call that. Never mind. And so then we come up with this design that actually meets all the requirements, despite the fact that nobody thought it was possible. We find a way to do it. So this antenna provides dual frequency with circular polarization and provide more than 80% efficiency at both frequencies. It's entirely made of metal. It can survive the cryogenic temperature. It can operate at cryogenic temperature, and it can also survive the high radiation environment of Europa. So when I say survive, the antenna can always survive, but you want to make sure that the antenna is not consistently going to discharge, because these discharges are going to propagate to the telecommunication subsystem, and it will damage some of the hardware, critical hardware. So we design it in a way that this will not happen by making sure that every single component, every single part of the antenna is DC grounded, which reduce the likelihood of IESD events. So the first prototype that we fabricated is an 8x8 subarray. We achieved the aperture efficiency that we needed to achieve. So when I define efficiency, let's be clear about this. This is the ratio between realized gain, so that includes all the losses, over the maximum directivity that you can get out of the aperture of the antenna. And we got more than 80% with this efficiency definition. And you can see that the agreement between calculated and measurement is perfect. Then comparing this technology with what has been used before, so on MSL, they achieve about 50% efficiency. On MER, 25% efficiency at uplink and 50% efficiency at downlink. But those will not survive the environment of Europa because they are mainly made of dielectric. And then this one, which is a radial slot array, which is the one that you see on the bottom, achieved, that was the baseline for this mission initially, achieved 37% efficiency at uplink and 18% efficiency at downlink. And that's the reason why we thought that DT was not possible. And as a result, our antenna allow us to be smaller, less mass, relaxes the pointing requirements, and allows us to handle much higher power. And as a result, you can combine it with a tweeter, a 100-watt tweeter at X-band, and be able to achieve much larger data rate. So if you go from 25 watt SSPA to 100 watt a tweeter, you get 6 dB of improvement there on top of all the other gain improvements. So this is why we're pushing for this subarray for future Mars mission as well. So then we built a 16x16, which consists of 2x2 subarrays put in an array, and the array, the 2x2 subarray array, are excited with waveguides. So the waveguide is dividing from 1 to 4 ports. And here is the agreement between calculated and measured. The efficiency that we obtain on the first prototype are still very impressive. And the agreement between calculated and measurement is just very impressive. You can barely see the difference between the two. So this shows you how the antenna actually falls on top of the surface, and then it deploys with the gimbal, and the gimbal will be pointing toward Earth. Yeah. And finally, we fabricated a 32x32, and we measured. And as you can see, we also obtained a very good accuracy. We qualified the antenna by doing IESD measurement, TID, not measurement, testing. So we basically put it in this vacuum chamber where we go to cryogenic temperature, and we bombard this antenna with electrons. And we do that so that the 3 mission life of total ionizing dose are being reached. And also we make sure that the rate of charging is the same as the real mission, so that you can simulate what the IESD discharging and the rate of discharges that you will see. And we did not see any discharge, or the only discharge that they have seen, they couldn't tell if it was only noise or if it was actual discharges. So that tells, and that was actually the first time ever that they tested a piece of hardware and they see such low discharges, and that's why they couldn't tell if it was noise or not. So our antenna is ready to go to Europa. We reached TRL6, which stands for technology readiness level. And whenever we go into a flight missions, we want to be at TRL6 to move forward with the technology. This is a nice picture of the Europa lander. Here you can see the actual antenna that I was just showing that we tested, so that you have a good scale idea. And also here you can see the landing legs. These legs allows the lander to land on any type of topology. And so we don't expect the surface to be perfectly flat. And so we need to be able to land on chaotic surfaces. And that's why our mechanical team is working on that as well, and they are making a lot of progress in order to reach this TRL6 grail. I think I'm running out of time, so I'm probably gonna skip quite fast. This is a mission, surface water and ocean topography, which is a Earth.
You have you have time for 15 more minutes because we have.
Okay.
Next session is at 11 o'clock our time, half an hour later.
Okay, perfect. Thank you. So this mission is an Earth science mission. It's a very, very large spacecraft for which we have done a lot of work, and you will see an example of this work. So we have developed a telecommunication antenna that provides dual polarization, which allow us to communicate with two different polarization at the same time within 8.025 to 8.4 gigahertz bandwidth. So we have two ports that goes into a polarizer. Each of the ports provide different polarization. One is right, the other one is left polarization. This antenna was designed to operate on a very crowded nadir deck where there is two large reflectors. There is the altimeter that you see here. There is the radiometer that you see here that would cause strong multipass and a strong multipass that will generate interferences. And then the antenna also need to have a very good cross-polarization discrimination, because the cross-polarization of one polarization to another will actually be additional interferences as well. So the requirements are that the XPD needs to be more than 20 dB at 60 degree off borosides to minimize cross-polarization losses. And we also need a very rapid roll-off after this 60 degree off boroside, so that we don't have multipass or strong multipass contribution. And that's why past 90 degree, we need to be less than minus 15 dBi of gain. So we designed this antenna, which is externally corrugated horn, and combined with a polarizer. Like I said, each port provides the two polarization. And you can see here at the 60 degree that we get a very good cross-polarization discrimination, and that's what we see on the bottom. So if you look on the bottom, we have, in free space, we have more than 25 dB of cross-polarization discrimination. Once you do that, you still need to verify that the performance are met on the spacecraft and across the temperature. So we tested the antenna from minus 100 to plus 100 degrees Celsius. And we simulated the performance on the spacecraft using TICRA-GRASP, where we modeled all the key elements that could contribute. And you can see that the XPD still met at 60 degrees off borosides. That was a very stringent requirement that was successfully met by developing this antenna. And we didn't have a lot of time to come up with this design. It was less than a year. I mean, the design, you need to come up with a design that shows that it works very quickly. It's less than a month. And then to get to a prototype would be about 6 months, more or less. And then we had a flight hardware that was fully tested within a year and a half. Again, publication below, feel free to take a look at it if you want more details. So here is actually a video of the spacecraft deploying the large deployable antenna, which is a reflector array. And it's very, very high power. And so we did a lot of work to make sure that everything will work properly, since we have a very, very high power being radiated from the radar toward the nadir deck. And I'm not going to go into the details for that, but here I wanted you to have a grasp of the complexity of the deployment. It's K-band, so the surface deployment needs to be excellent, the deployment accuracy needs to be excellent, and everything needs to be extremely stable because this is an interferometer. So the phase accuracy between these two antennas needs to be very, very good. Okay, and now I'm going to talk about the Mars helicopter. So for the Mars helicopter, we designed the antenna on the helicopter itself and also on the rover. And I'm going to show you how we made sure that the link will close with these two antennas and the process to do this. So first, in the real life, you have constraints that you really don't have in the academy world. So I really want people to be aware of this constraint that we have when we design these things. So first, the ground plane that we have on the helicopter is very small. So we actually have a ground plane where we used as a reflective surface is the solar array. And that was the only way. That's the only option that we had. So because the ground plane or the reflective surface is asymmetric, you will have a cross-polarization component that looks like this. So it's not ideal. And then if you account for the blades that are made of carbon fiber, it's also a very good reflective surface at 900 megahertz, which is the frequency of operation for the telecom subsystem for the helicopter. So when these blades are rotating, the cross-polarization will also be affected. As you can see, the gain remains fairly the same, but the cross-pole keeps moving. So you need to account for that when you're looking at the link budget. On the rover gave us the worst spot on the rover. And as you can see, the ground plane is even smaller, but we had to deal with it. So, okay. So we have a monopole antenna that we made bulky enough that it would survive the launch vibration and shock requirements. And as you can see, because of the multipass and the shadowing of all of these components on the rover, the gain is not great. The gain can be fairly low in some directions, and the cross-pole is not great either. So you need to account for that in your link budget to have a proper account of the polarization loss. So V polarization is what we're using. H polarization is the cross-pole. This is the map that we have when the helicopter is on the ground, when it's landed. And this is when we will transmit most of the images back to the rover. We can achieve 250 kilobits per second in the dark green spots, and we can achieve 20 kilobits per second on the light green spots. The center diameter, the center circle has a diameter of 250 meters, and the outer circle is 1 kilometer diameter. Most of the communication is going to happen within this 200 meter diameter. And so in average, we will be fairly good in most cases. In the worst case scenario, which we never designed for, it means that we will have the worst case alignments between the helicopter and the rover, and the blades will be in an orientation so that we have the worst polarization losses. You can see that in some spots we might lose communication. So we need to be aware of that, so that if that's the case, we know what to do. We can just spin the blades, or we can rotate the rover if needed. And when the helicopter is flying, there is no problem at all. You can see that the link is no problem. We can close the link within 1 kilometer without any issues in most cases. By the way, average cases is more than 90% of the case. So you need to be aware of this statistic when you are making an assessment as well. And that's the reason why we never design for worst case. Otherwise, that would just not make any sense, and the cost of the mission would go up very, very quickly. So we went and we did a field test where we have two mock-ups, the mock-ups for the rover, where we have the EM antenna, and on the other side, we have the helicopter mock-up. We placed it about 200 meters away, and we compare the measure results. We actually, you see the platform that's under the rover, we actually rotated it to do an assessment of the radiation pattern as well. So we could assess how the pattern of the antenna on the rover will affect the receive power. And we've never seen anything worse than the worst case prediction, which is exactly what we wanted to see. And you can see that we were never lower or on the average case most of the case. So that means that our link budget assessment was actually very, very good. So to conclude the talk, I have listed a few publications that we have in the literature published in the past 5 years. So I invite you to take a look at them if you're interested in this topic. We also have this month a publication that was released on the Mars helicopter on the topic that I was just presenting. So feel free to take a look at it where you can have more insight on how we actually perform all of this calculation. And to finish, I have a book that's coming up early 2021, published by Wiley, which is entitled CubeSat Antenna Design, which I invite you all to get a copy. And I think there is a lot of interesting content where we try to convey all of how the requirements are flown down to the antenna team and how the antenna team is working with the system team to actually work this requirement to come up with the simplest antenna design and the most robust mechanical design deployment, providing the best RF performance in taking into account all of the design constraints that we have. So I cannot emphasize enough how important it is to work very closely with the mechanical engineers and also the system engineers to work these requirements, to have a better trade, try to negotiate this requirement where it's possible. So I always say a good antenna engineer is an excellent system engineer. So don't close your bubble just into your expertise. You want to understand how telecom system engineer works. You want to understand how the radar also works so that you can work with the system engineer the requirements, because they actually don't understand what your constraints are. So those are the trade-offs that you need to work as an antenna engineer to get the best out of your missions. So thank you very much for your attention. Now I would like to open to questions. I apologize for the issues that we had early on, and I hope there is questions that I can answer.
In the chat box, we could take it.
Well, the session is now open for discussion. Questions are invited from the audience.
Sir, there are a few questions in the chat box. Would you please answer them?
Okay.
Okay, let me see if I can. I don't think I can see the chat while I'm sharing.
If someone could read the questions, then it would be good.
Yeah.
Sir, there is a question on the second or third slide talking about Marco X-band deployable reflected array. And the reflect array has 2 patch antennas on both sides of stable core material. Why do you need 2 patch arrays instead of 1?
Sorry, repeat the question about Marco. You said,
Yes, sir.
why is there? Yeah, please repeat the question.
So there is a question on the second or third slide talking about Marco X-band deployable reflected array. And the reflect array has 2 patch antennas on both sides of stable core material. Why do you need 2 patch arrays instead of 1?
Okay, I think, so just to be clear, a reflector is not a patch array. They do look like patch array, but it's not. It's a resonant element where we change the size of them to change the phase across the surface of the reflector. So that's saying the reason why we have the reflector on each side, the same pattern, is from a thermal point of view. If you have a perfect symmetry on the reflectory surface, you reduce the surface gradient across the surface. And so the surface will not bow as much. So that's the reason why it's very important to have something perfectly symmetrical.
This is Sudhakar.
Yep.
Yeah, the question is from my side. So if you have two arrays with a stable core, instead of that, why can't you use one reflector array and increase the stable core size? It reduces your cost, I believe, cost and mass.
Yes, so we actually looked at that. That's exactly what I was saying. So we look at different options. One option was to make the composite larger, but if you do that, the surface is still going to bow much more. So that was the trade-off that we found in terms of better surface flatness and mass. So we actually went through this trade-off early on. Yeah.
Okay. Thank you.
Hello.
Yep.
Say the array which you showed for say I think 16 by 16 possibly of a microstrip array, which is from the metamaterial side. Okay. Towards the end, see there you have a slot at the center of each of those patches. Are they really meant for only increasing your bandwidth, or it's for your specific
yeah.
you're looking for?
Here's the E-plane.
Yeah, excellent question. So the element here is actually excited on these bottom points, and we have on the center here we have a post that allows us to be directly in contact with the ground plane. So everything is in metal and holds against each other thanks to this post in the center. It's located in an area where the current is very close to zero, so it does not interfere with the RF of the patch elements. But then the shape, the reason why we have this slot is to get the circular polarization at 2 frequencies.
Yeah, that's what. Yeah, that's an important thing. Nice. So this when this is already flown or is about to be.
No, so that design was, we started working on that 2.5 years ago, I think, or maybe 3 years ago. We've reached TRL-6 now. So now we're ready to fly it for future mission. We specifically developed that for the Europa lander mission concept. And we brought it to TRL-6 for that purpose. But now we realize that this antenna has a lot of features that are advantageous compared to the antenna we're currently using on rovers and lander on Mars. So we're trying to infuse this antenna in future Mars missions as well.
Now, you were trying to qualify this at cryo temperatures also. So do you just
it has been qualified.
and then do the measurement?
So the way we qualify over thermal is that there is different type of tests that we do. There is a thermal cycling test where we verify that the antenna is surviving. So we have survival range. We have, sorry?
It will be passive during that time.
Yeah, for survival, it's passive, but for operational, we're actually checking the S parameter of the antenna. In that case, for the Europa mission concept, since we wanted to check the performance of this antenna at cryogenic temperature, which is lower than -170 Celsius, we're actually doing a radiation pattern measurement at cryogenic temperature as well. So we're putting that in an enclosure, foam enclosure that will not interfere with the RF performance, and we will use liquid nitrogen to go to this cryogenic temperature. And in real time, we'll get the radiation pattern and gain of this antenna. That's how we're qualifying to.
This is a great setup for making the measurements for this particular one. think it will go a long way.
Exactly, because
maintaining such type of antennas for future missions.
Yep.
Yeah. So thank you very much. This is Mahadevan from ISRO.
Thank you. Thank you.
Thank you.
Sir, there are a few more questions in the chat box. How do
Okay.
you choose which polarization to use when designing a spacecraft antenna?
Oh, so it's pretty straightforward. For telecommunication, it's always circularly polarized. For space to Earth, because we don't want to be impacted by the orientation of the spacecraft. If you have linear polarization, you need to make sure that the transmitting antenna and the receiving antenna are lining up. So you don't want to be dependent on the polarization. And circularly polarized is also less sensitive to rain, for instance. For the science mission is driven by science. So usually the scientists tell us what are their polarization requirements. Sometimes they want V and H at the same time. More rarely they want V and H and then they combine to get circular polarization as well. Sometimes they want circular polarization, but it happens much less. For the Mars helicopter mission, we use linearly polarized because it was more convenient for near-range communication, and especially in an environment where we have a lot of multipass and shadowing. So that's the reason why we used linear polarization.
Thank you, sir. So there's another question. Is it possible to design antennas at high frequencies such as terahertz range?
To design any antenna or a specific antenna?
I think the question was just asking about any antennas. Is it possible to design?
Oh, yeah, of course. We have designed and fabricated a lot of terahertz antennas. I invite you to look at Dr. Gautam Chattopadhyay's work, where he has extensively published on terahertz instruments, including antennas. Most of the time, they use horn antennas. Multi-flare horn are very convenient at terahertz frequencies because you can just drill and make arrays of them. And then there is other designs that are entirely micro machine antennas as well. So they do horns, they do metasurface antennas as well. The one that I was just showing with entirely made of metal. We made one, David Gonzalez designed one with, he called it the fakir bed antenna. It's made of post, where the height of the ground below the post changes. There is a lot of antenna solution at terahertz, but you need to be cognizant of the losses that you will incur with the different technology that we use, and that's why horn antennas are usually the best way to go for terahertz antennas.
Okay, sir.
Next question.
Sir, could you please comment on the transmission power and directivity used by ground stations to communicate with satellites, especially when dealing with interplanetary missions and even interstellar missions like Voyager 1 and 2?
Oh, yeah. I'm afraid I'm going to give you the wrong number. Yeah, I wouldn't venture give you the numbers. I don't exactly remember the gain of the antennas, but most of our deep space network antennas operate at X-band and K-band. And for Voyager, since the Voyager is so far away, our division consistently tried to improve the performance of the DSN, and I know that they've been working very actively into increasing the high power amplifier outputs. And I can't remember, I think it's 20 kilowatts, but I can't remember for sure. So I invite you to double check the number of where the state of the art stands for. All of that are readily available online. So feel free to check the JPL website where all of these numbers are shared.
Okay, sir. So the next question is, what is the application of helicopter versus rover on Mars?
Oh yeah, good question. So the purpose of the Mars helicopter is a technology demonstration. And in this case, the team that actually come up with this technology wanted to demonstrate that we are capable of flying on the surface of Mars. And the reason why it's so challenging, it's because the density is 1% of the one of Earth. And to be able to fly on the surface of Mars, you need to generate much more lift. So the RPM of the blade is much higher compared to the typical helicopter that we're using on the surface of Earth. So as a result, the helicopter is limited in terms of mass. So the constraint was 2 kilograms. So every subsystem that delivered to the helicopter had very, very strict mass allocation, and it was non-negotiable. There was very limited margin allocated for the subsystem, and we knew that if we exceeded this 2 kilogram requirement, we would not be able to fly on the surface of Europa, on the surface of Mars, sorry. And so that, yeah, so the goal of Mars is to go on Mars, land, fly, and demonstrate that we're capable of doing these flight maneuvers, and that will be a success for the Mars mission. And eventually will open up for future helicopter mission on the surface of Mars that will perform science. And we're looking at different instruments for future Mars helicopter missions, so that we could launch a constellation of those on the surface of Mars that could bring their own science. That's the end goal. Next question.
Sir, what is the material of reflector used in rain cube? It seems translucent.
The material used? Is that the question?
The material used in reflector in rain cube.
Yeah, so these reflectors are mesh reflector. So they are very similar. Actually, I don't have a picture. That would be interesting to share a picture here. You can also see it here. You can see it a little bit better, but they are mesh which are gold plated, and we pick the opening per inch of this mesh to be as reflective as possible at the frequency of operation. So at K-band, we tend to use 30 opening per inch or more. On RainCube, we managed to use 40 opening per inch, but those type of mesh are much more difficult to find. So that's why on this 1 meter reflector, we revert back to 30 OPI. Yes, Sudhakar.
Yeah, the material is gold-plated molybdenum.
Yes.
Yeah.
Yes.
It's about 1 mil in diameter. Hey, since you're on that RainCube, you have you showed the half-meter deployable reflector. Can you go back to this? Looks like it has a large FOVD. I don't know what FOVD you are using.
No, the FOVD is 0.5.
Yeah, that's a lot. So don't you think reducing FOVD will simplify the feed deployment?
I think we discussed about that on one-on-one. That's actually a very good question that people ask me all the time. So
what's the
Dr. Rao is saying that Dr. Rao is saying that if you used a lower FOVD, then you would have the subreflector much more lower, and you wouldn't need to deploy the subreflector. So that's his argument. However, if you do that, then the reeds are going to be, the curvature of the reeds is going to be much more significant, and you will not be able to make everything fit into this small canister. And that's a very good question, because that's actually the first thing that we looked in when we did a trade study to see what could fit and what should we be doing in terms of optics to minimize the number of deployments and come up with the best optics for this antenna. And that's ultimately the one that we picked. And in this paper that I provided on the bottom, we actually spend a lot of time explaining all the trade-off and how we came to this optics and why we picked a Cassegrain antenna.
Okay, thank you.
So one more question. When is your book is going to be released?
Early 2021, but it's already in pre-release, so you can already pre-order it.
Okay, thank you, sir. We are extremely thankful to you for sharing your deep knowledge about this topic with us, and your session was full of enthusiasm and knowledge. Thank you, sir. I also
thank you very much, and again, I apologize for the technical issue. Thank you for your patience.
Thank you, sir. I also thank the distinguished chair of the session, Professor A. Unnikrishnan, sir, for his valuable presence. Thank you.
May I add a few sentences? May I have few views from my side?
Sure, sir.
In fact, it had been a very wonderful presentation. He took us over a wide range of topics. And what really attracted me was the perfect sort of precision by which the results were presented. The temperature cycling, for example, is something which I think is just really mesmerizing for me. I was quite surprised that you can have that kind of facility for cycling the temperature of such a large range, which I think my colleague from ISR also was quite appreciating that. Also, what I attracted is that the academicians have to work in line with the systems engineers. I think there was a mention from Professor Kahat that is necessary. I think that throws light on the fact that the academic community has to work closely in association with the system engineers so that you can fabricate and produce the proper technology, the right kind of products out of the technology that is being developed. So overall, it has been a very wonderful presentation, and we are really thankful to you for the excellent amount of, for a large amount of technical material that you could provide us. So it's only proper that we need to know about the full biodata of the presenter, which I could not present at the beginning. I'm sorry for that. The conference organizers full biodata of this wind up. Would you do that? Hello?
Yeah,
Yes,
no
sir.
problem.
Yes, sir. Yes,
Kindly do that. Kindly give the full biodata of the speaker before we wind up.
Yes, sir. Because
I could not do that at the beginning. I should have done it, but because I wanted to start the whole session and was eager to listen to the speaker, kindly do that now.
Yeah, sure, sir. Because it is such an impressive talk, and it's so impressive because we see that he's so young and inspiring the youngsters who are attending the program. Dr. Stahat has completed his master's and PhD from University of Rennes in 2012, and he's a senior antenna engineer with NASA, as we have seen. And he has got 4 books to his credit, several patents, hundreds of articles and conferences and journals. And as he mentioned, his new book is on the line, and he has been awarded co-invented and award-winning rain cube mesh reflector antenna is being used, and he's the recipient of several other awards like CST University Publication Award, 2011 Best Paper Award, and NASA Early Career Achievement Medal Award, and so many. So this is very long, and it is shared in the website. So I'm sure we'll be hearing more of you in the future, and thank you so much for accepting our invitation to present during our APSYM 2020. Thank you again. Thank you, Unnikrishnan, sir.
Thank you. Bye.
Thank you. I request all the panelists to switch on the video to take a screenshot.
Thank you, sir. Thank you, everyone. Now we are entering in the first technical session of today, which is based on antennas. There are 6 paper presentations in this session, and I would like to invite our chairs Dr. Gopi Krishna from Calicut University, and Dr. Deepu V. Nair, Senior Engineer from Cambium Networks. I would like to hand over the platform to the chairs.
Thank you, Jayasri. I think I should wait for Dr. Deepu. Am I audible?
Yes, sir. Yes, sir.
Yes.
Oh, thank you very much. Okay. I'm not sure whether Dr. Deepu has joined.
I have made Deepu sir a panelist. So, Deepu sir, you can turn on a cam.
Good morning, Gopi Krishna.
Good morning, Deepu. Yes.
I think.
Can we start?
Yeah, sure.
Okay. So, dear attendees of APSYM 2020, on behalf of the organizers of APSYM 2020, we welcome you all to the technical session 3 on antennas. And we have 6 papers in the lineup for presentation. And the first one is dual band waveguide fed cylindrical dielectrical resonator antenna. And this will be, this is written by Shiba Wagis, P. Abdullah, Sam Colano, and Mary Babu, and Jasmine PM. So I invite
Gopi, this is, I think, a no-show paper. The authors are not.
Okay.
Yeah. So we'll go for the next one.
So the next one is planar antenna with a rectangular parasitic patch and strip for ultra-wideband applications. And it's written by Balaji RS and Sudhir Bauda. So I welcome the authors to present the paper.
I think the video is muted. Can you turn on the computer sound while sharing? You can share again and check the computer sound box.
I'm a fourth year. Good afternoon, everyone. My name is RS Balaji. I'm a fourth year electronics and communications major from Bitsula and Kegambilla Goa campus. And I'm presenting a planar antenna with a rectangular parasitic patch and a strip for ultra wideband applications in this presentation. Getting into it, what are the objectives? The objective was to design a compact antenna. Design it on FR4 substrate, which is easily available, it's economical, and it's low cost. And we wanted it to function for ultra wideband range of frequencies, that's from 3 to 10 gigahertz, and for X band, which is from 8 to 12 gigahertz. And what are the applications of the antenna? Well, it can be used for WiMAX, WLAN, C band, or for X band. Right. Anyway, so what we have achieved is 14 cross 14 cross 1.5 millimeter cube size on the FR4 substrate, and it functions for 2.83 to 12.22 gigahertz. So here's a short literature survey that we've done, a comparison of those data, mostly for bigger antennas, but the essence of it was to get an idea of what designs work and what designs don't work. So for instance, a deformed ground plane, or using slits and slots on the patch or on the ground plane helps you get an ultra wideband operation region, right? So that's the key takeaway from this literature survey. Moving on, here's the geometry of the antenna. There are some design elements I'd like to point out over here. One is the deformed ground plane, which turns out to be key in this particular application. The second one is the narrowing of this feed line from over here to over here, right? And the next thing is the cut on this ground plane, and then the strip that we add on top of it. And then there's this rectangular parasitic patch on the front, It also, please note over here that it lends an element of asymmetry to this antenna, which we'll discuss later in this presentation. So this went through a 4-stage development, not exactly 4 stages, there were more stages of course, but it's been simplified so that we can look at the performance of the antenna in each of these stages, which we've done over here. So we notice we start from this black line and then we move to this turquoise color, and then we go to this dark blue color, which just falls short of our region of operation. It doesn't reach 12 gigahertz. And then we add this strip on the ground plane, which actually takes us past 12 gigahertz, right? So that gives us somewhere between 3 to 12 gigahertz. So what we'll do now is we'll take 4 dimensions from this geometry and vary them to see the importance of these dimensions. Of course, I've picked the ones which cause the most change, the most sensitive dimensions in this, and I've selected 4. So let's look at it. So over here, we vary E1, and what we do is we keep the bottom fixed and then we vary the top edge. We increase it, decrease it, see how the performance changes, and then we notice that this red line is what gives the optimum results, and that's what we've used. Similarly, we change E2 as well. So what we do over here is we keep this top edge fixed and then we change this bottom edge. We move it up and down and we see how the performance changes over here. Once again, there's only one value which gives us the region that we are looking for. And then moving on to the ground plane, we look at what size it is required. Generally, it's recommended that we keep it at a minimum of 1.5 millimeter from the bottom, so that's what we've kept over here. And this is because when you actually fabricate it, your results sometimes tend to go different from what you get from the simulated results if you don't keep it to a minimum of 1.5 millimeters. So that's been set as a lower limit. And then of course we move up and then we notice that that doesn't really help things. Right? So this value of 2.5 for this ground plane is what is optimal for this particular functioning. And then finally, we also vary K2 by keeping the top edge fixed and then we change the bottom edge. So we take it closer to the top edge. So we go up to 9.3 mm and then it doesn't really work out. And then what happens if it gets connected to the ground plane is also simulated over here. So that's the turquoise line we see in here, which is completely not what we are looking for in this antenna. So that brings us to the end of parameterization of these dimensions. Moving on, let's look at the simulated gain and radiation efficiency across this operating range. So what we get is the peak gain, it comes out to 2.1 dB, and then the peak radiation efficiency is 51%, which is typically lesser than what we observed in the literature survey. However, the reason for this lower value is the size gains proportional to directivity. Directivity is proportional to size, and what happens is any of the literature survey that we look at, let's say we're looking at somewhere between 300 mm square area, then we get a peak gain of around 4 dB, and this antenna's area is 196 mm square. And so proportionally we get a decreased gain which comes out to a maximum of 2.1 dB. And also it falls as the frequency increases, and this is also true for peak radiation efficiency. It decreases with size, and also it decreases with frequency, because once you start going towards the higher frequencies, you start seeing ohmic losses and other kinds of losses in the antenna, which brings the radiation efficiency down. Right. And moving on, if you're looking at the copolar plots, then what we observe here is supposed to be bidirectional, and for the H plane supposed to be unidirectional. However, we see slight deviations from that pattern, and this is attributed to the asymmetric element in the antenna's design. Right, as we notice in the front of the antenna, there was this asymmetry, and that's the one which causes these small deformations, which should otherwise not be there in a symmetric antenna. And moving on, if you're looking at the input impedance, the real and imaginary parts, this red line gives you the real parts, supposed to be somewhere near 50 ohms. This is what we've designed it for, and it does stay near 50 ohms for the operating region. And the imaginary part is expected to be 0, and it is very close to 0 for most part of the operation region. and in the operation region, it's noted to be less than 0, which indicates a capacitive kind of an antenna, right? It's a capacitive antenna over here. Moving on, if you look at the current surface current distribution, this also gives us good insight into what element is causing what frequency of operation. So if you look for the redder arrows over here, you notice that this narrowing, right, this narrowing part of it, it contributes 3.5 and 5.2 gigahertz. Right, so this can be also compared over here, where this narrowing is present, and then you see this dip between 3 to 5, right? So that's what it corresponds to. And then, of course, while adding the final strip, you notice that you get a good resonance near 5. So once again, if you look at the strip that we've added, you see current in the greener portion, whereas the rest of it is blue, which means lesser, right? So which means this strip is actually contributing to operation in the 5.2 gigahertz region. And moving on, at the higher frequencies, once again, we notice that the strip on the back is contributing, and also this cut that we made, the parasitic patch on the front, so that's also responsible for these higher frequencies, which we can clearly see over here, and not so much over here, right? But over here it really marks it clearly, right? You see the red regions over here. Anyway, that brings us to the conclusion of this presentation. Here are the outcomes. We've designed a compact antenna. There's a fractional bandwidth of 124.81%, peak gain of 2.1 dB, peak radiation efficiency of 51%, and the antenna is useful for WiMAX, WLAN, C-band, and the X-band applications. Objective of compact size being met. It's being designed on the FR4 substrate, and it supports UWB and X-band operation, which were the objectives that we outlined earlier. And here are the references. With that, my presentation comes to an end. Thank you very much, and if there are any questions, I'd be happy to take them.
So, okay, the paper is open for discussion. If there are any questions, it can be asked now.
Gopi Krishna, I have a couple of questions. One of the slides you are mentioning variation study wherein you are showing H, right? H variation. What is this H parameter in that? I don't see that. There is an H1, there's an H2, but there is no H.
Is that? Right. So it was H1. What parameter we've taken over there is actually the height of the ground plane, and not the. So H2 marks what comes near the cut that we've made in the ground plane, and what was varied was the ground plane itself. So we keep that cut intact to allow the strip to not connect to the ground plane, and then we vary the height of the ground plane.
Okay, so there is one variation study where you're changing H1, and there is another study where you are changing E2, right? And
yes,
the response of that is complementary. Why is it so? It should ideally be same, right? Similar.
Sorry, the response of
E2 and
H1
and E2, they seem to be
okay.
If you go to the details.
Should I present my screen? Do you want to see it again?
Yep.
Okay.
I have a question. Hello.
Okay. So we're looking at H1 and E2, right?
E2. See, so as the behavior is complementary there, right? As you increase E2, you are eventually reducing H1, right?
No. E2 is on the front of the antenna.
That's fine.
H2 is on the back. So,
but when you increase E2, right, the ground plane comes closer to your patch, and then obviously the bandwidth will come down, right? And H2, it is different. It is different.
Right. However, I think over here it's seen more like as an independent thing. So even if you say use a smaller patch on the front, right? Let's say you take E2 much higher, right? Like let's say it goes up to C2 itself, but still the effect of that deformed ground plane, it still remains almost the same, right? Like which we can see over here. Over here, right? Like when you're looking at all of the changes, right? Like a step-by-step thing, we notice that the ground plane, once you bring it down, that's when you start getting this kind of a ultra, or rather a larger bandwidth, right? So what the ground plane crosses is that larger bandwidth, and like the variation of E2, at least it doesn't change that primary characteristic of it of the ground plane providing that larger bandwidth. Once you increase the ground plane, it just goes up.
That's it. So one more question, Balaji. The work is really good. Do you plan to measure this?
Yes, yeah, I realize it's a question that must be on your mind. What happened was we generally simulate and fabricate our antennas, but this time our fabrication facility was not available when I made this. So I believe it's still closed, and once it opens up, yes, we intend to fabricate it. And
because the effect of the connector on this antenna kind of like should be high. Agree, Gopi?
Right. So I actually mentioned it. So that's one thing that we observe is that usually when the ground plane, right, when its height is more than 1.5 mm, the effect of that SMA connector is not too much. Right, like that's something that we've noticed over time. Right, like
1.5 mm is very small, Balaji.
right, I get that. But we had this one antenna a while back, I think a year back, some other student made it, which was actually less than 1.5 mm, and that completely threw off the result when we are attaching the SMA. So generally we've noticed that when we keep it above 1.5, it doesn't change too much. But of course, it has to be fabricated. So.
Okay. Anyways, good work. I think it won't be complete until you do the complete measurement of this. And anyway, there's a question from Mahadevan sir. I think he's asking, the pattern presented are generally not acceptable. How do you propose to improve? I think he's mentioning about the
yeah, sure.
Sir, I think if you want to speak.
Actually, I also wanted to ask this question because he's using these parasitic patches. These are likely to cause degradation in the pattern. So how are you going to,
in what pattern?
Radiation pattern that you have shown. Yes.
Right. Like I think you can see it over here also. There is this deformation, right? Like because of this asymmetric element. So yes, that's definitely one concern.
See, the major parameter which you look for is always the radiation pattern. So at least for the frequencies of interest in the full wideband, we should make sure that the patterns are reasonably acceptable. So I think that is one major area where you have to work to make sure that the patterns are acceptable.
Right.
Also, how about the cross-polar levels of this antenna? Have you measured?
Cross-polar, I've not measured it over here. Usually it's very low for these types of antennas. Like the copolar is higher and then cross-polar is lower. Yeah, but like like I think we get a better idea once like the fabrication is done, right? That one we notice that it changes a little bit.
Because you are proposing it for Wi-Fi, WLAN bands and all, right? These deep nulls that you see at that 5.2 gigahertz and all are going to disturb it like pretty much. It's a very deep null there. So that and about the cross polar is correct. That needs to be improved because without that we may not use it. One thing impressive is that the size. Obviously, I think it has a very small size, 14 by 14.
Right. It was actually not this antenna directly that I had designed. So we had this quantum sensing application which required something below 15 cross 15. Right? Like that small. We had a small capsule where we had to keep this antenna. So it was originally intended for that, but later we realized that we can't use FR4 because we wanted to use it in like an ultra low vacuum chamber, right? Like so we couldn't use this particular design. But yes, that was kind of the application that we were intending for. So that's the reason for the size, right? Like the really small size.
Thank you.
Okay, another thing is that if it is intended for your UWB application, you should also think about doing the time domain analysis of these antenna.
Okay. All right.
So that is yeah. Okay. If there are any other questions from the audience. Okay. In that case, we'll move on to the next paper. And then thank you, Balaji, for presenting and answering our queries.
Right. Thank you so much. Also, like a special thank you to Professor Deepthi, if she's here. I'm not sure. You're really helpful, and yeah, thank you to all of the organizers. It was a very smooth experience. Thank you.
Okay. All the best. So, Deepu, you can proceed with the second paper of this session.
I think that is a compact triple band circularly polarized slot antenna for MIMO system by Devan and Anirban from NIT Goa. Over to you, Devan.
I hope you are doing good in this testing time. Before I begin with the presentation, I just wanted to ask you to all to be safe. Please take care. First of all, I would like to thank APSYM 2020 team for conducting virtual presentation because of COVID-19. So I'm Devan from NIT Goa and doing research on antenna domain. Here I'm going to present a compact triple band circularly polarized slot antenna for MIMO system.
We can't see you, Devan.
These are the contents of my presentation. Begin with the introduction.
Sir, the presentation is a virtual one, so I think the presenter is already with us. But
that's fine. I was just asking about the video. It's fine.
Okay.
Go ahead, Devan.
Of frequency spectrum and MIMO evolution, then propose antenna geometry for MIMO system, then parametric analysis has been done for compactness and CST simulation results. MIMO antenna analysis has been done, and in the last, conclusion and future scope of this design and references. The different part of the radio spectrum is allocated by the ITU for different radio transmission technology and applications. In this figure 1, you can see the various frequency bands like L bands stand for long wave and frequency range from 1 to 2 GHz. Similarly for S band, C band, X band, Q band, K, and so on. In this paper, we focus on C, Q, and lower K band applications. The evolution in the wireless communication system from CISO to MIMO is given in figure 2. CISO stands for single input, single output, means it has a single transmitter antenna and single receiver antenna. This kind of system is very simple. There is no diversity processing in this system, but it has a limited performance. Also, interference and fading will impact the system. CMOS stands for single input, multiple output. When the transmitter has a single antenna and the receiver has a multiple antennas, it has a receiver diversity. It is implemented. It is easy to implement it, but the receiver required processing, which affect the size and cost and the battery drain. MISO stands for multiple input, single output. It has a transmitter diversity. It has a multiple transmitter antenna at the transmitter and it has a single receiver to receive the data. Only processing is required at the transmitter end, which reduce the cost size at the receiver end. MIMO, where there is a more than one antenna at either of the end. Multiple input, multiple output. These require the processing but provide the additional data throughput capacity. The performance of the wireless communication system can be further improved by using the circularly polarized antenna. Also, the design antenna has a higher bandwidth, good isolation, and small in size. We have many options to design this kind of antennas like horn antenna, Yagi-Uda antenna, dipole antenna, loop antenna, log periodic antenna, microstrip patch antenna. Apart from all, the microstrip patch antenna has a unique feature like low weight, low cost, easy to fabricate, and easily we can achieve the required polarization. Microstrip patch antenna proposed geometry. The proposed single layer circularly polarized microstrip feed slot antenna geometry is shown in figure 3. The proposed structure is edged on Roger RT fighted dielectric substrate material, which is having the dielectric constant of 2.2. The geometry consists of a feed line with a single stub and modified slot in the ground plane. The identical element has been placed on opposite side by λh by 2 distance. It can be seen that one antenna is fed from plus y direction and another antenna is fed from negative minus y direction. Circular polarization is achieved because it produces orthogonal effects. The isolation can be improved by varying the G2, but the overall size become increased. The side is the dimension of the geometry is given. The overall dimension of the geometry is frequency because we have separated both the element by lambda h by 2 distance. As we increase the G2, the isolation has been improved at the lower band but the cost of the overall size. Now, in the proposed design, the stub has been aligned opposite side in the feed line with the same dimension. The S parameter of the antenna 2 is given in the figure 4b. It can be seen that the geometry gives notch at the lower band with the lower fractional bandwidth and the isolation has been improved. Further, in the proposed geometry, by incorporating stub on both the sides of the feed line with the same dimension is simulated, the S parameter is given in figure 4c. It can be seen that it has a 4 notch and the lower fractional bandwidth at the higher band. Also, the isolation has been improved over a resonating band, but the cost of the polarization and gain. VSWR. The VSWR of antenna 1, 2 and 3 are given in the figure 5a. It can be seen that it lies between 1 to 1.5 over the resonating bands. The S11 variation with the different M2 has been illustrated in figure 5b. It can be observed that as M2 increase, the notch frequency changes. The stub length varied from 1 mm to 5 mm. For particular 2.7 mm, the perfect resonance occurs. Similarly, the ground 2 slits with G1 variation and the effect on reflection coefficient is observed and given in figure 5c. It can be seen that G1 is vary from 0 mm to 2 mm. At particular 0.5 mm, we have achieved the sharp resonance. Surface current distribution. The surface current distribution of 2 port over the 3 resonating band is given in figure 6. When port 1 is excited, the port 2 is terminated with 50 ohm loading. The surface current distribution at lower band 6.40 GHz is given in figure 6a. It is clear that the sum of the current is distributed near to port 2 when port 1 is excited, which affect the isolation parameter. Similarly, when port 2 is excited, the sum of the current generated near to port 1. Similarly, for 12.50 GHz and 19.15 GHz, the current distribution over port 1 and port 2 is given in figure C, D, E, F respectively. At the higher frequency, the interference with the other port is less, which help to improve the isolation between two ports. 2D radiation pattern. Figure 7 shows 5 is equal to 0 and 5 is equal to 90 planes radiation patterns when port 1 and port 2 are excited at the simple frequencies of 6.40, 12.50 and 19.15 GHz respectively. It can be seen that the port 1 and port 2 radiation patterns are mirror image and quasi-omnidirectional. For all frequencies, the left magnitude is stronger than the right magnitude, which indicates the proposed antenna is left-hand circularly polarized. 3D directivity pattern. The 3D directivity pattern of the proposed antenna at the resonating frequencies are given in the figure 8. When port 1 and port 2 are excited together, the combined directivity pattern at 6.40, 12.50 and 19.15 gigahertz is given in figure 8. CP gain. The CP gain of the proposed antenna for 5 is equal to 0 and 5 is equal to 90 hertz are given in the figure 9a. It can be seen that the CP gain varies from 1.17 dBIC to 4.32 dBIC over the resonating band. The peak gain 4.32 dBIC is achieved at 12.50 GHz. The gain is smaller at the lower resonating frequencies due to the small size of the elements. Although variation of the peak gain is acceptable for the MIMO application. The action ratio versus frequency plot is given in figure 9b. Action ratio can be seen at the lower resonating band 6.40 GHz. The action ratio is 0.58 of the CP gain is acceptable to dBIC over the resonating bands. The peak gain 4.32 dBIC is achieved at 12.50 GHz. The gain is smaller at the lower resonating frequencies due to the small size of the elements. Although the variation of the CP gain is acceptable for the MIMO applications. The axial ratio versus frequency plot is given in figure 9b. The axial ratio, it can be seen that at the lower resonating band 6.40 GHz, the axial ratio bandwidth is 0.258 GHz. Furthermore, the axial ratio bandwidth at the lower Q band is improved due to the slots and two slits in the ground plane. The wide axial ratio bandwidth 2.86 GHz was achieved at 12.50 GHz. Similarly, at lower K band, the axial ratio bandwidth near to 0.731 GHz. The radiation efficiency of the proposed antenna is also given in figure 9b. It can be seen that the radiation efficiency varies from 55% to 90% over the resonating bands. ECC and DG performance. The envelope correlation coefficient and diversity gain are important performance parameters of the MIMO antenna. For better diversity performance, the ECC must be lower. The less than 0.5 ECC range is acceptable. The simulated ECC, which is plotted from 3D simulated radiation patterns, is given in figure 10. Furthermore, it can be calculated from the given equation. The DG of the MIMO antenna is calculated from the ECC. It can be seen that the ECC is higher at the 6.40 GHz, but it is less than 0.02 over the second and third resonating bands. Furthermore, the DG of the MIMO antenna is more than 9.5 dB at lower Q band and lower K band except at the first notch. Both the results reveals good diversity performance of the proposed MIMO antenna. We have used, for simulation we have used the CST Microwave Studio, and for equation we have used the MATLAB. Performance summary. The parametric results of the proposed antenna at resonating frequency 6.40, 12.50 and 19.15 GHz is given in table 2. It can be seen that it has a good return loss, and also we have achieved good fractional bandwidth over the resonating bands. Also maximum CP gain of 4.32 at 12.50 GHz we have achieved. Also we have achieved a maximum axial ratio bandwidth 21.19% at 12.50 GHz. Radiation efficiency varies from 55 to 84% over the resonating band. Also, we have achieved good MIMO characteristic parameters like ECC and DG over the resonating bands. Conclusions and future work. A compact two-port triple band circularly polarized slot antenna is proposed and gives good antenna performance over the resonating bands. We have obtained the fractional bandwidth of 6.58%, 7.32% and 14.20% at 6.40, 12.50 and 19.15 GHz respectively. Also, we have achieved a very good axial ratio bandwidth over the resonating bands. Furthermore, the triple band proposed antenna provides very good ECC and DG characteristics over the resonating bands. It can be used for C band, lower Q band as well as lower K bands MIMO applications. In future, we will design and fabricate the multi-port compact size antenna for MIMO systems. Furthermore, the triple band proposed antenna provides very good ECC and DG characteristics over the resonating bands. It can be used for C band, lower Q band as well as lower K bands MIMO applications. In future, we will design and fabricate the multi-port compact size antenna for MIMO systems. These all are the references. Thank you. If you have any query, you can mail me. My email address is written here. This work I have done under the supervision of my supervisor, Dr. Anirban Chatterjee. I hope you are doing good.
Krishna sir, I think we can move forward, right? If there are questions, I think we should move.
Yeah. Are there any questions from the audience part?
I have a question.
Yes, sir.
Regarding the frequency, see why your antenna is not working properly below the frequency that is at the S band and S band and C band.
Yeah, good morning, sir. Actually, yeah, am I audible?
Yes, sir, really.
Yes. Actually, sir, our antenna size is very small, actually 16 by 16 mm. So if we increase the size, it will resonate at lower band itself.
Oh.
So,
did you try for that?
Sorry?
Did you try for that?
No, actually, sir. But it will resonate, sir, definitely, because as we increase the size of the antenna, it will resonate at lower band.
Oh, okay.
So Devan, one question here. Your antenna, I think you started with 6.2 gigahertz, right?
Yeah, exactly, sir.
Obviously, there will be a harmonic at 12. So, I'm sure that is not a harmonic there, and you have intended that there will be a resonance as 12 gigahertz.
Yeah, sir. Actually, it's not a harmonic. That resonance occurs because of the slots and that stub that I have shown in the figure.
Again, another question. I think we have to evaluate that. We have to kind of like provide some proof that it is not a harmonic. The second question is that you told that you want to achieve a compact size, right? At 16 by 16 is not a compact size, and you are not separating the elements, means the ports. Now you've taken it as a factor of your highest frequency, which shouldn't be the case, right?
Yes, sir. But in this, it is not a single element. It is a two element actually. So for two element, it is 16 by 16. As I have literature surveys, it is a kind of compact size. As we increase the number of elements, or if we increase the separation between two elements, the size become increased.
Devan, but your prime frequency is 6.2, and we
exactly.
Very good isolation for MIMO, right? If MIMO doesn't have good isolation between the ports, then what is the use? What throughput are you going to get by using the system?
Yes, sir. Here around 6 point lower band only I am facing the problem of isolation, but at the upper band I'm getting the around 20 dB or 50 more than 15 dB isolation.
And also, when we see the gain plot, the gain is better at a lower frequency. Below 6.4 gigahertz, the gain is better. At 6.4 gigahertz, you have shown that it is only 1.17 dBi, I think. Any comment on that?
Actually, sir, at particular 6.40 gigahertz, I have achieved the 1.17 dBi gain. Might be, sir, current interruption at the particular lower frequency, less current interruption at the lower frequency. So might be achieving the good gain.
Okay, so the out of band performance of the antenna is better than the in band performance. That's what I feel. Okay, then can you explain on how does the stub aid in giving you the proper isolation that you require?
Yeah, sir.
Any physical explanation on how?
Actually, the stub is helpful for circular polarization also, and plus for resonating also. It's shown in figure 4. As we changing the stub direction, instead of putting in the same direction, we will putting in opposite direction, that resonating occur at the single band only. And if we'll put stub in the both the direction.
Okay, that you have already explained in the video. Yes. I was asking whether do you have any physical any explanation onto that kind of performance that is given by the steps?
Sorry. actually this single element now this is only for two port network. Now we are working on more than 8x8 or some 16x16 combination, and then later we are planning for fabrication also.
Okay, fine.
Devan, I think I agree with you. The size is compact. There may be advantages, but if you don't get good isolation, then there is no point in kind of like making it compact, right? You lose all the attraction there.
Yes.
And also, you don't have very good cross polarization, I guess. So that also needs to be worked upon.
Yes. Okay.
See, in MIMOs, when we go for arraying, I think this will further deteriorate, specifically the this one, the axle ratios. So the CP needs to be definitely improved, specifically when you are going for an array environment. So I think it requires some more development effort to make it better, specifically for MIMO cases. Thank you.
Okay.
But very good work. Very good work. It's a very important work for this particular area, in this area. But it requires still a lot of development to be done to come to some stage.
Agree, sir.
Thank you.
I think even though if you don't make it dual or triple band also, it's fine. But if you get very good performance in one band.
Yes. That is most important first.
Yeah.
Because we are not able to get the exact frequency where it's really working well. So in trying to get such a large bandwidth, you are not able to get a good performance for a specific frequency of interest. That's what you could see from the.
Okay, so with that, can we wind up this presentation? Okay, so Devan, thank you very much for and all the very best for your future.
Thank you, sir.
So the next paper is Improved Gain Vivaldi Antenna Design for True Wall Radar Applications by Anila Kyriakos, Teresa Angel George, and animals.
Good afternoon. Myself, Anila Kyriakos, and I'll be presenting our team's work on improved high-gain Vivaldi antenna design for through-wall radar applications. These are how the contents of my presentation has been organized. We'll start with an introduction. We'll see the contributions of our work. And then we start off with the basic Vivaldi antenna. And Vivaldi antenna, which is an inherently a UWB antenna. So what are the modifications that we have proposed to make it more suitable for through-wall radar applications? We look at the simulation results for both the basic Vivaldi antenna and the improved one after the modifications. Then we have fabricated both the antennas, and then we'll see how the experiment, the measured results corroborates the simulation results. We have the last concluding slide and then the references. Introduction. A through-wall radar is basically an indoor radar which is used to detect or image a target which can be moving or stationary on other side of an obstruction or a wall. So for this application, for a long time, it's UWB signals that are being used, mainly due to two reasons. Basically because of its penetration capability and then its fine time resolution. So the UWB antenna design has been a great interesting research area, especially for the through-wall radar application. So these are the desired characteristics of a UWB antenna for through-wall radar applications. It should have high and stable gain in the desired band, good impedance matching, directional radiation pattern, which implies high front-to-back ratio, and then compact size for portability, because through-wall radar, we expect the system to be portable. So we require it to be compact, as well as if it's low cost, then it's an added advantage. The contributions of our work include, we have actually proposed, simulated, and fabricated low-cost, compact, high-gain UWB antenna, which is desirable for through-wall radar applications. So to the basic Vivaldi antenna, which is inherently wideband, we add corrugations and metallic grating. So corrugations are added along the length of the antenna, and grating elements are inserted on the opening end of the exponential slot. Now these structures we'll be seeing in detail very shortly. The operating frequency range has improved. Okay, so it has become great. The bandwidth has increased, but the highlight is that most of the existing antenna designs, they are wideband, but the thing is that is towards the higher frequencies. But through-wall radar applications, there is a constraint on the frequencies that can be used, which we'll be seeing very shortly. So there's a requirement that it should have a stable radiation pattern even towards the lower frequencies, which is achieved using our design. We have stable radiation pattern even towards the lower frequency. Gain that is greater than 6 dBi is required, which is derived using the link budget equation. That also we have just will be seeing just in one or two slides. And in our the one which we have fabricated, that we have proposed, it has got a gain of 8.2 dBi at 4.5 gigahertz. Now, the fabricated antenna is tested and the measurement data is at par with the simulation results that we have obtained from CST Microwave Studio. So, these two figures, it just tells you why 2 to 8 gigahertz is ideal for through-wall radar applications. Now, the first factor is resolution. We know that higher the frequency of the transmitted signal, greater is the resolution capability. That is, capability to distinguish between two targets. But the main point here is we cannot just increase the frequency because the wall attenuation is directly proportional to frequency. As frequency increases, the attenuation offered by the walls also increases. So I can't just keep on increasing the frequency for the resolution concept. It has to be a trade-off between these two. So these are the results or experimental results that is obtained, that has been obtained from the book Moines G. Emin, the through-wall radar imaging. Okay? And it is seen that there's an exponential increase in the attenuation with frequency. And the one that has been highlighted in yellow, it shows that for a concrete block, okay, of thickness about 19.45 centimeter, which is maybe a little more thicker than the walls that we have. Okay, it offers about 13.62 dB at 5 gigahertz. So this is a value that we have considered for the calculations for the link budget equation. Now, regarding the antenna gain, the requirement has been calculated using the link budget equation. So here we have shown the equation, and these are the values that has been assumed. Okay, and from the given equation, we can find that the required gain of the receiver antenna should be greater than 6 dBi. Okay, so this is how we get the required frequency of operation and the required frequency band for TWR operation, and what is the minimum gain that is required. So since we have the requirements, let's move on to the structure. So the basic Vivaldi antenna that we have used, the basic design has been shown. It's simulated in CST. Okay, so basically it has got 3 layers. We have a substrate. The antenna is, in our case, we've chosen FR4 substrate, 0.8 millimeter thickness, and the permittivity of 4.3. Now you have the ground plane. So it consists of a uniform rectangular slot that is connected to an exponentially tapered slot, as you can see in the. Okay, so you have the exponentially tapered slot here, and to the end, to one end of the exponential tapered slot, you have a circular cavity is attached. The feeding technique, you have the radial stub has been used. Okay, so the cavity stub model is used for designing the wideband Vivaldi antenna. So basically, it's the radius of the circular cavity, okay, and the angle at which the flaring happens. Okay, so these are factors which determines the impedance matching of the antenna that you've designed. So you can see that the microstrip and the slot line, they cross at right angles to each other and they form a junction here. Now, these are the basic equations for the basic Vivaldi antenna. So Yfx, it's the exponential tapering rate. Okay, it is given by the following equation, where C is a constant and it is given by S by 2, where S is the slot width that we have chosen, and R is the opening rate, the exponential opening rate, and it is given by 1 by L on W by S, where L is the length of the antenna, W is the antenna width, and S is the slot width. So for the simulation of the antenna, we have chosen the following parameters. It has been consolidated into this particular table. The simulation results for the basic Vivaldi antenna is shown. Shown as the S11 and VSWR variation with frequency. It is seen that the antenna has an operating bandwidth of 8.8 gigahertz, and that is because you can see that the S11 is below minus 10 dB from 2.5 to 11.3. Even though there is a small, hike from the minus 10 dB at 2 points, it is satisfactory between 2.5 to 11.3. And the VSWR also, it lies below 2 dB, sorry, 2 for the particular bandwidth. So the gain obtained is about 6.6 dBi, which satisfies the gain requirement. So what we are trying to do is, if we can improve the gain, okay, as well as extend the operating bandwidth more into the lower frequency region, that is what we are trying to do. So here, yes, so these are the simulation results. So the fabricated antenna is shown, both the top view and the bottom view, and this is tested using a VNA, and the S11 result that we have obtained, it is found that it's less than minus 10. So this is the actual one, the measured result, 3.4 to 10.6. So that makes a bandwidth of 7.2 gigahertz. So these are the modifications that we have proposed. We have used both corrugations as well as metallic gratings to the basic Vivaldi structure. Both of them results in high gain, as well as it tries to increase the bandwidth towards a lower frequency range. So here you can see that the corrugations are added along. Okay, the corrugations are added along the length of the antenna, and in our structure we've used 8 corrugations on both sides of the antenna. Width of each corrugation has been chosen to be 5 millimeter, and the gap is 1.5 between 2 corrugations. Okay? And it is seen that the corrugations reduce by 1.5 millimeter as it moves on. Okay? Then we have seen that metallic grating elements are introduced at the opening end of the exponential slot. Okay? In our optimized result, we have chosen 5 metallic gratings, and they are of length 7 millimeter and a spacing of 2 millimeter. So this is how the proposed antenna looks like. This was simulated in CST, and the simulation results are shown. The operating bandwidth is found to increase from 1.7 to 11.4 gigahertz. It indicated very good matching because it was way below minus 10 dB for the whole operating range. And the VSWR was found to be less than 2 for the same operating frequency. It is seen that the gain also improved. Okay, you can see a maximum gain of 8.2 dBi at 4.5 gigahertz, and you can see that the gain is greater than 6 dBi for a large bandwidth. Okay, you can see that it is greater than 6 from about 2.2 to into 5.5, we can see that its value is greater than 6 dBi. Now these are the experimental results. So the antenna was fabricated as proposed, okay, and it was the results were measured using a VNA, and it was seen that the S11 variation with respect to frequency was also plotted. It was seen that it's less than minus 10 dB from 1.9 to 11.26 gigahertz. So that was a, the operating bandwidth is much higher, and that too towards a lower frequency range compared to the original Vivaldi antenna that we had, fabricated. So this is a conclusion. We have presented an improved design of high gain UWB Vivaldi antenna. The whole size of the antenna was about 12.8 centimeter in length and 7 centimeter in width. Okay, and making it compact because Vivaldi antenna is fabricated on a PCB, so it's a planar one. So it has a it's compact and it's low cost because of the substrate that we've chosen. Now, the proposed design, it adds corrugations and grating elements to the basic structure. When compared with the existing design, it has got two advantages. The first one, its gain is much higher when compared to the existing designs that is there presently used for TWR applications. And it was seen that the operating bandwidth extended more into the lower frequency range, which was suitable for through-wall radar applications. Okay, so the experimental results were found to match with the simulation results. These are the references that we have chosen. Thank you. So that is the end of my presentation. Thank you so much.
I hope the presenter is there to answer the questions.
Yes, sir.
Okay. Are there any questions from the audience?
So one question is, so while you have calculated the EARP, right, the link budget, have you taken the thickness of the wall into account, the spacing?
Yes, sir. There's a parameter called LW, which is actually the loss due to wall. It's LW square because the signal is passing through the wall twice because it has to strike the start and LW square in the denominator, it shows the loss due to the wall.
Okay.
So that is why we have taken it as 15 dB because from the result, the initial one that I've taken from that book, it was shown that if the thickness of the wall is 19.45 centimeters, close to 13. So we have actually taken a loss of 15 dB for the calculation on the higher side.
In the paper, right, you have shown gain until 6 gigahertz. Have you measured gain up till 12, or is it just that until 6?
Sorry, sir, I did not get your question.
No, you have shown the gain, right, in your paper.
Yes.
That is only until 6 gigahertz. So have you measured it until 12 gigahertz, or is it at 6 only?
No, it's like till 11 point. The gain was calculated for a large range of frequencies, and till 11.3, the maximum gain was obtained as 8.2 dBi. And then, sir, there was a graph. Can I show the PPT?
Sure.
Okay, this. Okay. This one we had taken it only till 6.
That was my question. And you see the gain is dropping at 6.
Yes. So after that, it's
comments is your directors. Is it improving gain? The other question is the pattern stable across the frequencies?
Yeah, we did not take it. We took it only till 6.
Because unless the work is anyways, you started with a wall penetrating radar and you are now going to a wideband antenna design. The work is important in the significance of millimeter waves, wherein we are trying to communicate the signals, 28 gigahertz and 60 gigahertz signals through the wall. So any system will be kind of like highly appreciated. So I think you have to be serious about that. bandwidth and all, the gain, the pattern response and all. So this is tremendously useful.
Yes, actually the gain, this will not still be satisfactory if we go for the practical cases, which I'll have to obviously go for an array. But the thing is, we are trying to set up a small system here, which we started off with the antenna part. Right now we are working on the signal processing part of it, and then we thought we'll start it off. Okay, so we thought of actually time domain analysis was not done of this particular antenna. We expect a lot to be done with this. This was just a initial results that we have gained. Shally sir, the frequencies beyond 60 GHz is of importance, which I did not keep it here. I'm sorry.
You may have to think of array designs and all. Again, yes. Have you taken the concrete thickness into account, the complete concrete thickness? Was it just done for concrete or some other wall?
The concrete wall.
EARP calculation.
Concrete wall.
What is the performance through glass? Any idea? Have you done any studies on that? Windows.
No, it's actually, we've just decided we have to do the whole experiment part. This was just the initial, the antenna design part of it. We are looking on the signal processing part right now. Only when it's done, we are going to experiment this officially. So,
okay. Madam, could you, Madam, could you just explain us what was the motivation behind using the corrugations and grating lines?
So most of the existing ones that we had, we actually thought of starting with the horn antenna. Then we thought, okay, why don't we actually design one? Okay, so
no, I was asking.
Yes, the corrugations.
What is the physics behind that?
Sir, actually, when we introduced corrugations, they as I have understood, it actually it restricts the or it improves the current density. Okay, so what it restricts to the inner region of the antenna, making it more radiating, or the gain improves that way. So it's like virtual antenna array being introduced into a simple antenna, because you are inserting corrugations into it. I mean, it's like not the correct one, but I was
even I have to check that.
Corrugations, we are not sure. I think.
No. I just wanted to know how you have arrived into that design. That's why I asked.
Corrugations are something that is already existing in a paper, sir. Corrugations are there, okay, but it's like what we tried to do was, most of the papers, or till what we have seen, the bandwidth was the problem that we had been seeing. Most of them, even though the papers with corrugation, they started off, or the good matching properties were found from 8 GHz on to the higher band. Okay, but since through wall radar, if I go for such high frequencies, obviously the wall is going to attenuate that. So we had to, bring it to the band that we are focusing on. So that is where the placing the corrugations, and then the gratings was not that it did not affect our the impedance matching much, to be very frank. It's actually the gain that it contributes, the gratings part. But the corrugations is the one that actually brought the characteristics to the lower frequencies. It also contributed to the gain, but the corrugations, because we studied the analysis separately, and it was corrugations that actually brought the response to the lower frequencies, which could good matching problem.
Also, are there any improvement in the change in phase center of the antenna while you introduce the corrugations? Because these Vivaldi antennas are likely to have variation in their phase center, even though they have very wide bandwidth.
Right. I haven't checked through it.
Okay, thank you. If there are no more questions.
There is a question in the
box. Yes. How were the dimensions of corrugations and metallic gratings calculated?
Okay.
That's a question from Muhammad Nihal.
Okay. So here, in corrugations, it's like we had an equation which not maybe we can share, and it's basically okay. There are two. Okay. Sir, I don't know the equations by heart. I've not kept it here. Maybe
it's all right.
Okay, Sherko, there are specific equations for the metallic gratings. To be very frank, we just, it's like the number of metallic gratings, yeah, we actually varied such that we looked at the performance and then we did it. Okay, it was not, based on a particular formula or something. But corrugations, yes, there's a formula which I'll surely share it to you. I can mail it to you, the actual design process, which
That's
I've
all
not
right.
kept it right now.
Okay, sure. Then. Okay. So can we move to the next presentation? Thank you. If there are no other questions. Okay, thank you. Thank you for presenting the paper to.
Thank you so much, sir. Thank you for the opportunity. Thank you.
Okay, Deepu, you can.
Continue, sir. It doesn't matter.
The next paper is rectangular meandered wire inverted F antenna for UHF applications by S. Femina Begum, Thomas Chako, and KK Mukundan.
Good morning. Myself, Femina Begum, working in RF Systems Group of Avionics Entity, Vikram Sarabhai Space Center, Thiruvananthapuram. I am here to present the paper Rectangular Meandered Wire Inverted F Antenna for UHF Applications. The co-authors of this paper are Mr. Thomas Chako and Mr. KK Mukundan. The presentation is outlined as Introduction, Design of the Antenna Element, Results and Discussion, and Conclusion. Introduction. The lower range of UHF frequency band is usually used by different communication systems like amateur radio, private mobile radio, radio astronomy systems, industrial telemetry, etc. The 406 MHz band is especially used for some specialized applications like radio sonde system for meteorological application and search and rescue beacon. The search and rescue beacons are regulated by international consortium which is called COSPAS-SARSAT. They have very stringent specification on the antennas as well as these devices. All these compact handheld communication devices requires confined or low profile antennas. At the same time, they have to meet all these requirement specifications. So, for any low profile antenna at UHF band, inverted F antenna is a best choice. But the common planar inverted F antennas, which is usually fabricated in microstrip configuration, they have low gain, reduced bandwidth, and distorted radiation pattern. But the 3D inverted F antennas can provide a better performance compared to these planar inverted F antennas. Here, this paper presents a rectangular meandered wire inverted F antenna for UHF communication devices at 406 MHz frequency. This is a 3D antenna. Design of antenna element. The antenna has a rectangular shape and its overall dimensions is 70 by 36 by 20 mm. This antenna is mounted on a circular ground plane of radius 50 mm. This antenna is fabricated using an enameled copper wire with a circular cross section and with a diameter of 1 mm and an SMA flange connector. Here, the feed pin of the flange connector is extended as the feed element of the antenna and the shorting leg of the antenna is connected to the flange of the connector. Here, the last element of the rectangular antenna is meandered or folded downwards. This gives the freedom of adjusting the length of the antenna to tune the frequency. If it was a coplanar rectangular design, then the last element will be near to the shorting pin. Then the gap between the shorting pin as well as the last element of the antenna will affect the impedance matching. So by meandering downwards, We can adjust the length freely without affecting the impedance matching. The connectorized configuration of the antenna allows the antenna to be separate from the ground plane, and this makes the fabrication of the antenna easy as well as testing also. So the ground plane, the circular ground plane can be a part of the communication device and the antenna can be separate. This will be very useful in production point of view. Results and discussion. Design, simulation and analysis of the antenna is carried out in ANSYS HFSS software. Here, the impedance matching of the antenna is achieved by adjusting the gap between feed pin and shorting length. The variation of the S parameter with this gap is shown in the figure. The antenna provides a maximum gain of 2.5 dB with the monopole type radiation pattern. The 10 dB impedance bandwidth is 1 MHz. Here, the simulated and measured S parameters are shown, as well as the simulated 3D radiation pattern and 2D radiation patterns are shown. The 2D radiation patterns are shown at XY, YZ and XZ planes. Conclusion. The proposed rectangular meandered wire inverted F antenna provides a maximum gain of 2.5 dB and a return loss of 12 dB at 406 MHz frequency. The proposed design presents a cost-effective, low-profile antenna for UHF applications. The geometry and miniature configuration of the antenna makes it a suitable candidate for UHF communication devices. Thank you.
Okay, if there are any questions regarding the presentation.
Have you measured the gain of the antenna? Actual measurement?
Hello, I have made Femina ma'am speaker, so you can unmute.
Hello, we have fabricated the antenna, but we couldn't measure the gain because of the pandemic and all. Anyway, we have measured the S parameters.
But Femia ma'am, the question here is right. What is the difference compared to the existing PIF antennas that we currently have? What any highlight that you want to suggest?
Yeah, the first thing is the compact design itself, because we usually this inverted F antennas we are using in mobile phone and all, they are in the planar configuration. The thing is that the specific application like radio sonde as well as beacon, there requires a uniform pattern. Uniform means there is the gain should be within certain limits over the specific range of elevation angle. If we are fabricating in a planar antenna, we cannot meet that gain specification as well as this bandwidth specification. So anyway, we have to go for a 3D antenna. And 3D antenna, other than inverted F, the monopole is the other option. But when we are going for a monopole antenna, there will be projecting elements. Our aim is to design an antenna which can be confined to the package or the dome of the device. That's why we have gone for this design, and in literature I could find only a patent with similar design.
Again, we have not used a large ground here, right? In any of the device that you're going to put this on, you'll have a larger ground. So
yeah, a 10 centimeter ground plane, we have done the measurement for this analysis. If our device is having a lower ground plane, we can fine tune it.
No, this particular design that you've shown here, right, doesn't have a ground other than the short in the coax, right? So will it give that much gain? That's a question.
The gain is measured with the 10. I have in the presentation I have specified the ground plane usually is of 50 millimeter radius. So with that only we have done all the simulation as well as the measurement. I have not shown that in the image.
It is not mentioned in the paper as well. So I think there may be some kind
Yeah, it is mentioned in the paper. It is mentioned in the paper as well as in the presentation. In the design, I think the second point is that 50 millimeter radius is mentioned. It is not in the photograph, that's all. Ground is mentioned.
Okay, that's all I had. Thank you. You're on mute.
Thank you.
Yeah, Gobi sir.
Yeah, I have no more questions. If there are no other questions from the audience part, we can move on to the next paper.
I think sir had a question.
What is the simulated gain and bandwidth, Mahadevan sir?
So the maximum gain is 2.5 dB and bandwidth is 1 megahertz at 10 dB.
But the bandwidth is too narrow. No, it can be definitely improved.
So if we can increase the wire length, we can increase the bandwidth also. But we have tried with this configuration as this is suitable for our requirement. That's why we didn't try for a large bandwidth. Of course, we can improve the bandwidth.
Yeah, because otherwise it becomes an one-off antenna specifically meant only for that 406 megahertz. So we want to make it slightly general. The bandwidth has to be improved.
True. Correct, sir.
Yeah. Okay, good.
Thank you, sir.
There's another question from Praveen, sir, I think. Is suggesting the same thing. The antenna must be optimized with the ground plane included. I think it's answered. It's fine.
Okay, sir.
Yeah.
Because it may go to different platforms. So definitely you must have a good simulation with a larger platform.
Okay, sir. I have done with the 10 centimeter radius ground plane, circular ground plane. We can optimize the antenna with different shape and size also.
Okay. Okay, madam. Thank you very much for presenting and answering the queries.
Thank you.
Well, the next paper is multi-port driven frequency scanning antenna system for high PAPR signals. And this is authored by Gopika R and Chinmay Saha.
A very warm good evening to all. This is Gopika R, research scholar from Indian Institute of Space Science and Technology, working under the guidance of Dr. Chinmay Saha. It's indeed a great pleasure to give a presentation before such a vibrant technical community. I thank the APSYM organizers for this opportunity during the pandemic. I'm here to present a multi-port driven frequency scanning antenna system for high PAPR signals. So to begin with, the term PAPR or peak to average power ratio is quite common among the communication engineers. A signal having high PAPR can offer higher bitrate and spectral efficiency, and both these quantities are matters of concern in an efficient wireless system. So, extensive research has been carried out on such waveforms and signals, and it is found that the multi-carrier or multi-tone signals have better PAPR than the single-tone. So, OFDM, which is a very popular choice of communication signal, is also a multi-tone. So, in figure 1a, the time domain representations of single-tone and OFDM signals are given. So, as indicated, the ratio between peak and average power values of OFDM is way more than that of a single-tone. Now, we have the high PAPR signal or multi-tone as our transmission signal. What we need next is an efficient system which is capable of transmitting this multi-tone to the receiver. For every transmitter, the power amplifier is the most critical subsystem. The concern over power amplifier efficiency made the division of traditional structures to class A, class B, class C, etc. But all these classes offer the maximum efficiency only at the peak power value. So for high PAPR signal, the maximum efficiency will be attained only for few points of instances. So we have some architectures specifically for high PAPR signal amplification in the literature. Most popular among them are Doherty and outphasing. Even combinations and modifications of these are also reported. In figure 1b, the blue line indicates class AB, black shows Doherty, and the green represents outphasing. So it is evident from the figure that Doherty and outphasing can offer wider range of efficient power levels than the normal power amplifier configuration. So both this Doherty and outphasing configurations use two power amplifiers for the operation. These architectures are given in figure 2a. The input signal is split into two and are given as input towards the two separate power amplifiers in both of these architectures. These signal outputs are then combined to get amplified high PAPR signals. This basic structure of Doherty and outphasing methods demands a combiner that adds up the high PAPR signals at the output efficiently. That brings us to the generic combiner types. So, in general, any two-put combiner can be divided to two, series and parallel combiners. The key metrics for identification of a series combiner is admittance, and that of a parallel combiner is impedance. The properties of both are shown here. During the fabrication at higher frequencies, parallel combiners are easier to fabricate and hence more preferable also. In figure B and C of 2, it shows that the combiners of both Doherty and outphasing can have a parallel combiner inside. So additional transmission lines with parallel combiner can give the combiner of desired amplifier topology for high PAPR signal transmission. Or in other words, parallel combiners are inevitable elements for multitone amplification. So the parallel combiners, which is coming at the output of multitone signal amplification, should be followed by antenna in the transmitter structure. But for a communication system, the antenna mostly be arranged in array fashion, which means the power divider is also involved. But more the passive networks are involved between the amplification stage and the antenna, more will be the loss, and that will degrade the system efficiency also. This may be overcome by integrating the antenna structure and combiner. Since the antenna is taking up the function of combiner and radiation simultaneously, the structure may be called a radiator. The radiator design is possible by inserting multiple ports to the structure such that the desired function is also taken care along with the antenna function. The multi-port driven radiators can be employed to integrate the impedance matching networks also. The complex current patterns that are difficult to be formed in single port designs can be achieved very easily in this method. So, in this work, a multi-port driven radiator that can work as both combiner antenna and antenna is proposed. The top view of the proposed structure is shown in figure 4. So as indicated, the structure has three ports, F1, F2 and F3, and these are arranged symmetrically around the ring. So that makes the angle of separation between the ports as 120 degree. Out of these, F3 is terminated with match load and F1 and F2 are the input feeds. The ring structure has a central radius of R and width W. The radius R is chosen such that the circumference is 3 times the wavelength of operational frequency. Here we have chosen 24 GHz as the operational frequency since this is included in the ISM band. The width W is optimized to obtain the best radiation properties. The dimensions of the structure for 24 GHz are shown in the table here. The structure shows frequency scanning nature due to the max load termination, and the radiation properties are improved due to the shorting wires placed along the mean circumference of the ring. The substrate chosen here is 10 mil RT Duroid 5880 due to the low loss tangent. So, in one of the previous slides, we have already shown that the parallel combiner is identified by the impedance matrix with all the element values equal and should be same as that of the input impedance of single port fed antenna. So here we show that the proposed structure also satisfies this condition. Since the structure is symmetrical and port conditions are identical, computation of Z11 and Z21 will suffice. For calculating the same, the port 2, F2 has to be open. Assuming this condition as depicted in figure 5, Z11 will be equal to V1 by I1. Now this value will be equal to input impedance Zin of single port antenna, because for a structure with only one port, let's say F1 is present, becomes equivalent to the two-port structure with other port F2 open. So this makes Z11 equals Zin. Similarly, Z21 equals V2 by I1 with port F2 open. We have designed the structure such that the loop circumference is integer multiple of 3 lambda, which makes the ports F1 and F2 separated by a distance of lambda. This ensures that V1 is equal to V2 and thus Z21 is equal to Z11, which is same as that of the Zin. Thus all the elements of the impedance matrix become equal and thus the structure acts as a parallel combiner inherently. Now the structure was simulated in a 3D EM solver to get the results. Since the structure was claimed to act as a parallel combiner along with the antenna function, the impedance parameters Z11, Z21 and Zin, the input impedance of single port fed antenna, are plotted in figure 6. Both the real and imaginary parts are plotted for a frequency range of 20 to 30 GHz by blue and orange lines respectively. So as the plot indicates, the values match at 25.6 GHz instead of 24 GHz. The magnitude of E field plots for both these frequencies, 24 and 25.6 GHz, are shown here. The animated field variations show that the fields at 25.6 GHz are symmetrical compared to that of the fields at 24 GHz. This matching frequency can be tuned by optimizing the W. So in previous slide, the combiner action was presented. So in here, we discussed the antenna nature. Due to the max load at port 3, the antenna shows a traveling wave nature, which gives rise to a beam scanning nature with change in frequency in the direction towards port F3. Here, the direction is y-axis. Due to this nature, the radiation pattern at plane phi equals 90 shows an angular scanning from -5 degree to 26 degree for a range of 22 to 25.8 GHz. The excitations are phase differed by 120 degree to avoid null formation in the pattern due to structural symmetry. The normalized radiation patterns are shown in figure 8a. The gain and radiation efficiency are shown in figure 8b. Throughout the scanning range mentioned above, 22 to 25.8 GHz, the structure gives gain above 7 dBi and efficiency above 75%. Thus, a scan range of 31 degree is obtained with a 3.8 GHz bandwidth. So, coming to the summary and future prospect of this work, the proposed structure integrates combiner and antenna action to a single structure that makes the structure compact, low profile, and efficient. Due to the frequency scanning nature, the structure does not need a complex circuitry or control signals to do the beam scanning for target localization. This makes the system low cost also, low profile applications. The structure may be thus further improved by employing non-reciprocity, and thus instead of matched termination at port 3, the receiver may be connected directly. This possibility will be explored in the future for various wireless applications. The references used for the work and the presentation are given here. And thank you for the patient hearing, and I am open to questions and suggestions. Thank you.
Good work. Anyways, I have a question.
Yes, sir.
On figure number 4, you have said that there is a normalized radiation pattern, right? If I don't normalize it, what is the variation of gain across various steering angles across frequency?
Yes, sir. That is the plot which is given on the same slide. Can I show the screen, sir? Give me a second, sir. I'll share the screen. Sir, hope my screen is visible.
Yes.
Sir, in this screen, the figure number B. So it shows that the variation of the gain, which is given on the left side of the y-axis. Left side y-axis is for the gain. The blue plot is for the gain. So if you see here, the variation is all between 2 dB variation is coming in this frequency range from 8 to nearly maximum of 9.5 is coming at that frequency range.
So if we include that data in figure number 8, in the first figure, right? Then does it
Yes, sir.
pattern, or is it kind of like similar?
It is kind of similar, sir, but then the problem is we will not be able to see this both sides clearly. So for that reason, I have plotted it as a normalized and then gain versus frequency as separate plots.
Hope there are no distortions in the pattern, right? With frequency.
No, sir. There are distortions in the other side. Like I have shown you only the phi equals 90 degree. The phi equals 0 degree. That plane is having some distortions. We are trying to make a constant out of that pattern also. But yes, there are distortions in the other side. Other plane, the orthogonal plane.
But I think that will be very informative, Gopika, if you can include that slide as well, where you show the variation in pattern with respect.
Sure, sir.
Thank you. Yes.
Thank you, sir.
Okay. Are there any other questions from the audience? Okay, I think there are no more questions.
Thank you, sir.
And yeah, it's already 12:30, and it's time for us to wind up the session. And we thank all the participants.
Sorry to interrupt. There's another question from Praveen.
Yeah.
So he's asking, keeping the frequency constant, can you achieve beam scanning through phase change too?
Actually, we are using it for a power amplifier application. So we cannot actually change the phase because that angle of 60 and minus 60 degree has been taken from the amplifier consideration. So we have no liberty to change the phase. We have the liberty to change only the frequency.
Thank you.
Okay. Thank you, participants, for your knowledge shared with us, and thank you, chairs, for sparing your valuable time with us. So by this, we come to the end of the forenoon session. Let's resume this event at 2 p.m. Thank you.
It's already 12:30, and we end up the session. Thank you very much, thank you very much, dear participants, for
Good evening, one and all. My name is Prem Sai Regalla. I am going to present the accepted paper which is titled as Application of a Cylindrical Dielectric Resonator as an angular displacement sensor. The authors are Prem Sai Regalla and A.
Welcome back, everyone. Now, we head on to the first alumni talk. It's a great opportunity for us to listen to the words by knowledgeable speaker Robin Augustine, who is also an alumni of DOE QuizAt. The title of the talk is Fat Intra-Body Communication Technology, Enabling High Data Rate for Human Implant and Wearable Applications. The distinguished chair for this session is Sujit R. from Bharatiya University. I would like to hand over the platform to the chair. We welcome you, sir.
Thank you.
Yeah, very good afternoon to all of you. So, good morning to Robin. Am I audible?
Good morning, Sujit. Can you hear me, Sujit?
Hello?
Can you hear me?
Yeah, it's a little bit mild, but maybe the volume is a little bit less.
Is that better? Can you hear me now?
Yeah, it's a little bit better. Okay, so I am Sujit Raman, UGC Assistant Professor at Bharatiya University. So I am extremely happy to chair today's session, which is an invited talk by Professor Robin Augustine on the topic Fat Intra-Body Communication. So Professor Robin Augustine is an associate professor and head of the Microwaves in Medical Engineering Group, Department of Electrical Engineering, Uppsala University, Sweden. And Professor Robin received his master's degree in electronics from Cochin University of Science and Technology, India in 2005, and doctoral degree in electronics and optics system from University of Paris, France in 2009. He joined Uppsala University in 2011 as a senior researcher. He's a co-author or author of more than 160 publications, including journals and conferences. And there are 3 patents for his credit also. He's a regular session chair and convened session organizer on UCAP. And he's the editorial board member of IET Electronic Letters. And moreover, he's a PA of various European and international collaborative projects. And he's the recipient of Attractive Innovation Project 2020 Award from Uppsala University Innovation. He's the founder, chairman, and CTO of the Swedish medtech company Provington AB. And there are a lot of projects listed here. So I think it's better we can move on to his presentation rather than reading everything because it's a lot of lists there. So I'm very happy to introduce Professor Robin Augustine because you're a good friend of mine and it's a great opportunity for me to introduce you here. And we all are eagerly waiting to listen from you, Professor Robin. Please carry on.
Yeah, thank you. Thank you very much.
Yeah.
It has been a pleasure for me to have associated with you, Sujit, to be opening with the very first sentence. Thank you very much for this invitation. I really.
Professor Robin, the sound is a little bit mild. If you can just increase the volume.
Yeah, is it better? It seems like I have to hold the mic all the time now.
Okay, no problem.
But that's no problem. I can do it. So yeah, as you duly mentioned, Sujit, Cochin University is my alma mater. So I owe my sincere gratitude to the university, so that university has made me, especially the DOE, Department of Electronic Science. So thank you for that. And then of course let's go into the talk. Okay, as Sujit introduced me, I'm Robin Augustine. Now I'm presently in Uppsala University. I'm working as associate professor. So the talk today would be on fat intra-body communication, and the fat intra-body communication is something that I have pioneered over these years, over 10 years now. So we have got a good amount of applications and also some patents ongoing. So the idea of this presentation is to introduce you to this technology and to make a familiarization of the usability of this technology in our day-to-day life. Okay, so let's. Sujit, I hope I can share my screen, right? I can share my presentation.
Yes, sure.
Yeah. So in this case, you have to stop sharing.
The host has to give you the permission.
Yeah. Could you give me the permission so that I could share my presentation, please?
Edwin, could you please give him the permission?
Yeah, one second.
Okay.
Okay, you can share now.
Yeah, thanks.
I don't know if you see my presentation now. Do you?
Yes, it's visible.
Okay, excellent. Thank you. All right, so I start with giving you a background about Uppsala, where I am now. So Uppsala, Sujit knows it because Sujit had been here as a postdoc. Uppsala University is a university located in Scandinavia. Scandinavia is part of Northern Europe. And as you can see, it's the image of the globe, and then the arrow points down to Uppsala. So it's close to Arctic Circle, so it can be really cold during winters. So Uppsala is majorly a student city, meaning that we have predominantly student population here, and it has been the oldest university in the whole Scandinavia. It was established in 1477. And there had been a lot of Nobel laureates from this university. And the photos that you see on the screen is basically some glimpses from Uppsala. So a bit more detail about the Uppsala University. It is ranked one of first 100 universities worldwide, and it has 9 faculties, and there are 3 domains in which these faculties are spread. So the domains are majorly the arts, social science, medicine, and pharmacy. So the turnover is 700 million euro, and this turnover means that okay, we usually have external fundings from the European Union, also from national agencies, but also we have our own internal faculty funding. Right. So the departments, I mean, these are former departments. So there are quite many departments. We have engineering sciences, chemistry, mathematics, physics, and astronomy. And also we have something called the Swedish Institute of Space Physics. So we have a very strong group or very strong department for astronomy, astrophysics science. Then, of course, one other thing that we take a special pride on is our clean room facility. We have one of the biggest facilities for ultra clean fabrication. So we have, we are well equipped. We have well equipped clean room facilities as well. So my group is called Microwaves in Medical Engineering. So our focus is more about application of microwaves in medicine. So, but not only microwaves, but also other technologies are being used in my group for finding solutions for medical problems. So as you can see on the screen, this is my group, and these are like 2 different photos from 2 different times. So our group had been like on an average with the strength of 11 people, employed members. So the photo that you see to the right is more recent. So these are some of the members of the groups. And then these are the collaborators that we have. Let me start with a global issue of obesity. So obesity is something that even us in India has to deal with because of lifestyle, basically the food habits and all that. So what is the problem of obesity? I mean, obesity itself is not a problem. Obesity is a problem when you have to suffer comorbidities because you have complications due to fat accumulations in arteries and veins and so forth. So such scenarios could create problems with heart, with brain, with other internal organs. So in most of the cases, what you really need is that, as it is said on the slide here, that the rescue mission is not often failed because of the lack of treatment. In most cases, it is the lack of diagnosis that creates in fatalities, that ends up in fatalities. So you have to have a real-time diagnosis, a real-time monitoring of various disease conditions. And how can that be possible? And this is where you are talking about implanted solutions, where you can have various sensors that are implanted into the body, and they stays there, and then they relay information about the health status of that particular organ in real time. So how could that be possible? Because when you talk about it, body itself is a hostile environment, meaning that if you implant something, then it will be easily deteriorated, degraded by the bodily fluids. So to have something long-term implanted in the body is almost a nightmare. But on the other hand, thanks to the technology of prostheses and implants, especially regarding bone, because you have heard of, hip surgeries or knee replacement surgeries where you get either bioceramic implants or metallic implants. So those are the kind of implants that could stay longer. So it's not unheard of that the implants can survive longer in the human body environment. So one can think of making such implants also. But the real issue there would be making these implants smart and also active, not passive, because prostheses are usually passive implants, right? So what you want to do is to make active implants embedded with electronics that could relay information, that could pick information in the first place, and then later relay information. So picking up information is something that has been extensively researched on in terms of sensorics. But relaying information is something, especially in the intra-body context, is something that is really, really new. It's not really mature yet, because we yet have to see what are the possibilities one could use in order to transmit data within the body or on the surface of the body to something off the body, external to the body. So there are different propositions over past 2 decades. I mean, for example, we all start with, maybe you are familiar with galvanic and capacitive couplings. So those solutions have to address these requirements. For example, in the body, you're talking about, compared to like on-air communication, you're talking about short-range communication. You're talking about using body tissues themselves as transmission medium. Again, you're talking about near field communication because the distance itself is small. Then again, you have to consider which location you want your relay stations to be positioned. Do you want it in your head, in your chest, in your abdomen, or in the legs? Okay, it really depends on the condition that you want to address or condition that you want to monitor. So, the issue with capacitive galvanic, and also there are inductive solutions, is that they all work with low frequency communication modalities, communication protocol. So inherently, when you use low frequency, the problem is bandwidth, and the amount of data you can send over low bandwidth or low frequency is very limited. But when you're talking about real-time sending of data, transmission of data, as well as physiological data collection, then you have to collect a lot of amount of data, which has to be streamed in a real-time basis, which becomes a bottleneck for those technologies. So those technologies are very efficient when it comes to like simple monitoring, such as temperature monitoring or a pH level monitoring. So such information it can be handled rather easily. Whereas when you have to consider other physiological parameters, like if you want to measure the EEG, electroencephalogram, or ECG, so then you're talking about multiple channels working together. So that inherently means larger bandwidth requirement. So in those cases, these wireless solutions will not render useful. So you need to have alternative methods. So this is where we have proposed something called fat interbody communication. So what is fat interbody communication? Fat interbody communication is the technology, or is the technique by which you use the omnipresent ubiquitous fat in the body as a transmission medium in order to communicate from one point in the body to the other. So how is that possible? So if you look into this pictures, so you have basically provided with cross-sectional diagrams or cross-sectional images. They are real human images. They are taken from cadavers, meaning that dead humans frozen and cut. So those images are a bit gory to look at, but anyhow, what you can see is that the human body is surrounded with a layer of fat. And when you look at the fat is sandwiched between an upper layer of skin and a lower layer of muscle. So you have, when you think about it, you have 3 layers of 3 distinct permittivities, or let's say you have 2, you can approximate skin and muscle to a single permittivity because they are like above 40, above 50. And then fat is one very interesting tissue in the body, which is close to a dielectric because it has a very low, I mean, of course, when dielectrics can be any dielectric constant, right? I mean, but on the other hand, the conductivity is very, very low. So you have a low conducting, low dielectric material, which is fat. And also it is, one other good thing is that it is non-frequency, non-dispersive when it comes to its water content, because it's a very low water content tissue. So it will basically act as an inorganic material. I mean, even if it's an organic material, because of its low water content, it doesn't have a lot of frequency dispersion. So it has a stable performance over large frequency range. So again, when you think about it, you see that the fat layer is beautifully sandwiched between skin and muscle. And then as you all are electromagnetics people, are having antenna background, you can imagine that, okay, so then if you have a medium that are confined with highly dielectric and highly conducting mediums on either side, then you have a confinement of signals and fields within that boundary. So this is what exactly is happening. So what you could do is to excite a signal in one of the places and then make it propagate through that channel, through this fat, and bring it to the other end. So what would be the benefit that you gain from that? So you will gain the capacity of data that you can send. You could gain larger distance of transmission. You could gain better performance because galvanic coupling and capacitive coupling has highly dependent on the saturation level of the human. So if one day if you are well saturated, drinking water a lot, in that case your performance might go high. In the other day when you are like in outdoors, you've been perspiring a lot, the performance might go bad. And then of course security. What do you mean by security? Security is a confinement of your data within the required let's say required boundaries. So here the required boundary is your own body. So you don't want the data to be eavesdropped to another person so that he can put a ransomware into your device and then ask for money, for instance. And again, of course, the consumer is of prime importance because the consumer comfort has to be considered. For capacitive and galvanic coupling, what you would need is an environment that is modified, optimized for the technology to perform, meaning that the person has to walk or work on a grounded platform, meaning that, for example, a large infinite metallic sheet, and then as long as he or she is walking on it, the technique will work. So we have a collaborating institute called RISE in Sweden. They are based in a city called Linköping, a bit south to Uppsala. So the thing is that they work with capacitive coupling, and they have to have custom-made environments for the person to walk on so that the technology could work. So that was a very big bottleneck for them, because you cannot imagine this technology work in an outdoors environment. You cannot imagine if the technology would work if the person is taking a shower, for instance. So it is not very user friendly, to be very honest. Okay, so how could you do that? I mean, you can have those fat IBC nodes which are transmitting signals from one end, and then in some cases you might need some repeater nodes so that you could amplify those signals and receive it and transmit to larger distances. Then also as part of that, you would also have sensors that are implanted in the vital organs, and those sensors will transmit data through the fat IBC, and that data will be collected on a node called aggregator. An aggregator is something that relays the information to a person who is well trained or is responsible for the health of this person, meaning that your family doctor, your clinician. So how should that be possible? And this should be only possible through a secure system. For example, we collaborate with a company called, the company called Intel. And what they provide is a gateway called IHAB, and that is a secure gateway with firewall installed so that you cannot hack into it. But they give you a direct highway from the person to the hospital records. So it is called HIS, Hospital Information System. So that the doctor, the practitioner gets the data, the update, the status of the patient directly. Okay, so these are some results from what we have done in our studies. So the results compared to the phantom and ex vivo tissue. So phantoms are, as you know, phantoms are emulatory models that represents human body in its dielectric properties. So we could make phantoms of, we have a very good phantom fabrication facility where we could make phantoms of typically any part of the body, any organ, So what we have done in this study is to make a phantom of 3 layers: skin, fat, and muscle. And then we tried various propagation models at predominantly at 2.4 gigahertz to see how how good the fat transmits the signals through. And there the major parameter that you want to look at is the coupling S2/1, because when you talk about the near field communication, you don't most of those far field approximations doesn't work. So here you are mostly interested in if the data is leaving the node and getting received on the other node, and then if you lose the data, if you keep the integrity of the data. So this is what is important. And if you study S2/1, and that is more than enough for such applications. So that's why S2/1 has been adopted as a calibration or as a standard verification method. So as you can see, in phantom studies, we see that, okay, for different lengths from 2 centimeter until 10 centimeter, you get a pretty good coupling. And this is state of the art compared to any other, available technologies, including galvanic, capacitive, inductive coupling. And ex vivo means here we have used tissues from animals. I mean, here they are porcine tissues, meaning, okay, they are extracted from pig. So we have used porcine skin, fat, and muscle for this study. And we have comparable results. Of course, one obvious difference between man and pig is that pig fat do have a higher conductivity than human fat. So what you would extrapolate from this result is that the S2/1 parameters will lie in between the phantom results and ex vivo results for human, because for phantoms, the losses were a bit lower, and for ex vivo, the losses were a bit higher, whereas the human has something in between. So we have done following studies and even more. I have not included further studies in this one because some are partly being published and some are recently published. Of course, in our first article, we proved that the intra-body microwave communication through adipose, which is fat tissue, is possible. And in the second publication, we showed in our experimentation that real data packets could be transmitted through intra-body network using the fat tissue without packet loss with integrity. And then, of course, we studied the reliability of the fat intra-body communication, meaning that, given because the body is very, let's say, dispersive. So it has a structure which is not even, it is not homogeneous, it has a different morphology at different parts. So one has to consider that. So you have to see what is the absolute minimum or what is the threshold that you can expect over a distance, given all these abnormalities, and you will calibrate your communication to that threshold. So so you will normalize towards that. So that's the idea there. And then, of course, we, as I said, we also tried the effect of thickness inhomogeneity in fat, and see like how, if the fat flares out at some part of the body, or how it will affect your communication, or if it contracted some part of the body, how it can affect. So those studies were done. Then, of course, we have done other studies, like, for example, presence of blood vessels, which is a very very viable scenario that you could have crisscrossing blood vessels, larger arteries going through fat, and how that could affect the communication. Then we have also seen like how implanted antennas would work in a fat environment. Then some results have been also extracted from fat channel bending and polarization studies. And again, one feature of this fat channel is that you could have front to back coupling very easily, because you could also imagine some solutions of like low energy Bluetooth. So low energy Bluetooth is basically Bluetooth, but it is mostly used in wearable applications. So it works well when you have to communicate from the surface of the body to a device which is far from the body. But when you have to communicate from front of the body, frontal part of the body to back side of the body, then the body itself consumes a lot of signals. It eats up a lot of signals, and a lot less will go back to the body unless you have a reflector around it. So if you're standing next to a wall, for instance, then you have a multipath. So then you could get a reception in the back. But here through fat channel, you can have a direct path around the body through the fat channel, and with much lesser loss. So these are some examples of some topology optimized antennas that we have made in order to design a probe that could launch signals into FAT. And, you know, I mean, these are some characterization results, and then you see that there is a very good matching over the R band for this probe. So this matching is when you have like through connection, when you connect one probe face to the other. So these are some examples of the experimental setups that we had. And, you know, you see these 3-layer models in the picture. So the 3-layer models comprise of, the top one comprise of skin phantom, fat phantom, and muscle phantom. And then you have those probes on either ends. And then you have, you know, one probe launches a signal, the other one receives. Then you would think, right, okay, your body is not a section of tissue. Your body is a cylinder. Your body is a complete system where you're trying a section here. So how would that be a representative of what's really happening in the body if you want to excite the signal? Yeah, the explanation is that the signal received, I mean, the best quality signal received to the other port from the transmission probe is the one that travels through the fat. All the other part is losses, right? So this is like really a worst case scenario. So if you are succeeding in this worst case scenario, okay, you will succeed. You will definitely succeed in the case where you have the body, where you have those nodes implanted in the body. All right. So and you know, in the second image, what you see is basically an ex vivo tissue, that is the excised porcine tissue with skin, fat, and muscle. And then, you know, we obtain similar results. As I said, a fat of the pork do have, porcine tissue do have a larger conductivity. So you have larger losses. Of course, it happens something here with those graphs, but anyhow, the idea is that we have studied transmission through different other mediums, such as skin and muscle. Yeah, I think I have a question from Jean-Marc. Yeah, I mean, thank you for this question, Jean-Marc. I think I could answer your question right after this discussion, if you don't mind. Thank you. Yeah, so we also have done, we also have data packet transmission through FAT, where we used software-defined radio in order to transmit data. And then we have transmitted data packets through it. We have also measured the spectral density, and then also, you know, looked at the received power, whereas we also looked at the data and calculated the packet reception. So we have seen that, okay, I mean, it doesn't really affect the packet reception, no matter how far you are from the how far you are from the transmitter. And also what we have seen is that, okay, we can calculate approximately, let's say, to the maximum 2 dB per centimeter loss within the fat channel. And then, of course, you know, the fat channel could also be used for sensing. You could also use this for like tumor tissue models in this case. So, for example, what we have done here is to add a perturband into the transmission channel and see the correlation between the perturband size and the transmission itself. So, as you know, the perturband size increases and it constricts the channel, then of course you start seeing a drop in the reception, which is very much expected. But again, this also gives you an idea about how much of a size you would require for your perturband in order to constrict your channel. So what we have seen is that, okay, we can still have a reliable communication even if you have a 60% clogging of the channel. But on the other hand, okay, if you measure the absolute ST1, you will see the difference. You will see the minor signatures there, which could be used for sensing. So this could be also a possibility to use for a very simple device for screening breast cancer or monitoring the relapse of breast cancer once the person has gone through the surgery. So there is also always a strong chance of relapses. So you could also think of devices like an online monitor and you know, recurrences of such tumor. So this is also a study where we tried to understand how, you know, how the channel constrictions would affect your affect your communication basically. So this is also the results from them. So you see that, okay, there could be some effects, but not very large effects. So yeah. So, I mean, given the size that we have tried, there could be differences from -2 dB to -4 dB. So in one case, we tried a concave structure where the fat is basically, pushing in, and in the other one is the convex structure when the fat is pushing out. So in one case, fat is thicker, the other case, fat is narrower, right? So in narrow cases, of course, you will not have substantial effect because, the propagation would love presence of fat. Whereas, in the thicker case, it will not affect because the propagation loves thickness of fat. Whereas in narrow case, you will have an effect, but not very, very high effect. So that's why you will have a larger depletion of the transmission. Yeah, there are also some studies regarding the effects of the blood vessels crisscrossing the fat channel. So it has to do with the way that it is positioned. For example, if the blood vessels are orthogonally positioned to the transmission, the direction of the transmission of the signal, or it is in parallel to it. So there is also a splitter recombiner effect in some cases, whereas in other cases, you will have just a reflector in front of your direction of propagation. So then you will have a sharp drop in your reception. So these kind of studies were also done, and then we have published a paper in IEEE Access, I guess, about this. So this is also a study where we tried to do different transmission losses models with respect to where you excite in the body, because when you talk about fat channel, you can excite in fat either, or you can excite on the skin. Because you are talking about two different applications. You are talking about implant applications where everything has to be implanted. You can also talk about wearable applications where things can stand on the skin, but still the communication happens within fat. So you could either excite from skin or from fat. But as you can see in this table, there is a disadvantage if you excite from the surface of skin, because the problem is that skin is a very lossy medium, right? So we'll have the first step of loss in the skin, and then only the remaining thing will go through the fat, and then you will have the next stage of loss in the coupling portion of the skin, wherever you have the exit port. Whereas if you have a direct link within fat, then you have the best case scenario. But again, this is not impossible to excite that through skin. You can do it. But of course, you need a lot of applicator optimization in order to minimize that loss in skin. So this is an example. It's a E-field distribution of how the signal propagates from an implanted monopole to the other implanted monopole. So these are some work. I'm not going through a lot of details here because, I think there are 3 ongoing patent applications. So I'm not supposed to talk a lot about the excitation procedures as such. So, but I would like to show you a video, and then I would like to conclude with that, which I think you will appreciate. Sujit, can I share a video also?
Sure, you can share the video.
Yeah. Just give me a moment so that I could find the video. It should be there. Yeah, in the meanwhile, there are some questions I could answer the question too. Right. Okay. Okay, I have a question from Jean-Marc. Jean-Marc, hello, Jean-Marc. So Jean-Marc says, hello, Robin. How do you compare parallel plate propagation with on-body communication in terms of propagation losses? How do you include body losses? How do you include the body curvature? What maximum transmitter power and minimum receive power usually required? How do compare your architecture with communication using external reflections and or relays to transmit the data from one node to another? Yeah, thank you, Roma. So maybe I can take the first question here. How do you compare parallel plate propagation with on-body communication in terms of propagation losses? Jean-Marc, to be really honest, this is not a parallel wave propagation. It will be a dielectric waveguide kind of propagation. So you cannot completely approximate that to parallel plate because you don't have, as compared to metallic boundaries, skin and muscle do have losses. So they are. I mean, you can consider, or you can model it as lossy waveguides. And again, whereas you also have conductivity to skin and muscle, that helps you. That is the predominant factor that helps you to confine the signals within the channel. Then the question was how with on-body communication in terms of propagation losses. Yeah, Sujit, is that possible that I could interact with Jean-Marc?
Yeah, it's possible. If it's there, means he can directly talk.
Okay.
Yeah.
Jean-Marc, you there?
Yeah, I'm here. Can you hear me?
Yes, I can hear you, Jean-Marc.
So more precisely, my question was, okay, as you know, we can make purely on-body surface, from one point to another point on the body because the waves can be stuck on a lossy surface. So you can go from the front of the body to the back of the body. But as far as I remember, losses might be of the order of minus 40 dB. And in your case, because you concentrate your wave between the skin and the muscle, it seems that it's on your slide right now, you can expect minus 25 dB. So my feeling is that you have less losses using the fat layer compared to purely
you have.
Okay, that's clear. Okay, clear.
You have very low losses because fat inherently has almost no losses compared to skin.
But obviously, it's easier to make nodes on the body surface compared to nodes inside the body surface. I mean, inside the body, it's going to be much more easier to implement antennas
inside
on the body surface.
Exactly, inside the body it's much more easier. It's very straightforward, but the trick really lies where you want to have wearable application. So if you want to have your applicator on the body, still you want to couple through the fat. In this case, that first stage of coupling is going to be detrimental in order to get the best performance of your channel. Okay, I mean, to some aspect, maybe you could also excite creeping waves, as theory had been doing.
The creeping wave.
Yeah, exactly. Creeping wave propagation could be used, but we have also been successful in having low loss coupling into fat from the skin. So this is something that unfortunately I could not disclose how to do it, but we can do it. Because
I think you are directly launching the signal into the fat, right, rather than launching into
exactly.
The
So
skin,
because one good thing is the skin is thin. So when you propagate along the skin, you have larger thickness or larger distance, and then you have larger losses. But if you can compensate that with a resonance coupling from the skin surface to the fat, and if you leave the propagation within the fat, and then you couple it out from somewhere else, then you will still have lower losses compared to what you have on the skin transmission. So this is possible. But it will be lower than the quality, or the advantage will be lower than the direct coupling within fat. And coming back to your question about curvature, so from our simulations and also from our experiments, we have also proved that the curvature usually benefits for front to back coupling. Again, because the skin confines the signal from escaping, restricting the signals to escape from the body. So the curvature helps in coupling the signal from front to back. So it was very useful, actually, the curves in the body. Then, yeah, regarding the architecture with the communication, so we have also tried different modulation techniques. So we also have seen that almost all modulation techniques would work. And we could also, in fact, retrofit fat IBC antennas, or we call it fat IBC antennas, to standard BLE modules. So you can basically use BLE protocol for the communication, low energy Bluetooth protocol for communication. The only thing that you have to do is to change the front ends. Jean-Marc, thank you.
Okay, Robin, we have some other questions in the chat box.
Yes, I have a question from Mahadevan. Body, skin, muscle, etc. are highly lossy dielectric, which may demand higher power transmission, and hence safety comes into picture. Can you comment? Yeah, exactly. I mean, that's a very good point. And this is also why fat channel becomes extremely important, because fat channel needs very low energy. I mean, I will show you a demonstration, a real demonstration, and this is basically an answer for these questions. but before going into this demonstration, I would like to say that we have proven that we could even use, I mean, at most 1 milliwatt for the communication, which is not needed. So we started with 10 microwatt, and even 100 microwatt is more than enough to span a length of 1 meter in the body. So this will not create any sort of SAR concerns, because, I mean, of course, SAR has a direct relation with the amount of power you are inserting into the tissue, right? So yeah. But of course, you know, when you're thinking about transmission through skin and muscle, and also the confinement, the natural confinement you are obtaining reduces the diffraction or the penetration of those signal into the other layers. We also see that from our simulations and also from measurements. We also have thermal readouts to see that if the surrounding tissues are being heated up due to the presence of these signals in fat, which we saw was not the case. So we are not very concerned about that. And now we are running two big projects. One is a European project called SynTech, where we collaborate with ST Microelectronics, where we have distributed systems of sensors that communicate with each other, sitting on the surface of the body. And we also have a new project. It's a FET Open project, which I'm coordinating. And in that case, we have a direct communication from the brain to an artificial extremity through the body. So in both cases, we were able to convince the reviewers that, okay, this is not a safety concern, because the power used or the power requirement is very low, a maximum of 100 microwatts. I have another question. How much input power is normally used to establish intra-body communication through fat layer? Because due to body curvature and irregularities in fat distribution might cause large losses. Yeah, body curvature usually doesn't, I mean, as I said before, doesn't add to the losses. So curvature is not a problem. What could add to the loss would be like the amount of constriction in the channel. So that's what we are also looking at, like, okay, what power is an optimum for a threshold to be suggested for this communication. So again, as I said, we have been successful on pig models using 10 microwatts, and we have used pig models which are rather young pig models, like 3 months old. So they are not mature enough to develop enough fat in their body. So it was like only 5 millimeter thick maximum. So 3 to 5 millimeter thick fat was what we've been, trying. So in those cases, we've been successful with real sensors and real actuators to demonstrate a combined performance using, I think it was close to 20 microwatts. So then the question is like, what is the transmitted power? So transmitted power was that. And then the received power, okay, I mean, we have not checked the received power, but anyhow, that was enough for us to not lose any data packets. I hope I can share the video now.
Okay, I think.
Yeah, I mean,
the questions. Yeah, I can
is there
go ahead with
question?
another questions. I think there is no questions.
Okay.
So maybe I can ask for some more questions, Robin. So it's not questions, it's actually some concerns regarding this. Like what question are raised here, it's regarding the regularities in fat distribution, right? So mostly I think they might have concerned about the size of the transmission lane mostly, because the size of the fat layer is changing from time to time rather than the breadth. So the size of the transmission lane is changing. So whether that will cause to the losses, that may be the question. Or maybe from person to person it can change, right? From
yeah, exactly.
person to person. So how?
So I'm very well aware of that, and this is also the reason why we have to. Okay, I mean, it is very interesting because in the SynTech project, what we propose is that the human morphology is very different. The spectrum of morphology is very different. It's very vast. So we want to prove that this technology would work for an athlete who has, let's say, 7% body fat.
Okay.
Okay, and an obese person. So obese person, you understand how much fat the person would have. So you are talking about a spectrum with extremes of an athletic person and obese person. And then we would make models for athletic and obese person, both in numerical setting and also in phantom setting. So we have done that, and we have also tried body-worn nodes for fat IBC, and proven that on these two models, that they both work, right, for communication. So this has been established. Yes, I get one more question.
No, one more thing from my side. This is another concern, Robin. Actually, when whether we can compare this one to wireless body area networks, because in wireless body area networks we have different sensor nodes and different point, right? So it's very difficult to transmit from one node to another node through air by modifying the pattern and everything. So I feel it will be very useful when if you want to communicate from the front side, one sensor in the front side to the back side. So through the body, if it is possible to communicate, means it will be very good for wireless body area networks. So how will you comment on that? Compare this particular in the fat body communication with the W band?
I think the beauty of fat body communication, and also because if you have body-worn devices which communicates through air, the biggest issue is that you have environmental influences onto that, right? So it is not confined in a space. So it is open to everything. So if imagine if you are outdoors and you are exposed to rain, for instance, I mean everything will drop, right? This will not simply work. You cannot do it underwater. You cannot do it while you're having shower and all that. Whereas when you have this signal confined in fat, all those anomalies are being removed. So you will have a robust, reliable communication in this scenario.
Okay, right.
Yeah. So okay, there's also one last question, if I can answer, Sujit.
Yeah, sure.
Yeah. So the question is like, what about the effect of EM interference from other implanted devices in the body? EM interference, I mean, this is relevant for any electronic device, right? So before implanting any electronic device into your body, you should have the EMI compliance. So you have, I mean, that's a different ball game. So this applies in any implanted devices or any electronic devices as a whole. So I mean, this is definitely a concern. So you have to take care of it well before you think about implanting something in the body. So that comes in the EMI aspect.
Mm-hmm. Yes.
All right. So can I play the video?
Yeah, sure.
Hello, sir. Does the video have audio?
Yeah, I'm sharing with audio. Let's see if it works.
Okay.
Short, FAT IBC is a novel intra-body communication approach that uses the fat tissue inside one's body as a transmission medium for low-power microwaves. FAT IBC can enable communication at high data rates between multiple implanted or wearable body devices. One example of such a wearable device is a controllable prosthetic arm, also known as a bionic arm. In this video, we will demonstrate how a bionic arm is being controlled over fat IBC on a euthanized pig. Fat IBC is of course intended for humans, but pigs are very similar to humans in many anatomical ways. In the future, we hope to apply fat IBC to the human body. DGXP-free radio transceivers were used for the wireless communication. These radio transceivers are able to communicate with each other using the IEEE 802.15.4 network protocol. Each transceiver can be connected to a microcontroller or to a computer to create a wireless node that can both send and receive data. 2 temperature and humidity sensors were used in order to have some variable sensor data to send over the fat channel. Arduino Uno microcontroller boards were used to communicate with sensors and actuators, as well as for interfacing with the XP transceivers. Also, a dedicated USB interface allowed us to have one of the XP transceivers connected directly to a computer. A 3D printed multiple degree of freedom bionic arm, produced in-house by MMG, was used to visualize the working state of the system. Only 2 fingers were active for this demonstration. Antennas constructed specifically for the purpose of fat IBC were used, with 4 of them being designed to be implanted into fat tissue. The 5th and last antenna was designed to sit on the outside against the skin. 4 antennas were implanted inside of the belly of the pig in a square pattern. The 5th antenna sat in the middle of the square, but instead of being implanted, it sat against the skin on the outside. This node is known as the aggregator node and allows us to monitor the data that is being sent inside the body. Node 1 and Node 3 each have a temperature and humidity sensor connected. Each node reads the temperature and humidity values of its sensor. This data is then transmitted over the fat channel inside data packets. Packets are sent every 100 milliseconds as broadcast messages for all available nodes using a transmit power of 1.5 milliwatts at the XP transceiver. Otherwise, if the humidity at node 1 is less or equal to that of node 3, the index finger will be fully extended and the middle finger will be fully flexed. The microcontrollers at node 2 and node 4 run identical code, but control only one finger each. Squeezing one of the sensors in one's hand increases its humidity reading. As the humidity rises above that of the other sensor, we see the corresponding actuation in the bionic arm. When we loosen our grip of the sensor and instead squeeze the other sensor, the actuation of the bionic arm will change once again as the humidity readings change.
Thank you.
Thank you. Nice demonstration. So for curiosity, I'm asking, it's the big model, right?
Yeah, that's a big model, yes. Yeah, so this is a new product that we have. It's called B-Kratos. So B-Kratos is about brain-computer interface. So in this product that we do, what we try to do is to make a technology that is advanced compared to Neuralink. And Neuralink is something that is owned by Elon Musk, owner of Tesla, probably you know. So here we would like to do a real-time relay of thought process in the brain, so that you could use your brain to you control an artificial extremity through the fat channel communication. So yeah, so that's where we are now. Yeah, thank you.
Thank you very much, Robin Augustine, for the nice presentations. I invite attendees and panelists for if you have any queries or questions.
So I think there are no more doubts.
Okay, so if there is no more doubt, means I thank Professor Robin Augustine for wonderful presentation, and I also thank the organizers for giving us opportunity to chair the session and present. Thank you.
Thank you very much.
Thank you, sir, for sharing your profound knowledge with your talk, and it was full of real and valuable information. I also thank the distinguished chair, Sujit sir, for his valuable presence. I would also like to request you all to turn on the camera so that we can take a snapshot of the session, entire session.
Sir, can you stop sharing the screen so that we can have maximum participants on screen?
So, yeah, done that.
Okay, I think we have taken enough screenshot.
Okay, thank you.
Our next alumni session will be at 3:30. It will be handled by Manju Henry. The topic is the hyperspectral microwave sounder constellation of nanosatellites for climatic change and mitigation. Thank you.
Dr. Manchu, an alumni of this great institution. I am very happy to invite you to this webinar, APSYM 20. Very glad to.
Hello, ma'am. This is Deepti here. Would you like to try? Would you like to try sharing your video and?
Okay, let us start.
Not yet, sir. We have got that.
Okay, please. Time is 1:30.
No, it is 15:30. It is 10 more minutes, sir. 30 minutes.
Yes, correct.
Can you all see my screen?
Yes, I can. We can also see.
Yeah, okay.
You might need to put a slideshow because we can read your notes also.
Yeah. Can you see it now?
Yes, ma'am.
Yes, ma'am.
It's clear.
Yeah, okay.
Okay, let us start.
Yeah.
So we have.
Oh, good evening. Good evening to all.
So the schedule is.
Dr. Manju, as an alumni of this great institution, I am very happy to invite you to this webinar.
Hello, sir.
20.
Hello,
Can you
sir.
hear me?
Yes, the schedule is the session is to start at 3:30, so we can wait 10 minutes because people haven't joined.
Okay.
Okay, sir.
Definitely.
Welcome back. Moving on to our next session, we have with us Dr. Manju Henry from Rutherford Appleton Laboratory, UK. It's an honor for us to welcome her, who's also an alumni of Department of Electronics. The title of the talk is the Hyperspectral Microwave Sounder Constellation of Nanosatellites for Climate Change and Mitigation. We welcome you, ma'am. I now welcome the distinguished chair of the session, Professor Katie Matthew from CUSAT. I would like to hand over the platform to the chair.
Thank you. Dr. Manju, as an alumni of this great institution, I am very happy to invite you to this webinar, APSYM 2020.
Yeah, I'm pleased to come and give a talk to the university
nice.
as well.
It's my pleasure.
Yeah, it's
yes.
And thank you very much for the introduction as well. So I will start presenting my.
No. Let me introduce you.
Yeah. Okay.
Okay. It is my pleasure to introduce Dr. Manju to you. Dr. Manju Henry is currently working as the section leader of a millimeter wave technology group for small satellite payloads at RIL Space Science and Technology Facility Council, UK. She obtained her PhD degree in electronic engineering from CUSAT in 2002 and completed 5 years of postdoctoral studies at the Karlsruhe Institute of Technology, Germany and University of Surrey, UK. She is a leading technologist in the development of terahertz instrumentation, developed devices and systems for use in Earth observation and astronomy and material processing. She has undertaken key roles in several European Union, European Space Agency, European Southern Observatory projects, including Atacama Large Millimeter Array Telescope, METOP second generation satellite. Please, Manju.
Yeah, thank you. Thank you very much for your introduction. Yeah, I'm going to talk about the millimeter wave, submillimeter wave sensing from space. We look at a case study. It's a hyperspectral microwave sounder constellation of nanosatellite for climate change and mitigation. I'm working in the millimeter wave technology group at RAL Space STFC. So, give you an overview. I will give an introduction. I will explain the terahertz science application and its impact. Give some examples on terahertz astronomy missions from space, like Herschel, HiFi, and Planck. And we'll look into the Earth observation mission examples like METOP second generation, and the next generation meteorological sounders, which is the main topic of my presentation. That's a hyperspectral microwave sounders, and look into the case study of HIMSS constellation of nanosatellite for climate change and mitigation. So give an introduction on RAL Space and Millimeter Wave Technology Group before I go into the technical presentation. On the right-hand side is the aerial view of RAL Space at the Rutherford Appleton Laboratory, which is located 30 kilometers south of Oxford in UK. RAL Space is an integral part of Science and Technology Facilities Council, which is one of the research councils in UK. In addition to STFC, along with 6 other research councils and Research England and Innovate UK constitute the UK Research and Innovation. So basically, I'm part of RAL Space, STFC, UKRI. RAL Space is involved in the world-class science research and technology development, and we have been developing space programs, experience and expertise involved in more than 210 spacecraft missions so far. We work throughout the life cycle of the space missions. So starting from the inception of the design, the conceptual design, of the future mission, defining the requirements, and then involved in the design of technology and also scientific instrumentation, then handling of the data, and also in the providing the test facilities. For example, we have the vibration facility, we have the space test chambers for testing satellites, for testing instruments, as well as components. So another test facility is also being developed on campus. It's called the National Satellite Test Facility, which will have an 8-meter vacuum chamber, which will replicate the space on Earth, on ground. And we can do testing of the satellites ranging from very large satellites to small satellites in this facility, which is going to be commenced in 2022. So coming to millimeter wave technology group, we are developing cutting edge technology for frequencies ranging from 20 gigahertz and going up to 2 terahertz. So we start from the scratch, designing the devices. That's like the critical components like Schottky diodes. We manufacture and design it in-house. Then we are involved in the component development and design. For example, starting from free space components like frequency selective surfaces, antennas, mirrors, going into passive components like diplexers, orthomode transducers, and active components like mixers, multipliers, etc. Then we build the system, and mainly the systems for radio astronomy and Earth observation. So millimeter wave, sub-millimeter wave, if you talk about this frequency range, it lies in between the microwave and the infrared. In terms of frequency, is 30 gigahertz from up to 3 terahertz. 1 terahertz is 1000 gigahertz. So this frequency range compared to gamma rays and X-rays, they have very low power. So the photon energy is quite small. So I'm calling them not in terms of wavelength, but in terms of energy. They are small waves, but they have huge impact. So millimeter wave, sub-millimeter wave, what are the unique attributes? They are, as I explained, they have very low energy. Low energy implies non-ionizing, and they are considered safe for human exposure compared to X-rays and gamma rays. They are able to penetrate through clothing and various dielectric materials that are opaque to visible and infrared. Because of this reason, we can use terahertz in passive screening for security screening in airports. So you can see the photograph of a passive scanner used in an airport for looking at the concealed weapons. You can also look at the chemical molecular species of water vapor, oxygen, carbon monoxide. You can measure all this. And because of the bandwidth this frequency range is offering, you can also have application in ultra high data rate communication. But the most important application and having science impact, which I explain in my next slides. So if you look into the universe with different types of terahertz signals or with EM waves, visible light or X-rays or gamma rays, you see different physical objects. For example, if you are looking with X-rays or gamma rays, you can see active galaxies. If you look with visible light, you can see this light coming from the stars. Instead of that, if you are using terahertz and millimeter waves, sub-millimeter waves, the benefit is you will be able to look into the cold, dark, interstellar medium and cosmic microwave background. Using this, you will be able to understand the stellar and galactic formation and evolution of the universe. Similarly, this can be the terahertz radiation can be used for studying planetary atmospheres like gas giants and comets, And it also gives you information on the solar system. In order to get the best resolution, you have to do in situ or close encounter measurements, but there are no terahertz landers yet. Similarly, coming to the Earth observation, if you can study the oxygen and water vapor in the Earth's atmosphere, in the upper and lower atmosphere, you can do the weather forecasting and also numerical weather prediction. So, astronomy observations. So when it comes to astronomical observations, we have heard about a lot of ground-based observatories like Mauna Kea in Hawaii, the Stewart Observatory in Arizona, the Atacama Large Millimeter Observatory telescope in Chile, in Chanjandor Plateau. All these are constructed in dry areas at very high altitudes. This is because there is atmospheric absorption when there is water vapor. So to reduce this atmospheric absorption and to detect these faint signals, usually they are located at high altitude. Even at these excellent sites, atmospheric transmission is quite limited. This is shown by the photograph on the right-hand side. If you look at the transmission from various sites, including from Ridge A on Stewart Observatory and Mauna Kea and Chanjandor, you can see the transmission is significantly falls down because of the absorption in the atmosphere. So higher altitude observation is the best. So we can reduce this atmospheric absorption. An example is Sophia. We can do this observation from airborne observatories. An example is Sophia Observatory. But the conditions are still not perfect. If you look at the red and the black curve, the red curve is from the good ground site and the black is from the Sophia Observatory. So for astronomy, the best situation is no atmospheric attenuation, gives you perfect seeing conditions. So this can be tolerated, but it's still not good. So the best is the space. In the space, there are three classes of orbit. If you look into, there is low Earth orbit. That's where most of the weather satellites are launched. You have medium Earth orbit. They are used for navigation and specialty satellites. And the communication satellite from the geostationary orbit. As we go high in orbit, the time it takes for the rotation increases. So for example, if you are observing from, for example, 700 kilometers, the time it takes for one rotation will be around 99 minutes. From 3,600 kilometers, it's around 23 hours and 54 minutes. So in the geostationary orbit, you will be looking at the same point on the Earth always. Another sweet orbit is these Lagrangian points. So the benefit of Lagrangian points is that the gravitational pull from the Earth will be cancelled by the gravitational pull from the Sun. So there will be, these are stable orbits. So we have several Lagrange points, L1, L2, L3, L4, and L5. These are done for solar observations and studies. Beyond that, it's used for planetary exploration. So space is the best for these scientific observations and studies. Give you an example of a space mission. That's the Herschel Hi-Fi, which is launched by ESA. So one of the instruments used on this is the heterodyne instrument for far infrared. This was used for studying the evolution of galaxies, star and planet formation. The payload is located in this case at the focal plane of the 3.5 meter diameter telescope, and it has very sensitive receivers. These receivers are superconducting insulated superconducting receivers operating in the frequency range from 0.5 terahertz going up to 1.9 terahertz. These receivers requires cooling. So liquid helium is used as the coolant, but the problem is it will stop functioning properly when it ran out of the coolant. It has achieved a lifetime of 3 years from Lagrange point 2 location. And the spectral resolution achieved was 0.12 1 megahertz. Another example is used in terahertz astronomy application is the Planck Cosmic Microwave Background Observatory. So cosmic microwave background is the leftover radiation from Big Bang. Over the billions of years, the universe has been expanding and it's cooling greatly. Due to the expansion of the space, the wavelengths of the photons are increasing because there is a redshift. Currently, they are in the frequency around 1 millimeter to 2 millimeter. So the frequency range from 150 to 300 gigahertz. And the temperature is around 2.7 Kelvin. So it's ideal for studying. The millimeter wave observations are ideal. Sub-millimeter wave observations are ideal for studying this CMP observatory. In Planck, there is the low frequency instrument with instruments ranging from 30 gigahertz to 75 gigahertz. And here the instrument is cooled to 20 Kelvin. And for the high frequency instruments ranging from 0.1 terahertz to 0.9 terahertz, it's cooled to 0.1 Kelvin. Now coming to Earth observation from space. You can view Earth atmospheric species that are not visible from the ground, from the Earth's atmosphere. Doing so, you can see through aerosols. If you consider visible and infrared, they won't be able to see through the aerosols, but in the case of the microwave, you will be able to. I have a small video showing how these polar satellites are orbiting around Earth, and the Earth is rotating as well. Because of this reason, we will get a full global coverage. So these meteorological satellites, like METOP second generation satellites, will be able to measure the water and oxygen in the Earth's atmosphere and thereby predict the precipitation and atmospheric temperature. And the polar orbit provides full global coverage, as you have seen. So why millimeter waves? If you think of infrared, there are different types of instruments available for weather forecasting. This will include infrared, there are microwave sounders, infrared imagers are available. They are radio occultation instruments, but out of all these, millimeter waves have the most significant impact because they allow the global observation of temperature and weather in all weather conditions because they can penetrate through cloud. If you look into the Earth's atmosphere, you can see that if you look at the NOVA satellite view of Europe, it's covered with cloud. If you consider most of the time, any point on the Earth or the Earth's surface is covered with 50% with cloud. So most of the events happen in the order of hours when it comes to severe weather events like hurricanes or tornadoes. They are usually cloud shrouded and the key observables vary within 15 kilometers and 15 minutes. So you need to make very frequent observation. At the same time, you have to use instruments with millimeter waves, which reduces the forecast errors significantly. So these millimeter wave instruments play a crucial role in weather forecasting. So one of the examples of Earth observation mission is the METOP second generation. These satellites are currently being built. This is going to be launched in 2022 and will be operational until 2040. Each launch will contain 2 satellites, A and B, and there are 3 pairs. They will be launched into 800 kilometers and their lifetime is around 7 years. So you get a total of 20 years coverage and the observation will allow you to go beyond 2040. So the satellite instruments will be able to provide temperature, humidity, wind speed, trace gases, land and ocean images. There are 3 instruments on board METOP second generation satellites, which are millimeter wave, operating in the millimeter wave, sub-millimeter wave range, going up to 600 gigahertz. They are microwave sounders, microwave imagers, and ice cloud imagers. So we have been at Millimeter Technology Group was involved in the development of the receivers for the METOP second generation satellites. For both all these instruments, microwave sounder, microwave imager, and ice cloud imager. Above 100 gigahertz, we are using heterodyne systems. What's the heterodyne systems mean? The feeble signals from the Earth's atmosphere is collected by the antenna, as shown in the figure. It's amplified by a low noise amplifier. It will add less noise into the system. And we have a mixer for down converting into intermediate frequency. This is done by mixing the incoming signal with the local oscillator signal, and a difference in the frequency is generated, which is called the intermediate frequency. Intermediate frequency will be at lower frequency. So there are components available for processing these intermediate frequency signals. Either we can use filter banks or use backend spectrometers for processing the spectrum. For this, we are using a lot of components developed in-house. For example, we have packaged these low noise amplifiers, we have mixers, multipliers, and as well as space qualified Schottky diodes to build these instruments. So here are some photographs showing the engineering qualification model of the front-end receiver we developed for microwave sounder instrument at 229 gigahertz. So also for the microwave imager, two receivers, one operating at 166 gigahertz and 183 gigahertz. You can see here the RF modules, the LNA, and at the input port, the antenna will be connected, and you can see the mixer. The local oscillator signals coming in will mixed and down converted into intermediate frequency. For these, most of these components need DC, and there is a DC electronics box which is used for supplying the bias for the various components in the instrument. So we have successfully done the flight testing, and 160 gigahertz flight model has been shipped last week to APSYM for integration. So another important work we are doing is the calibration. We need to calibrate these instruments on ground before launch. An example on MWS, microwave sounding instrument, is a cross-track scanner. So when the satellite is flying, you can see the scanner. A nonlinear scanner will be doing the scanning the Earth. At the same time, it will be looking into the cold space as well as into the onboard calibration target. So why we need a calibration target? The calibration target and this cold space view are required for calibrating these instruments. So the calibration targets usually have absorption very high. So whatever signals falling on it will be absorbed. Therefore, the emissivity is equal to 1. So why we need that high absorption is if the emissivity is equal to 1, you can say the physical temperature measured is equal to the brightness temperature. Brightness temperature is the unit we measure the radiance from the microwaves, radiance going from Earth's atmosphere into the satellites. So the fabrication was quite challenging, and also the design is quite challenging here. It consists of aluminum pyramids, which is coated with ecosob material, which is carbon with iron loaded material. We can't use very thick, like thick layers of absorbers cannot be used because that will increase the variation of temperature between the pyramid tip and the base. In the base, we have thermometers for measuring the actual physical temperature of the target. So before launching, we test it in our thermal vacuum chambers, replicating the space environment. So we have the two calibration targets. One calibration target is maintained at 80K, and the other one, the temperature is varied from 80K to 315K, and that will replicate an Earth target. So you can see here we have measured a return loss less than minus 45 dB over the entire frequency range where the instrument is operating from 20 gigahertz to 230 gigahertz. So we have a major challenge in terms of climate. Extreme events are on a rise. The catastrophes resulting due to these extreme events are causing billions of losses. If you compare to 1980 and to 2018, almost these number of natural loss events almost doubled. So these are from various like geophysical events, meteorological events, hydrological events, and climatological events. So this is due to global warming. The average global temperature is rising, and this is leading to acute hazards such as heat waves and floods. They grow in frequency and severity, and chronic hazards such as drought and rising sea levels are also intensifying. So what we need is an improved weather forecasting. So that's what I'm looking for into hyperspectral microwave sounder. So the Earth observation have current meteorological satellites, which we are being built and going to be launched, have serious limitations. Let's look into what are the problems with the current meteorological state-of-the-art meteorological satellites. They are large satellites, and they need a capital commitment over 300 million pounds. And because it's being developed on large satellites, so costly, frequent technological updates are not possible. And the number of satellites you can launch in the orbit is limited to 2. Take the case of METOP second generation. You will have 2 satellites in operation, which will give you a revisit rate of 12 hours. What I mean by revisit rate is the number of times the same satellite see the same point on the Earth. When it comes to hurricanes, as well as the transient events like tornadoes, in these cases, we have to increase the revisit rate at least to 30 minutes. So this is a serious limitation of our weather satellites. And another important limitation is they are giving low resolution because the spectral resolution is quite limited. And this reduces the accuracy of weather forecasting. With the rollout of 5G is going to be a serious threat in the future for our weather satellite. This is because these interference signals will mask these faint signals coming from the Earth's atmosphere. So that's also going to be a serious threat. How we can address this problem? That's why we need these hyperspectral microwave sounders. What's a hyperspectral microwave sounder? We have 2 channels in this HIMS instrument, one operating from 50 to 68 gigahertz. That's for oxygen sensing and temperature profiling. 175 to 192 gigahertz channel, and that's for water vapor sensing. This is first of its kind. This hasn't been demonstrated before. Hyperspectral microwave sounders improve the spectral resolution by 100-fold. So as a result, the accuracy of weather forecasting improves. So this is what's a HIMS constellation of satellites for climate change and mitigation we have proposed. So this gives a rapid revisit rate of better than 30 minutes if we can launch a constellation of nanosatellite, which will be cheaper compared to these large satellites. And this will also give a better spectral resolution. So let's look into compare these 2 cases with METOP second generation and the hyperspectral microwave sounder. On the METOP SG, you're looking at a mass or a weight of around 4,000 kilos. Whereas for the hyperspectral microwave sounders, you are looking into 20 kilo. The number of channels in this case is increased to 1,000. Whereas in the METOP second generation satellite instruments, the maximum number of channels is 20. So with hyperspectral microwave sounders, think about these spectral channels give you different slices from the Earth's atmosphere. By increasing the spectral resolution, you will get more information from the Earth's atmosphere, which will improve the accuracy of weather forecasting. So we are expecting an improvement of 30% in precipitation and 10% in temperature observation. This will increase the vertical resolution and thereby improves the vertical forecast accuracy. And it's also crucial for noise mitigation, because in the future, as I explained, it's going to be a major challenge for the weather satellites because of these interfering signals. So the benefit of hyperspectral microwave sound is because they have numerous channels. If there are interfering channels, it can be removed without loss of information. So that's the benefit of hyperspectral microwave sounding. We have done the technology development of this instrument. The requirement was, it was quite technically challenging, the development was. The reason being, the radiometric precision or the sensitivity required was 4-fold better than the current instrument being developed for METOP second generation. We have managed to achieve this using very low noise amplifiers and also using ultra high resolution spectrometer as the backend. We measured a system noise temperature less than 200 Kelvin. That means we are getting an NE delta T. That's the minimum noise temperature measured of the order of 0.25 Kelvin. So there is some margin there as well. And the wideband spectrometer was developed by Star Dundee. It's a company that's spin out from Dundee University. And they have developed the spectrometer and a factor of improvement of 40 compared to the baseline. So one another challenge is miniaturizing the radiometers, because these radiometers we can't get it installed on nanosatellites. If we can't miniaturize the hyperspectral microwave sounders, then we have to go for large platforms. Then it will be difficult to launch a constellation, which we are planning of 30 satellites to get the 30-minute revisit rate. So we managed to get all these components packed by putting it into vertical stacks, and an ultra compact radiometer was built and tested, and it gives similar sensitivity to the better than the microwave sound radiometers. The volume is reduced by a factor of 50. So you can see here the electronics, the DC, you have seen earlier, all these coaxial cables are replaced by flexible PCBs, and all the waveguides are integrated inside this module. So you have all the functionalities inside this small block, including low noise amplifiers, mixers, multipliers, everything are integrated into the block. You also have the compact wideband spectrometer reduced into a size of 100 by 100 by 46. So we can accommodate the whole radiometer inside a nanosatellite. So this is the roadmap we are planning. So initially we demonstrated the instrument in the lab. The next step is to take it into an airborne demonstrator. So we usually measure it on facility for airborne and atmospheric measurement. It's a NERC facility, Natural Environment Research Council facility. So we are going to test the instrument in January 2021. Then we also got the funding to develop a pre-prototype payload for a nanosatellite. And we are hoping that we will be able to launch it by 2022. And a constellation can be built by 2027. We are looking for funding from private and government grants to realize our ambition. So why now? So new space is opening up because the launch costs and the spacecraft costs are rapidly decreasing. The weather previously was part of meteorological institutes, but now even NOAA, the US Meteorological Institute, they are considering incorporating private weather data. So it's a rapidly emerging market. There is huge processing power available. So there is advances in computing and AI, and this will help us to give actionable insights into the weather. And we also will be able to address the congestion of frequencies using hyperspectral microwave sounders. So it's a favorable economics and emerging market opportunity. So these are very important for addressing science as also real world challenges. An example, I have shown a couple of examples for the explaining the global impact. For example, the Event Horizon Telescope. Event Horizon Telescope is a collection of telescopes that's all over the world, which work in unison to take the photograph of the black hole shadow. And they managed to take the millimeter waves using ALMA telescope and the JCMT telescope at Hawaii. They managed to take the black hole shadow of the M87 galaxy, which is a significant achievement. If we can build this constellation of hyperspectral microwave satellites, we will be able to mitigate against catastrophes like hurricanes and tornadoes. It's also quite crucial for managing future energy resources, because these energy resources like wind and solar is dependent on weather. So it will help to manage the grid and also managing the managing our energy resources. And also this HIMSS and Spectre constellation is that Spectre is another instrument I'm building for frequency monitoring as well, which is crucial for future 5G threat for our weather satellites. So I'm concluding my presentation. So we have looked into the benefits of terahertz, what's its importance to Earth observation and astronomy. This provides key astrophysical information relating to stellar and galactic evolution. It's also very important for remote sounding the Earth's atmosphere. Terahertz observation from space will increase with METOP-SG and small generation of constellation satellites we are planning. There are also other wider operational benefits like weather prediction, security, transportation, gas sensing, telecommunications, etc. These wave energies are quite small for these terahertz, but they have huge impact. And thank you very much for listening. The new innovations will lead to new space, and it's open for questions.
Thank you, Manju. Now it's time for interaction. You can ask questions.
Hello.
Hello.
Yes.
I would like to know that how is 5G going to affect your weather satellite to such a great extent?
Yeah.
And
so
5G is a fully planned activity for this. And then if 5G is going to bother, then 6G may bother you more. So
of course,
what is the mitigating things which we are thinking of?
yeah. So the 5G currently it's up to 24 gigahertz. The meteorologists are really worried because even the harmonics can cause interference. An example is the small satellite SMOS, and that satellite with the it's operating in the 1.4 gigahertz. The effects of RFIs on this small satellite is significant. Yeah. So yeah, so we are expecting that if it rolls into this frequency range, it's going to affect our weather satellite. So only option is to have instruments which are resilient to 5G. HIMSS is an example. So everyone is planning, even NOAA is thinking of all the future instruments need to be hyperspectral. So the benefit is even if you are contaminating your channels, some of these channels, we will be able to remove these channels without loss of information. Whereas in the current satellites, where the instruments have limited number of channels, even if you lose 1 or 2 channels, you will lose a lot of information.
So, thank you very much. It's a very great research work which needs to be done. And then, of course, we have other bands of IR, VNIR, etc. But they are all not microwave based. They are, of course, they are based because of the problems of actual detection. And then this one, I mean, they have limited applications. So anyway, this microwave sounder and this will have a great application in future. And I think, or possibly they have to look for real bands where they could exclusively operate. I think that is also another thing which they have to see.
Yeah, there are protection provided by these, like ITUs, they provide protection. But the problem is the protected channels will be okay. But in the nearby channels, where there's the harmonics or the window channels will get affected. So for example, if you take 5G, it's going up to 24 gigahertz at the moment. If you take its second harmonic, it's in the 50 gigahertz, right in the oxygen
Right
band.
in that oxygen band, correct.
So that's going to be a problem in the future. We know the might of the telecommunication. They won't stop. They will get extended to higher frequencies. So we have to take our own measures to be resilient to the RFIs.
Communication anyway is a must and has to take top priority. Otherwise, we can't even talk to each other. Thank you very much.
Thank you.
Dr. Manju, your work is very challenging because your scanning passive radiometer is operating with a frequency range of 23 to 229 gigahertz, and also the temperature variation is from 80K to 350K. It's very challenging one, no?
Yeah, it is. It's quite challenging, and developing this instrumentation, because it's basically at higher frequency. When you go higher in frequency, all the sizes will come down. So if you're manufacturing the waveguides, the size goes significantly small. So we have this very high like precision development facility where we manufacture, we have these kern machines and nano machines, which enable us to achieve these waveguide sizes. So it's really challenging.
Any questions, please?
Hello.
Yeah.
Is 5G safe for human health?
I don't think it will be an issue because that's what I explained previously. We have seen that they are non-ionizing compared to X-rays and gamma rays. These microwaves and millimeter waves, they are very less power. So there is not much research done in this area to prove that they are going to affect your health. So I don't think it's going to be a problem. It's something like people are exaggerating on it.
Okay, one small question out of curiosity. After your course in QSET, which other course led you to reach this point?
Okay, so I have, after completing in 2002, I worked as a postdoctoral researcher at Karlsruhe Institute of Technology in Germany for 2 years. Then I worked in 3 years at University of Surrey. Then I moved to STFC, Rutherford Appleton Laboratory in 2007. So I have been working in the lab for the last 13 years now.
So as a doctorate, you left QSET, isn't it?
Yeah, I got my PhD from
who was your
University.
guide?
as Dr. C.K. Anandan.
Oh, very nice, very happy, very proud. Okay, nice.
Any more questions?
Hi, Manju.
Hi, Anandan sir.
Nice to see you presenting.
Yeah, thank you.
Okay, thank
Then,
you. Yeah.
okay, let me conclude then.
Yeah, thank you.
Dr. Manju, your
Excuse me.
research field is very interesting and relevant, mainly for weather forecast, atmospheric study, global warming, etc. You have presented the work very beautifully with enough supporting data. It is rather an exhaustive study, including the challenges and the limitations. I'm very happy to see that you have filed for patent also. Congratulations.
Thank you. Thank you.
Excuse me. I think we can take a screenshot if every panelist turn on their video.
Yeah.
Okay, I think we have taken screenshots. Thank you.
Thank you.
Thank you, ma'am, for your enlightening talk. I also thank the chair, Professor K.T. Matthew, for his presence. Thank you.
Thank you.
Our next speaker is Professor Patricia Savi from Politecnico di Torino, Italy. The title of her talk is Graphene Tunability at Microwave Frequency. The distinguished chair for the session is Professor C.K. Anandan from CUSAT. I would like to hand over the platform to the chair. We welcome you, sir.
Thank you very much, Mr. Chairman.
Yeah, hello.
Hello. I just have to understand how to show you my presentation.
I will just introduce you.
And because I have a share screen, but it's only related to the panel, so I don't find any way to share my PowerPoint or PDF. I don't know what is the best.
Ma'am, you can share. You can press the share screen button, and then you can select the window which has your presentation.
Okay, yes, I manage. At the beginning, it was not working,
Okay.
but now it's working. So,
Okay. I'm happy to introduce Professor Patricia Savi, who is from Italy. He's working in Politecnico di Torino, Italy. Of course, we had worked together. She's an expert in FSS. She was a consultant in Alenia and conducted research on the analysis and design of dielectric radomes after her PhD. Then she worked in a Center for Antennas and Electromagnetics under the National Research Council of Italy for about 10 years. Then she joined the Electronics Department of Politecnico di Torino, which is deemed to be university, as an associate professor, and she currently is a professor. Her area of interest include dielectric radomes, FSS, waveguide discontinuities and microfilters, high altitude platform propagation channels, and GNSS, that is a global navigation satellite system reflectometry, and for soil moisture retrieval and things like that. And now her current interest is on characterization of microfrequency of novel materials, carbon nanotubes, graphene, etc. So the micromaterials, it is currently an important topic because when we talk about 5G and all, that reconfigurable antennas and devices. So tunable devices, it's a very important component in that. So I request Professor Savi to give her a talk on this topic on tunable devices, micro devices on graphene. So over to you, Dr. Savi.
Thank you very much for your introduction. And this is the title of my presentation. And I am in Torino. Here is a map, and I'm very glad to join you virtually at your conference. And Torino is in a region called Piemonte in North Italy. Perhaps you know Piemonte because and Torino because of the Egyptian Museum and the Fiat car manufacturing and also Olympic Games. And if you're tasting wine for the special red wine. The symbol of the town is Mola Antonelliana. That is a building that is poor concrete, height 168 meter. And I'm working now in Politecnico. I started my research career as a CNR, then after 10 years as a professor, and then I moved to Politecnico, and Politecnico di Torino started in 1859 and has two buildings for engineering and architecture. The building for engineering is relatively new and is downtown, while for the architecture faculty, we have a castle, very nice and very expensive to maintain, that is close to the River Po. And specifically, I am Politecnico as many international students. These are not the last year data, the previous year, but anyway, we have a 16% of international students. And you have the list, and your country is not so high, but anyway, we have 2% of students from India. And I'm specifically working in the electronic and telecommunication department. We have now a new building, and here I am in the red spot just across this bridge. In Polito, there are 11 departments. Each one is devoted to a special research topic. And I work in the electronic and telecommunication departments, but I have many cooperation with DISA2 department, that is Applied Science and Technology, and also Mechanical and Aerospace Engineering department. Here is the outline of my presentation. I briefly talk about graphene properties at microwave frequency and of commercial graphene flakes characterization. Then I will move on the tunable devices that we developed with the help of these commercial graphene flakes. We started doing a tunable attenuator, a phase shifter, and antennas with 1, 2, and 3 stubs. Then some conclusion. As you know, graphene is a two-dimensional array of carbon atoms arranged in a honeycomb lattice. And since the discovery in 2004, there has been plenty of theoretical study about graphene and their properties from a mechanical, electrical, thermal point of view and application. In fact, graphene exhibit a high value of conductance, mobility, mechanical strength, so could be used in a big variety of fields. But I'm most interested, obviously, in the microwave frequency range in which I'm working. And at this frequency, graphene behaves as a tunable resistor. what I mean, if you consider a graphene layer deposition that could be drop casted or screen printed, it exhibits general high resistance. When you apply a DC voltage to the graphene deposition, the resistance reduces. So this idea is at the basis of microwave tunable devices based on a standard device modified with an insertion of graphene pad or deposition in order to have these tunability effects. We decided to use commercial graphene. This work was mainly developed in the last 2 years with my colleague Mohammad Yazir. And he was a former student of mine and a master course. Then he did a PhD with Professor Bozzi in Pavia and worked also with Stefano Bellucci. And then he came back to Polito and for 1 year of research assistant. And we started working on these ideas of using commercial graphene in order to have tunable devices. So we started with tunable attenuator, phase shifter, and patch antennas modified with stubs in order to have to change the frequency of operating of the antenna. We decided to use commercial graphene because till now some experiments were done on this topic, but using lab graphene made in the lab. So I had some graphene flakes bought from Nano Innova, is a Spanish company, and we analyzed first these flakes with the Raman and spectrum and the phasm. Here is in the red curve is the Raman spectrum we obtained for this type of graphene. This analysis was done in cooperation with DZAT and my colleague Massimo Rover. It is a very, very expert on Raman spectroscopy. So he explained me that this graphene could be few layer, 5, even perhaps 10 layer graphene, surely is not mono layer. And looking at the 2D peak, if you have here for a comparison, I have the Raman spectrum of graphite. You see the 2D peak with this bumps. We don't have so much this effect, but the 2D NG peak for us is only 0.5 and it should be more than 1 in a monolayer graphene. Anyway, that was a reasonable graphene type from a commercial point of view, so we used in our analysis this type of graphene. We also did phasm analysis. Here are 2 images, different dimensions in nanometer, and if you look at the right images, you can see flakes of graphene, just to be sure that the graphene we were using could be reasonably considered a few layer graphene. And the first components we tried to realize, was quite simple, a tunable attenuator. This is form, we did the design on a Rogers substrate with a thickness 0.78, epsilon is 3.6 and tan delta is 0.004. And we just designed a transmission line, a very simple transmission line with a gap. And in the gap, we inserted by drop casting the graphene. The line width was 1.66 in order to have a characteristic impedance of 50 ohms. By applying a DC bias voltage to the graphene deposition, the graphene resistance drops and also the attenuation. First, we did some simulation in order to understand the dimensions, the optimum dimension of the graphene deposition. If you look at the aspect ratio, defined as the length L over the width W, we did some consideration about the influence of the shape of the graphene deposition. So the aspect ratio 1 means a square deposition, and the aspect ratio 0.1 a very very thin rectangular deposition. We choose a typical value of resistance for graphene ranging from 300 to 3000 ohm per square, modeling graphene as a thin resistive sheet in the ANSYS HFSS simulator. We obtain the transmission coefficient, the S21 dB that you have here. There are many curves because they represent three different aspect ratios, 0.1, 0.3, and 1, and the minimum and maximum values of sheet resistance. We have noticed that, for example, with aspect ratio 1, we have minus 12 dB of S to 1, and a good range, I mean a good variation. This case is the red plot. So from 300 to 350 of resistance, that is minus 32 dB, we go to almost 12 dB. So the dynamic range of variation with the DC voltage applied is quite good. But if you consider an aspect ratio of 0.1, second case, and it's the black curve, dotted and solid, you have minus 3 dB for the transmission coefficient. That is fine, but the range of variation is reduced, is less than 10 dB. So as usually is a trade-off, the shape of the graphene, at least from a simulation analysis, depending on what you want. So we choose an intermediate value of aspect ratio 0.5 that gives minus 6 dB of transmission and a range of variation with the DC voltage applied of 15 dB. Choosing this aspect ratio, then we analyze what is happening, changing the sheet resistance of the graphene again from 350 and 3500. And you can see that you go from minus 22 dB to minus 6. And so we expect a similar variation in the experiment applying a DC voltage tuning the deposition. Measurement, we realized the line, it was very simple, just with a standard etching technique. We deposit the graphene flakes with drop casting, just making a mixture of alcohol isopropylic and graphene flakes. And we deposit the graphene flakes on this gap, and then the alcohol is evaporating. And here on the left, you see the measurement. We have two broadband bias T connected to the line, and connected to the radio frequency port of the bias T is connected to the network analyzer. And then we have a DC voltage supply in order to have the different voltage to the graphene part. Here is the first results. You see the value in the table that are plotted in the graph. The voltage applied is from 1 to almost 10 voltage. And from the measuring the current and voltage, then we have the resistance of graphene, and then we can evaluate, given the shape of the pad of the position of the graphene, we can also measure, calculate the sheet resistance. So we go from a very high value for almost no voltage and current apply is 1000, and then we have a progressive reduction of the resistance up to 9.6 volt. A small break because of the is midday, and I'm afraid you're disturbed by the bell. That I don't know if you can hear it or not, and if it's a problem.
It's all right, ma'am. Can wait.
If it's not a problem because of the bell, I go on. And here you have another result, the transmission coefficient as a function of frequency. While we were doing the voltage, DC voltage measurement, we were also using the network analyzer to measure each step the transmission coefficient. So you see what happens from 1 volt, that is corresponding to a very high resistance, up to 10 volt, that is growing. The transmission coefficient is going from minus 18 dB to approximately minus 8 dB. So we were, this is the first attempt of having a tunability of graphene flakes deposition was quite good as a result. And we went on and we tried to do a phase shift. So there are many applications of these components in electrical steerable antennas, or for cellular communication, wireless LAN, automotive radar navigation, space system. And the basic principle of this component is to change the path of the signal, and to have a short path and a long path in order to change the phase of the signal. We decided to do this with a configuration based on a transmission line here on the left, and 2 stub line in order to have a symmetric configuration and more effects. The stub line are open circuit at the end, and we model a graphene pad with a resistance here connected to the ground. So the lamped resistor are modeling the graphene, and we have also a tapered line in order to go from 50 ohm to 100 ohm line and match all the structure. Again, with this configuration, we've started to analyze the configuration, understand the behavior with some simulation based on ADS and HFSS, in order to find the input resistance, a real part and imaginary part, and in order to optimize the geometry. The length of the tapered line here, and also the length of the stub open at the end. And we made some analysis in order to understand how can we have to vary the graphene resistance and the length to have the best results. Here is some data. We tried, here is the length, the column and the length of the tapered line. It was chosen 3 millimeter, 4, 5, 6. Here also the length as a function of wavelength, and the length instead of the line and the stub. And in order to find maximum variation of the imaginary part and relative small variation of the real part for the input impedance, we found that the best solution could be have a tapered line of 6 millimeter and a line stub of 0.3. You see that here you have a 44 for the variation of the imaginary part. That is the maximum. After this analysis, that was done with ADS. This is a model with ADS. Then we did a full wave analysis, considering this time a Rogers substrate of 3035, thickness 1.5 millimeters, and the thickness of the copper of here now see a mistake, 35 micron. Okay, and the line, the width of the line, in order to have an impedance of 50 ohm, is at 3.2 millimeter. Here you have a zoom of the one of the stub. You have the tapered line and the pad and the graphene deposited between this pad short circuit and the line. We had to have some distance between the short circuit hole and the pad, so we decided for this small plate in order to be able to drop cast the graphene. And here's some results. We did all the analysis for frequency 4 gigahertz. And concerning the amplitude and phase variation of the S21 parameter, the amplitude variation, you can see that is decreasing for increasing the length of the stub from 0.25 to 0.3. And instead the phase variation is increasing for increasing the line of the stub. So we found an optimum length, at least from a simulation point of view, of 0.3 lambda for the stub. In this way, we can have a minimum amplitude variation and a reasonable phase variation. We finally looked also at the aspect ratio. Also in this case, here the deposition of the graphene as a length and width that can be changed. And so we did an analysis with a different aspect ratio, 0.2, 0.8. And we noticed that reducing the variation, the aspect ratio from 0.2 to 0.8, here is the variation. Varies the amplitude and phase, obviously, of the transmission parameters. So we choose the case in which we have a maximum phase variation that this nominal was 73 degree for an aspect ratio of 0.2. Here is the setup. Measurement setup. We use in this time a portable vector network analyzer, very small here, connected to a laptop, power supply, and bias for radio frequency measurement, and the phase shifter here. Port 1, port 2, here is the prototype, one of the prototype we did of the phase shifter. Not very easy to see, but in this small gap, there are 4 graphene deposition. They are always drop casted with alcohol isopropyl. And here the results. First, we did again the simulation, looking at the real variation of the resistivity we had with our graphene. And in the second panel, the measurement, S11, the amplitude and the phase. So you can see here in this part the phase variation that we obtain starting from 0 volt, the orange plot, to 6 volt, that is the black plot. And here is the variation we had in this work. It was 33 degree. Yes, the theoretical one was much further optimized. I realized with better technique. We just used the standard etching technique to do all the components. And the figure of merit of the phase shifter, defined as phase shift variation degree on the insertion loss variation. Anyway, in this work is quite good. It's 82. In a previous work of Jacek was only 13. They had a 40 degree of phase shift, a little more, but not such a high figure of merit. So with a design, thanks to simulation and a try and error procedure, we managed to have a reasonable phase shift with a quite high figure of merit. And last components, if I still have time, is the tunable graphene antenna that was designed starting from an idea of Professor Nashdam that was in Torino as a visiting professor for 1 year in 2017, and he was studying a patch antenna with a carbon nanotube film. But carbon nanotube film cannot be tuned with applied DC voltage. But starting with from this idea, we modified the design, optimizing the place in which the graphene deposition should be inserted in this stub. This is a standard patch antenna inset feed, as you can see, but on the radiating edge is inserted in the middle stub, short circuit stub, with a gap, and in the gap the graphene position. And from this design, yes, was done a model in order to understand the position of the graphene. This is the stub, short via, can be simply modeled with a transmission line theory. So a first line of length L1, then the graphene deposition that is modeled as a resistance, and the second line. So starting from the original configuration in which the gap was in the middle of the stub, we defined better performance if the graphene pad is close to the patch antenna. And with one stub design, the shift in the resonant frequency of the antenna that was around 5 gigahertz was found to be around 200 megahertz frequency shift, at least for simulated results. And this antenna was designed on a taconics substrate and with a similar results, but we went on and we tried a different configuration with 2 stubs symmetrically placed along the radiating edge. We had, at least for simulation, a very low reflection coefficient, minus 27 dB, and better shift in frequency. And then we also try a 3-stub configuration, but at least for the 2-stub configuration, here you can see the prototype that was measured in anechoic chamber for the gain and also for the tuning. Here in this table you have the tuning voltage from 0.3 to 10 volt, the current value, and the resistance that in this case was from 700 to 70. And you see what happens to the reflection S11 of the antenna. From 0.3 volt, for example, the blue plot, you go here, the red curve is at 10.5 volt. And so we had a shifting frequency of 350 megahertz by applying this voltage to the graphene pad. And finally, we try a three-stub design if it's even more complicated to the deposition and so on. And we had even better results, at least in simulation of more than 400 megahertz shift in the frequency due to the DC voltage applied to the graphene part. We also checked the gain of the antenna and we measured the gain, and we found that the gain value, fortunately, in the project was not so much affected by the presence of the stub and of the graphene pad. So with this configuration 1, 2, and 3 stub, we can manage varying the resistance of graphene but applied voltage to have a good tunability of the antenna of at least of 300-400 megahertz. Some conclusion now about all this work. We tried with commercial graphene to obtain devices that could be tuned with an applied DC voltage. We did a cheap fabrication of tunable components, and also the graphene that was commercially available was not so expensive as monolayer graphene that could be realized in a lab. And we had a good performance on the attenuator and the phase shifter. Currently, we are working on the phase shifter. We found a better configuration with a different layout in order to increase the phase variation that was around 33 degrees, and with this new configuration we can get more than that. And we also tried with a patch antenna with graphene inserted in addition on a stub, and we had an improvement in antenna reflection coefficient, no particular impact on the gain on the antenna, and the possibility of vary the frequency, the resonant frequency of the antenna of up to 400 megahertz. Let's conclude my presentation. Thanks a lot for listening, and if you have any questions.
Okay, Dr. Savi. Grazie.
Thanks a lot.
There is one question in the chat box. How does the attenuation obtained vary with temperature?
So going back to the graphene antenna or the attenuator?
Attenuation, yeah. I mean, the property of that graphene, when you apply the voltage, it is varying. So how does the temperature affect on that one?
The temperature, yes. We had to be very careful in doing the experiment in all cases. In fact, at the beginning, we were not able to do the experiment at all because we were burning the graphene deposition. So you managed to do the experiment without burning the graphene by applying for a very short time the current and voltage. So at the beginning, it was the first problem we had to afford. We were not able to do the experiment because after 2 or 3 steps, we were, for example, you see the table of value for the attenuator here. Okay, after 2-3 steps, we were burning the deposition. Then we understood that was a temperature problem, and we overcome this problem of applying for a very short time the current. Just immediately stop after the acquisition, the current, not leaving everything on and just save data and do other things. And so step by step, we managed to arrive up to 10 volt of voltage applied. And we stop when we burn the graphene, obviously.
There is another one. Can we use graphene for microfrequency without DC bias?
Use graphene as a DC bias?
You can't tune.
Is this a question? I'm not sure to get a question. Volume not in. I think you can do it. We never try. We just started with attenuator and phase shifter design. That was a consequence of the attenuator, because from a simple line with a pad of graphene, then we decided this configuration of a phase shifter and an antenna. So more components can be realized and explored from this point of view of tunability of graphene patch deposition and the components.
I have one or two questions. So you have tried the frequency range. I think it is around 5 or 6 gigahertz. And as you move to higher frequency in that range, that variation was less. That impedance variation, attenuation variation. So what about when you go to higher frequency in X band or like that? Will you expect this, or you have to change the voltage more? Because there is a
I think you can go, yes, we work mainly in S band or 5 gigahertz, because we realize all the component in our lab, and also because the effect, if you increase the frequency, this effect is reducing. Perhaps I have a slide that can be explained this. Okay, this it seems what is happening going to micro and millimeter waves to terahertz. So the conductivity is changing. Seems reasonably changing, and microwave and millimeter waves, but then it's reduced this variation, and you have no changes. So there is a limit on this. It's better to stay on this frequency range and not to go to terahertz and so on if you want to see this effect.
It is how do you apply the voltage? It's almost a two-dimensional this thing. You are applying top and bottom, or sideways?
Sideways. We were applying the with the sideways for the graphene pad.
So how does it? Yeah, you have shown with the aspect ratio. I think you have shown that. So that means when you change the aspect ratio, the property also will be changing, the way in which you apply the voltage.
Yes, we also did the aspect ratio analysis, because depending on the shape of the pad, obviously also the results is changing.
Okay.
And so from the resistance, we both for the phase shifter, but even perhaps clear in for the tunable attenuator. Okay, this analysis we did for the tunable attenuator holds also for the phase shifter and all other components. There is a trade-off on the shape. If it's too thin and the deposition, it is not possible manually to do the position properly. And if it's squared, you have a good range of variation, but not a very high value of S1, which is mission is poor. So you always have to first consider the shape of the deposition and simulate and try to find the optimum shape for the application you're looking for.
Okay, thank you. Any more questions from the participants? Please. So if there are no more questions, I thank Professor Savi for this presentation, because I think these are things which we can also try here using this commercial graphene and do some experiments with that one.
Maybe very, very happy if you can cooperate on this
Yeah,
topic.
sure. We'll try that. So
Thank you, ma'am. And thank you, sir. That was a really good extraordinary speech. Thank you for your rich words. I also thank the distinguished chair and the sir for his valuable presence. I also request all of you to turn on the camera so that we can take a snapshot.
if you can, okay.
We have taken the screenshots. So passing over to Ashwati.
We'll take a short break and resume at 5:30 for the technical session.
A very good evening to all. Now we are entering to the last technical session of today, which is based on electromagnetic applications and emerging technologies. There are 5 papers to be presented in the session. The distinguished chairs for this session are Dr. Basudev Ghosh from IIST Trivandrum and Dr. Hamsakutti V from King's Odd University. We welcome you. I would like to hand over the platform to the chairs.
Yeah, good evening. Can you hear me?
Yes, we can hear you.
Yes. Yeah, good evening, Dr. Hamsakutti.
Yeah, good evening, Dr. Basudev.
Yeah.
How are you?
Good evening, Dipti. Yeah, fine.
Yeah, Dipti, hi.
Hi, how are you?
Yeah, fine. So I think we can start because all the 5 papers are there or?
Yes, it should be there.
Okay. So, Basudev, we can start?
Yeah.
Okay.
So for this session, the first paper is on a miniaturized electromagnetic invisibility clocking scheme by Sarin, Vinesh, Manoj, and Vasudevan. So I would like to request to start the presentation.
I think Vinesh is going to present or Sarin?
It will be a recorded video, I think.
Okay. Oh.
It is a recorded video for first 10 minutes and then the question answer, it will be live. They are available online.
Okay.
Audio is not clear.
Yes, sorry, I cannot hear you.
Hello. Can you share the computer sound?
No, it's okay.
Yeah, now I can hear.
Good morning to all.
Okay.
I am Vinesh PP from Government College Chittoor, Palakkad, working as a project fellow in a DST Circuit Manager project. And I am here to present the paper entitled A Miniaturized Electromagnetic Invisibility Clocking Scheme. And this is the organization of my presentation. Initially, some previous works in clocking scheme. Then comes to the clocking scheme that we used in our work, that is dog-bone clocking scheme, and its geometry, scattering studies, etc. Then about the measurement setup, bistatic and monostatic measurements are used here. Then comes to its results, discussion, and conclusion. See, this is the first practical realization of electromagnetic clocking scheme by J.P. Pentry in 2006. The target was a copper cylinder and it was hidden inside the clock. The clock was constructed using artificially structured metamaterial, that is a cylindrically arranged SRR array. And they claimed the clock decreased scattering from hidden object while at the same time reducing its shadow. See, this is the another approach of clocking by Andrea Alu and Nader Angita in 2005. Here the target is a dielectric cylinder or sphere with low permittivity, and it is covered by a lossless plasmonic or metamaterials. When the target size increases, there are the chances of scattering from higher order multipoles. So by proper design of this metamaterial covers near their plasma resonance may induce a dramatic drop of the scattering cross-section. Here we propose a miniaturized version of the clocking scheme using cylindrically arranged dog-bone metallic inclusions. To extract the true reason behind the clocking scheme, multiple scattering theory has been utilized. And it is found that the strong excitation of magnetic resonance, along with the non-resonant excitation of electric dipole moment, significantly reduce the far-field scattering from the structure. The invisibility mechanism is experimentally proved using backscattering measurements, and these are validated using full-wave simulation studies. And this is the geometry of clocking scheme. See the first figure. This is the unit cell. The dog-bone metallic elements are printed on the FR epoxy substrate, and these are arranged in a cylindrical fashion around the metallic target. The target is selected as, the diameter of the target is selected as 10 mm. See the second figure. It shows the dimension of the dog-bone metallic implant, and we used this standard photolithographic technique to fabricate the dog-bone cell. 5 such unit cells are aligned vertically to obtain the final structure. The total length of the metallic cylinder is 160 mm, and the final structure contains a total of 40 dog-bone metallic particles. And see the third figure. It is the fabricated prototype of dog-bone clocking scheme. These are some scattering studies. The complete structure is simulated using CST Microwave Studio software. See the first figure. It shows the resultant scattering cross-section of the clocked and unclocked cylinders. For this computation, full structure is illuminated with a plane wave excitation. We can see here the scattering cross-section shows a significant dip at 1.62 GHz. To study the scattering properties, a three-dimensional scattered power of the clocked and unclocked schemes at this resonance are analyzed. The second and third figure, which is the RCS of clocked and unclocked target. See the second one. It scatters electromagnetic power equally in the azimuth plane. And see the third figure. The maximum RCS of the clocked target is found to be significantly low. The reduction in scattering characteristics could be understood by studying the electric field distribution around the structure. So we have to analyze the electric field distribution. And this is the simulated electric field distribution around the clocked and unclocked structure. See the first figure. It is the unclocked structure. Consider the electromagnetic power is flowing from the left of the computational domain to the right. Here the metallic cylinder perturbs the flow of electromagnetic power, and a shadow is observed behind the target. The target scatters power uniformly along the azimuth plane, so it could be detectable for far-field scattering measurements. See the second figure. It is the clocked structure. We can see the clocked target significantly reduces scattering from the metallic target. Here the shadow is absent, and the clocking structure smoothly transfers power from left to right of the domain. To find the actual reason behind the scattering suppression, we have done multiple scattering studies. Here, the surface current distributions are spatially integrated, and the variable PMT are the electric, magnetic, and toroidal dipole moments, and J is the surface current density. See the first graph. It is the computed scattered power from these three multipoles. It is observed that the electric dipole moment is strongly suppressed throughout the entire frequency band. See the second figure. The anti-parallel current circulating on the target and the dog-bone arm cancels the radiation from the electric dipole moment. In this way, the scattering is reduced. And this is a photograph of the backscattering measurement setup. Experiments are performed on the fabricated prototype using vector network analyzer inside an anechoic chamber. And two ultra-wideband horn antennas are used for this purpose. One is configured in the transmission mode, and the second one is in the reception mode. The target without the clock is placed at the center of the turntable assembly. The received power is taken as a reference with the two ultra-wideband antennas, and they are placed close to each other with an offset of 5 degrees facing the target. And we have performed the FGT calibration also. And then we replaced the target with the clocking structure. And the receiving antenna is rotated in the azimuth plane to record the backscattered power in various directions. And the corresponding bistatic backscattered power from the target at the resonance 1.62 gigahertz is shown in figure B. Backscatter reduction better than minus 7.9 dB is observed here for all the receiving angles under consideration. The clocking layer efficiently suppresses the backscattering from the metallic target. And this is the monostatic measurement result. It is performed by rotating the clocked target in the azimuth plane, and the backscattered power is recorded, which is shown in the figure. The backscattered power is significantly reduced for all these azimuth rotations. And I am concluding my presentation. An electromagnetic invisibility clocking scheme in the microwave regime is achieved here, and the dog-bone metallic inclusions arranged around a cylindrical metallic target used for reducing the scattering cross-section, and the scattering cross-section, the scattering reduction better than minus 7.9 dB is achieved here. And finally, the multiple scattering theory reveals that the higher order toroidal moment is destroyed due to the significant excitation of magnetic dipole moment on the structure, resulting in scattering reduction. Thank you.
Okay,
Yeah, thank you.
This authors are not present, I guess, to take the question answer. They are unable to connect.
Okay. There.
Oh. Okay. So that is the status.
So that means we can go for the next paper.
I guess that would be better.
Yeah.
Okay, then I think we can go for the next paper. The second paper is prediction of complex permittivity of polar liquids using a regression-based artificial neural networks. And the authors are Tushara and Mridula, Anju Pradeep, and Mohanan. So I don't know who is going to present, maybe Tushara.
Respected participants, welcome all to the presentation of the paper titled Prediction of Complex Permittivity of Polar Liquids Using Regression-Based Artificial Neural Network. These are the contents of the presentation. Moving on to the introduction, complex permittivity plays a significant role in material characterization. It gives insight into the structure of the material, temperature in the environment, amount of impurities present. But permittivity is a frequency-dependent parameter. To get an idea about the dielectric dispersion characteristics, the permittivity at wide range of frequency must be available, but that may not be always the case. The permittivity, in practice, permittivity might be known only at few selected frequency points. The solution is the Debye equation and its derivatives. This paper focuses on polar liquids because it has gained considerable interest in the recent years. In the field of dielectric instrumentation, that is, as good reference materials for the calibration of the testing equipments, and for biomedical application, that is, in the field of specific absorption rate metrology. The reason for that is, it was observed that the complex permittivity of the human tissues are similar in magnitude that of the polar liquids. But these polar liquids are dispersive in nature. The reason for that is at microwave frequencies, the effective orientation polarization is dominating. It can be described empirically using formulae like Debye equation or its derivatives. It is described in the National Physical Laboratory NPL report titled as MAT23. The NPL report describes the details of the common polar liquids ethanol, methanol, propanol 1, propanol 2, butanol 1, ethane diol, and dimethyl sulfoxide. It describes the measured values of the complex permittivity for a frequency range of 0.1 GHz to 5 GHz and a temperature range of 10 degrees Celsius to 50 degrees Celsius. And it also describes the measured values of the Debye parameters, that is a static permittivity, high frequency permittivity, and the relaxation frequency for a temperature range of 10 degrees Celsius to 50 degrees Celsius. It describes which Debye equation fits with the measured values of the complex permittivity of these polar liquids. These are the Debye equations and its derivatives. From this table, it is clear that the polar liquids are, the measured values of the polar liquids are, measured values of the complex permittivity of the polar liquids are fitted with different Debye equation and its derivatives. The best fit equation differs among the polar liquids. The reason for that is the best fit equation, it depends upon the structure of the polar liquids, the temperature, and also the frequency. Here, from the table, the methanol, which is the complex permittivity is fitted with a single Debye equation because it is found to be having short chain molecule. The methanol has short chain molecules. So it is the measured value is found to be fitted with a single Debye equation, whereas the liquids like butanol, propanol 1, propanol 2, ethanol, these are the liquids with long chain molecules. So two relaxation times are there. In those cases, it is found to be fitted with a double Debye equation. As temperature increases, the NPL report describes that the second relaxation frequency of some liquids are exceeding the limit of the measured frequency, that is the 5 GHz. So because of that, those type of cases were fitted with the Debye gamma relaxation equation, where gamma is the empirical factor. There are liquids like ethane diol, which are found to be exhibiting an asymmetric distribution of the relaxation time, which is indicated with beta. Those cases are found to be fitted with the Davidson-Cole equation. When beta becomes equal to 1, it becomes a single Debye relaxation equation. So from the table, the idea getting us the different different polar liquids are fitted with different Debye equations. So a prior knowledge about best fit equation must be there to calculate the permittivity at different frequency. And also the related Debye parameters must be known to us for the calculation. This paper proposes a model which is a regression-based ANN model implemented using Python with Keras library, which can predict the permittivity of the polar liquids without without having a prior idea about which is the best fit equation for each liquid, and also it requires only the static permittivity and the high frequency permittivity to make the prediction. Along with that, the paper proposes equations to calculate the epsilon s and epsilon infinity. That is, if the values of epsilon s and epsilon infinity are unknown, those equations can be used. This is the data set description. That is, the values are taken from the range of values are also mentioned here. These values are taken from the NPL report. Inputs are the Debye parameters and the frequency of interest and the temperature to predict the permittivity, the complex permittivity of the polar liquids. The proposed model, it's a regression-based ANN model, and the basic structure is input layer, hidden layer, and output layer. In the input layer, 4 features are taken as the 4 nodes. Hidden layer, it is responsible for the learning of the complexity among the data. Then output layer, one node is there to predict the complex permittivity. The real part will be predicted. The same replica of that architecture will be used to predict the imaginary part. Data set is randomly split into training set and test set. The training set consists of 800 sample and test set 200 sample. Activation function used is the hyperbolic tangent, and optimized is the ADAM, that is the adaptive learning optimization algorithm. Then the assessment of the proposed model was done using Low's function, that is a mean square error, that will give the idea about the difference between the predicted value and the actual value. And parameter tuning was done to improve the performance of the model, and the parameters used are the epochs, batch size, and the number of hidden layers. Epoch is the number of iterations, batch size, how the total number of samples are divided into different batches, and the number of samples present in each batch. Then the model fit was measured by comparing the training loss with the test loss, and good fit is achieved when training loss becomes equal to approximately equal to the test set loss, and overfit, that is good fit means the model is performing well in both the training set and the test set. Overfit condition is the training loss will be less than the test loss, that is the model performs well in the training loss but training set, but it can't perform well in test set. Underfit is the condition when the training loss is more compared to test loss. The meaning is the model is not trained well. The resultant analysis, the model performance validation was done. The figure shows the plot of the loss against epochs on training and test set. This from the figure. It's first figure is for the prediction of the real part, and second one for the imaginary part prediction. A good fit was achieved by this model because the the loss is found to be decreasing, and it decreases to a point of stability. Along with that, there is minimum gap between the training loss and the test loss. Then there is a trade-off existing between the training time and the loss. That is, if you are increasing the number of epochs, loss may decrease, but at the same time, training time is increasing. Along with that, if you are now increasing the number of epochs, there is a chance of overfit of the model. Because of that, the parameters are optimized at these values: number of epochs 1000, batch size 16, and number of hidden layers equal to 2. For this case, it is getting the real part permittivity is predicted with an error of 0.23 in training set and test set, whereas the imaginary part, the training loss is 0.24 and the test loss is 0.33. Then the maximum training time of this model is going to be 57 seconds, and with this system specification, Intel Core i5 processor, 1.6 gigahertz of clock speed, and 8 GB RAM. The model performance evaluation was done by comparing the predicted values with the actual value. The figure shows the predicted value in blue lines and the real value in red lines. First figure is for real part and second one for the imaginary part. Here, from the figure, we get the idea that the predicted value is almost close to the real value. So the model performs well. The paper also proposes the equations to calculate epsilon as an epsilon infinity, that is the Debye parameter, static permittivity, and the high frequency permittivity, because these are the input to the model. So if the values of these are unknown, we can use this equation. From the data set, it was observed that there is a linear relationship existing between the temperature and these Debye parameters. So linear regression was applied to derive these, to develop these equations, and these equations are valid only from 10 degrees Celsius to 50 degrees Celsius. And for different polar liquids, different equations are there, and the performance of this model was evaluated using the parameters R square and mean square error. R square indicates the goodness of the fit of the regression model, which must be ideally 1. And for mean square error, it's error in the calculation, and that must be ideally 0. From the table, it was observed that the linear regression model performs well. Conclusion. The paper proposes a regression-based ANN model, which is based on Python 3.5 and Keras library. It predicts the complex permittivity of the polar liquids for a specified frequency range and temperature, and it uses only minimum features and makes the prediction without the details of the specific equation, relaxation frequency, and the empirical factors. And the error of the real part and imaginary part is also very low. And linear-based regression-based equations are also developed to calculate epsilon s and epsilon infinity if they are unknown. And this model avoids the complexity in the measurement procedure, identification of the best fit the wave model, and the related calculation. These are the references. Thank you all.
Okay, thank you, Tushara, for your nice presentation. Now, first, maybe we can we can check for is there any question from the audience? I think Tushara is available.
Yes, sir.
So first, any question from the audience, please? There is no question. I have a few questions. Okay. Tushara, you said that this method or your algorithm you developed, this can go complex permittivity only up to 5 giga, right?
Yes, sir.
Why you limit 5 giga? Why can't you go for above that 5 giga? Because now the world is moving towards higher frequencies. So why you limit at 5 giga? Can you do something in your world to improve it to higher frequency?
Sir, this is actually machine learning based algorithm. So for the training purpose, we need the data set, and that data set is taken from the National Physical Laboratory report, and we are training the machine with that data, so that measured values were only up to 5 gigahertz. That is why we have used that values.
But if you want, you can try for higher frequency. Your algorithm will apply for higher frequency as well?
Yes, sir. The algorithm can be extended to that frequency, but the data availability is the problem.
Okay. And whether this is this algorithm that can be applicable for example, other polar liquids like water or sugar juice or anything, you have the same results?
Yes, sir. It can be applied to other. It can be extended to other polar liquids also.
Okay, so how much is the accuracy in terms of, even in the complex permittivity, in terms of the losses of the material or the liquid?
Accuracy is in the case of regression-based artificial neural network. It's a regression-based analysis. Because of that, we are predicting. We are dealing with the loss, that is the error in the calculation. The error in the calculation is actually in the case of this real part prediction, it is around 0.23, and in the case of imaginary part prediction, in the training set it is 0.24, and the test set it is 0.33. So that much difference is happening between this predicted value and the actual value.
Okay, what do you mean by 2.3 and 2.2? You are maybe the tolerance compared to the real practical results?
Yes, sir. The predicted and the actual.
And also, I read that because in your paper I saw that the mean square error, if the training data set contains 200 samples, while the test data comprised of 800 samples, why you take this 200 and 800? From where you got these two values?
Actually, it is a practice to take the training set as the splitting of the data as 80:20. Along with that, the reason is like we have to. There is a complex relationship. Complex relationship is existing among the data. So to get the idea about to train the machine to learn the complexity among the data, it must be trained with sufficient number of data. So that is why the training set and the samples are more number of samples are there in the training set, and the test set consists of only 200.
Okay. Okay, and also I suggest you to at least you try your algorithm at high frequencies. Okay, for example, if possible at 60 gigahertz and 60 gigahertz, because we need the value of the real complex permittivity of different materials. So we need some very nice techniques like the algorithm you produce. Okay, so please try to extend your frequency. Don't stop at 5 giga. Okay.
Okay, thank you, sir. Thank you.
Okay, thank you
for
very
your
much.
suggestion.
Dr.
Yeah,
Tuesday,
Tushara, I have
some question.
Yeah, I have just two questions.
Sir.
So one is, what are the other methods of this estimation?
Sir.
Whatever you have estimated, what are the other methods? And my question is actually how your proposed algorithm is better than those methods.
Sir, actually, there's no other, I didn't find any literature related to this, that is comparing it with another model, such a thing was not there. So we proposed the regression-based neural network. Other methods means the model itself can maybe it can be fine-tuned to improve the reduce the error, but other type of other models was not there in the literature. That is why we haven't compared it with another one.
So in that case, why ANN? Why you have used artificial neural network?
Sir, machine learning algorithms, like without going into the AN is actually coming under the part of the deep learning. So without going into that, we tried the machine learning algorithms, like ordinary machine learning algorithms, like the linear regression for multilinear regression, then random forest regression, support vector regression. In all these cases, the performance was not well. That is, the error was more. The error means that predicted value and the actual value was getting more. So the complexity among the data is that much, as their complexity was more. That is why we have forced to take this ANN model. The machine has to learn with the help of these neurons, the weight assigning. In that way, it has to proceed, and only the complexity can be learned, and the prediction will be better. That is why we have taken this model. We tried with this model.
Have you used a tool, or it's a you have written your own code?
Sir?
You have used any tool, MATLAB or whatever tool is available, that tool you have used, or you have written?
Python with Keras library is used. Yes, sir. With our code.
Okay, fine. So that's from my side. So if any other questions are there?
Thank you, sir.
Yeah, thank you. So we can move on to next paper.
I think yes.
Yeah, so the third paper is on non-linearity compensation algorithm for FMCW SAR. The authors are Anindya Ghosh and Devashish Chakraborty.
Good evening, everyone. I am Anindya Ghosh from IIT Kharagpur. Today I am going to present my work, which is accepted in IEEE APSYM 2020. This work is done under the supervision of my professor, Professor Devashish Chakraborty. The outline of this work is as follows: introduction, problem formulation, error compensation, simulation for point target, and conclusions. The introduction is consists of this basic knowledge of signal source in FMCW radar or synthetic aperture radar. After that, the problem associated with this signal source, which is actually the nonlinearity in signal source. And next section will be carried over for the error compensation. The error is due to the nonlinearity, and this is compensated using a algorithm which is proposed here. And to validate this proposed work, we also provide some simulation result for point targets, and finally we conclude with some observations. Here you can see that a frequency modulated signal is generated, which is nothing but a frequency sweep with time. Here we are using up sharp as the frequency is increasing with time. The source is here is actually divided two signal for transmitting channel and receiving channel. Transmitting channel transmit a signal with linear frequency modulated property, and it will get reflected back from the target and received by the received signal, and at the mixer it will mixed up with the reference signal and give the SIF, which is IF signal. This IF signal is having frequency SIF, which is equal to alpha into tau. Alpha is chart rate, which is nothing but the rate of change of frequency with time, and tau is time delay, which is 2d by v, as it is traveling 2d distance with the velocity v equal to c. So this all information is associated with the distance d is equal to c FIF divided by 2 alpha. If we know alpha and FIF, we can easily find out d. But if it is having some non-linearity, that case it will have some error result. Here the error comes at the point of very beginning when the signal is transmitting end and the source is itself providing some nonlinearity at its input with the generated ramp, and output is also having some nonlinearity due to the device properties, active device properties. So what it will give, it will actually produce a time varying IF signal frequency with time. That means for a fixed target will not get fixed frequency over time. Here what we can do is we can attack this problem at the very beginning where the ramp is generated and VCO output is having some nonlinearity, or we can attack this problem at the end point where the signal is already received and it is ready for processing. So at the time of processing we can apply some algorithm to reduce these effects, nonlinearity effects. So there are some work available already in literature where the estimation of this nonlinearity is already discussed. So this part is not in our part of work here. We assume that we know the error signal, or if we don't know, we can apply the estimation to find out the error signal. Our intention is to use this estimated signal to remove the error for synthetic aperture error. Now the available work is already available with the current control oscillator, but it is very slow modulation speed. It needs very high power, and it is also having some problem with drift with temperature. In VCO with closed loop feedback is having some good result and linearity is better than 0.01%, but it is very complex in circuit nature, circuit configuration, and also it will not provide linearity above bandwidth 600 MHz. On the other hand, direct digital synthesizer or frequency synthesizer, whichever is, so it also provides some bandwidth limitation and require up conversion and very expensive. VNA is also not a portable one, and it has some problem with the phase deformation. Actually, for any kind of vibration or any kind of motion which are not intentional, or it will create some phase error problem with this, and it is very bulky and expensive also. In free running VCO, it is having some problem with linearity, but it is not costly at all, and we can use it in portable system also. maybe in ground-based synthetic aperture radar or any laptop-based radar or any kind of thing, this is a good option as a frequency source. Now we can define some parameter where alpha is chirp rate as discussed before, and the phase error function is ET, with carrier frequency is the transmitted signal of FC. Then transmitted signal is a quadratic phase response, as it is having linear frequency modulated signal, and with that error ET contributed by the signal source. Then after reflected back time delay tau, the received signal will be this. So IF signal is having the expression of this, which is actually defined by the equation 3. Then the IF signal having the phase with the extra term here due to this nonlinearity. If we further derive this expression with the IF signal phase, then we'll get this expression which indicates that the maximum phase error will be this quantity, as this quantity is having maximum value 1. So we can easily find out that one target is having its response at receiving signal with some two host target response. One is at plus FM signal, one is at minus FM signal. FM is errors frequency of error signal. Now this error can be omitted by this compensation algorithm, where received signal will be multiplied with the conjugated error signal, then pass it through a rescue filter, and after this output will be multiplied with the fractional of error signal again, and output will be applied at the window, and Fourier transform will give the frequency domain corrected signal. For each step we will get this result for a finite chirp, where rect T by T is define the finite chirp duration, and that case transmitted signal will be in this expression, and the received and the IF signal can be defined by equation 11. After getting this IF signal, this is the input signal here, and this input signal will be multiplied with the conjugate of error signal, which is this one. This conjugate of error signal will be passed through a rescue filter, and this rescue filter response will be again multiplied with the fractional of conjugate error signal, which is actually defined. This is for rescue filter, and this is for fractional error signal, and after windowing we can get this ideal signal, which is not having this extra nonlinear term, this already omitted. So here the simulation result shows that one particular red one is the ideal response for a single target, and blue is for the erroneous response of a single target. So here we can see these two host response are present with the single target, but as we don't know the exact location of target, and without any prior knowledge of target location, no one can detect which one is ghost target or which one is actual target. This is for single target, this is for multiple target. Here also these are also presenting number of ghost target. So our compensation strategy already removed this effect, and these steps are repeated for each and every range profile at different cross range position of the SAR, synthetic aperture radar configuration. We are assuming then that the stop and go process are going on to receive and transmit the signal in synthetic aperture radar mode. So for a multiple target, when the nonlinearity is present with the error function, error frequency 50 kilohertz, and the exact position is the coordinate are like this. So we are having this kind of response, which is clear from this that we are having number of side lobes here, and this image are not actually focused in synthetic aperture radar mode, but after compensating we are getting this response which actually removes all the effects of nonlinearity, and the targets can be located. So conclusion can be defined like this: nonlinearity in VCO frequency sweep degrades the resolution of sensor. Range detection in case of more than one target is more erroneous due to the side lobes. Number of side lobes are increasing in that case. Proposed algorithm is suitable for error compensation in synthetic aperture radar signal processing. These are reference. Thank you.
Yeah, thank you. So first of all, if there are some questions, we can take those questions. So I think there is no question from audience. So I would request Professor Hamsakutti to continue for his queries.
Okay, I think our audience are not asking any question. Anyway, so Mr. Kosh, my question is, I think you put the carrier frequency as 2.4 gigahertz. Is there any, why you choose 2.4 gigahertz as carrier frequency? Just for simulation purpose or?
Okay, I am audible now?
Yes, yes.
Yes,
Yeah,
actually we are planning to propose this concept, and after that we will be go for some higher frequencies like X band. So first of all, we just propose this for lower frequency, 2.4 gigahertz. We know there are some limitation with 2.4 gigahertz, but keeping all this thing in account, we are going with this low frequency first to implement our concept and also hardware. Hardware part is already have done, but it is not presented here.
Okay. So when it comes to multiple target, how you believe that your compensation algorithm is better compared to the already available algorithm in terms of accuracy?
I understand. I understand. This is very important question for this work. Actually, in every whatever is done in literature and available in literature, they are assuming that all are in short range radar. That means target are not at very far location. But from our mathematical location, we can find out this: if the range is very much longer than any short range location, in that case nonlinearity effect will be much more. And if range is long, that case number of target will also be, that probability of getting target will be more. So if our we are showing this, if this is the condition, in that case our proposed algorithm can be easily applicable for any kind of range. It may be for low range or high range. And for all these cases, if number of targets are high, in that case number of side lobes level will also be high. And there must be some condition if these targets are located nearly or they are separated from each other. So this condition should also be taken care of, and we are working on this. Some of result is already we have generated, so that will be our next part of the work.
Okay, so you mentioned that if there are multiple targets, is there is a minimum distance between the targets, or if targets are at any random distance, it doesn't matter, your algorithm will provide the means accurate result? Or is there any minimum distance between two targets?
Yes. See, for resolution purpose, there is antenna beam width should be defined for that particular case. If in a 3 dB beam width, two targets are situating, so that case we cannot detect these two. So this is the minimum distance for which we cannot distinguish two target. These two target must be separated at least the range which is nearly more than 3 dB beam width of antenna first, and also the range of frequency or operating frequency, which will give the resolution better for higher frequency. These are the minimum limits of the location of these targets.
So even the location, I mean the distance, and also even if it is in a particular angle, okay, it doesn't matter, or only distance.
Yes, only distance, because we are already showing the result for 2D, for range and cross range.
Okay, so when it comes to multiple angle, so your algorithm doesn't work?
For particular case means different angle means they are not aligned in straight or any straight or any parallel to sensor movement. It may be some other angle.
But in random angle, for example.
Okay, that case also it will work. That means they are in different range beam and range cross range locations.
Okay, thank you, Ghosh. Maybe.
Yeah, Anindya, I have some 1 or 2 questions.
Okay.
Yeah, first of all, this you have shown some this one PPT that you have this conjugate error signal, which is the input to your.
Yes.
So you are assuming that error already you know.
Yes.
So how that means, how will you know that error signal?
See, for this is the different part of this work. There is some already proposed work related to estimation of this error signal, and we also worked on this, and we have proposed one techniques to achieve this estimation process with some simplicity. And again, I would like to say the available work which are available in literature and many people are reported, these all are for short range error, and they are using derivative techniques to get the estimated error signal, especially for meta paper written by meta something. So they are proposing the technique for estimation of this error signal using derivative techniques. In that case, if range is very low, that case delay will be less, and they are assuming this can be represented as a derivative function, and after left hand right hand kind of thing, they will integrate over the time and get this error function. But in our case, we are assuming this function is already known, and for this case only we need to know estimated signal information and chart rate.
So you are telling that your this proposed algorithm, it is when the range is very high, it also works.
Yes.
So have you verified? So for your claim, have you any results?
Yes,
for
but
that,
this yes. Actually, this estimation work I am not reporting here, but in our cases we also consider other parameter in real cases where the noise figure and other kind of thing will be acting more significantly.
So as you said that other methods are for short range. So have you tried any of those methods for larger distance?
They are actually stated, these are only for the assumption is they have taken to take this estimation process using the derivative techniques, and this derivative can only be assumed when this range are very less.
And as you said in multiple targets, that you said that at least those targets should not come inside the antenna beam width.
Yes.
So how you are modeling that in your simulation?
In simulation, right now we are not considering this beam width actually, but in case of practical scenario, we have to take into account is that for lower frequency there will be this beam width will be very wider, and higher frequency this will be narrower. Or if we use any antenna array for lower frequency, that case we can also reduce the antenna beam width. In that
And
case, we
also,
can.
as you said, no, that it is not means angle of means angle of the target. It won't affect.
In that case, this will affect. If this angle is very means what should I say? If the slope between these two is very high, in that case they may be in between these 3D.
So in your simulation, you have simply taken the target which is on a straight line.
Yes, it is in a straight line.
Okay. Okay. Thank you. Thank you very much for your nice presentation.
Thank you, sir.
So,
yeah, so
I think we can move to the fourth paper. So our fourth paper is microwave analysis on bone mineral density by Shilpi Ruchi and Dibanila Ghosh. So you can start. Shilpi.
Good evening, everyone. I am Shilpi Ruchi Karketa, research scholar from IIT Bhubaneswar. I am here to present my conference paper on the topic microwave analysis on bone mineral density. So, the loss of calcium or the bone mass as the person ages, which leads to bone becoming thinner, and it is called as osteopenia. If the bone mass is further lost, the osteopenia leads to osteoporosis. This leads to bone becoming thinner and most likely to break or fracture. Here in this first image, we can see that healthy bone shows a broadband connection, but as the bone mass is decreasing, the bone is becoming more porous and it has a very disrupted band, which no longer contributes to the bone strength. These are the existing methods to evaluate the osteoporosis, which are DEXA, QCT, ultrasound, and MRI. DEXA is the gold standard to measure the bone mineral density, but as it is using X-ray, it has a very high radiation and it cannot understand the bone health or the quality. Next is the QCT, which is better than DEXA, and it can differentiate between the cortical and trabecular bone, but the radiation dosage are more than DEXA and thus there is a risk of cancer. Next is the ultrasound. The drawback of the ultrasound is that it cannot penetrate through the bone, it has a strong reflection and hence it doesn't give a very good result. Last is the MRI, which is very expensive and it is not easily available in all the clinics. Here we can see that DEXA, QCT and MRI are costly. It is very big in size and it is not portable, but it also takes too much time for evaluation. Although ultrasound is very small in size and it is portable, but it is not very accurate. And hence we have chosen microwave technique in our experiment, as it is having a non-ionizing radiation. It can easily penetrate through tissues. The wavelength is longer than optics. There is a wide range of frequencies, so we can choose any suitable frequency for our evaluation. It has the ability to focus the energy in particular direction. There are a variety of simulation tools available for computation such as CST, HFSS, FICO, etc. And hence it has a very low cost. So the objective of our paper is to conduct a simulation study on the performance of antenna with close proximity to the human body. And the second one is that to conduct an experimental analysis to characterize the bone mineral density through a pair of monopole antennas. So here we have chosen a planar stub monopole antenna for the experiment because it has an extremely wide band. It has a very simple geometry. It has an omnidirectional radiation pattern. It has a very low cost. It can be easily integrated with the circuit and it can be easily fabricated in our lab. Here in this design, we have used an open stub which is integrated in the ground plane, which improves the impedance matching of the antenna by increasing or decreasing the capacitance or the inductance of antenna, hence improving the overall impedance. So this is the antenna design for the planar monopole antenna. The first image is the radiating part of the antenna, which consists of circular radiating part with circular slot. It is fed through microstrip line. The second image is the ground plane of the antenna, which consists of partial ground plane with which with length L and width B. To improve the bandwidth of the antenna, we have integrated an open stub on the top of the partial ground plane width of length Ls and width Bs. All the parameters of this antenna are given in this table. The equations used for the calculation of the antenna are also given here. So, and the lower image is the fabricated antenna. So here we are showing the return loss of the stub monopole antenna. So first, with this blue line, we can see that the return loss of this monopole antenna with partial ground plane, which is having a frequency band from 3 gigahertz to 6 gigahertz. But as we integrate stub on the partial ground plane, we can see that there is an improvement in frequency band from 3 gigahertz to 37 gigahertz. As we can see through this Smith chart that the monopole antenna is giving a better impedance matching. This is the simulated and measured return loss of the stub monopole antenna, which is in very good agreement. Here we have used a stub monopole antenna, and here we have used a human phantom mimic at the back of the antenna, which consists of skin, fat, muscles, and bone. And all the parameters for making this human phantom mimic are given in this table through tissue characteristics. Here we can find the permittivity, conductivity, loss tangent, and dimension of the human phantom mimic. So next is the optimization of antenna. The first image, here we see the simulated S11 of the planar monopole antenna without the human phantom mimic, and we are getting us a good S11. But as we add the human phantom mimic at the back of antenna, which is shown through the purple line, we can see that the return loss S11 is severely distorted and placed to the closely to the antenna. So in the second image, we can see we have conducted a comparative study with the different distance of the antenna with the human phantom mimic. So as the distance of the antenna is increasing from the phantom, the return loss performance also increases. Hence, we have used an optimum gap of 2.5 centimeter between the antenna and human phantom mimic, which is very suitable for the experiment. So this is the radiation pattern of the antenna with the human phantom mimic and without the human phantom mimic. So here which are observed at different frequencies of 3.929 gigahertz, 5.66 gigahertz, and 8.43 gigahertz. So through the second image, we can see that there is a coupling between the antenna and the human phantom mimic. Next is the case study on the animal bone. So here we can see the bone samples and the experimental setup. In order to show the advancement of osteoporosis and to reduce the bone mass, we have drilled some of the bones. We have dipped some of the bones in the soda, and we have dipped some of the bones in diluted HCl. For experimental setup, we have used two pair of two antennas, and there is a bone sample over here and the vector network analyzer. So in earlier papers, they have used S11 as the comparative parameter for detecting the osteoporosis through microwave techniques. But in our experiment, we don't observe much variation. So in the second image, we can see we have taken S21 parameter as the observation. So according to our analysis, S22 is decreasing as the bone mass is decreasing. As the bone mass with greater permittivity, as the bone mass with bones with low mass is having a greater permittivity, and hence it is absorbing more energy as compared to the healthy bones. So we have conducted another set of these 5 experiments with the same bone, and we have added a human phantom mimic with this bone. So here we can observe that there is an overall decrease in S21 as compared to the previous experiment, as the phantom is absorbing more energy. So the overall here also we see that S21 is decreasing as the bone mass is increasing. So we can conclude that monopole antenna can be used to differentiate between the bones with different masses. So here we are having our conclusion. In the study, a planar submonopole antenna ranging from 3 GHz to 10 GHz was used as a technique to study the level of bone mineral density. Conventionally, through CST microwave studio, we optimized the gap between the human phantom mimic and the antenna. This study was further augmented through two different experimental studies. The experimental study is demonstrated that the S21 is shifted downwards with a decrease in bone mass. So these are the references. Thank you.
Yeah, thank you. So, any questions from the? Yeah, I can see one question from Professor Anandan. Why you need ultra wideband antenna?
Good evening, sir. Actually, we tried with all the antennas. So actually, when we are using this ultra wideband, we tried for different frequencies. But when we saw like most efficiently, it is working from 3 gigahertz to 10 gigahertz. So we have used this frequency band, and we tried with narrow band, but we are not getting the results more efficiently. Like further, we have tried some statistical methods after this experiment. So we are getting good results with ultra wideband antenna.
Yeah, but that much difference I couldn't see in that S21 because your power level shown is -60 and all. That difference it could be with an experimental error also, because when you are using that such a small power level.
Yes, actually
how do you
the bone
distinguish?
size we got was very thin. That's why. And that other body phantom we are using, that is like larger compared to the bone size. That's why we are getting more error.
No, because we expect a large difference because you are using bone and drilled and dipped in HCl means that calcium might have gone. So that much difference means in the S21, a lot of difference we expect. So how will you distinguish? How can you use it for a clinical application? That is my doubt.
So actually, we will conduct one more experiment. We are trying that. So actually here we use only one bone. So we are planning to use we are trying to use human wrist. So we are having two bones. So we will try this experiment with two bones, and we have got some better results compared to this, because that human body phantom is becoming very large compared to the bone. That's why we are not getting a good result here. So we are continuing that experiment.
Okay, thank you.
Yeah, okay, Shilpi, I have some questions.
Yes, sir.
Yeah, so as just a continuation of Professor Vasudevan, what he asked, that you have used and you have shown some S11 till 50 gigahertz. And you are saying that you are using a UWB antenna till 37 gigahertz for your antenna. That S11 is less than 10 dB.
Yes, sir.
So my question is, why you need to go to till 37 gigahertz? Are you really going to use those high frequencies?
So we tried like all the frequencies. No, actually first I made the antenna. So after
No,
that we
my
implemented.
question is, as you said in your, I think, introduction slide,
Yes,
that
sir.
you have to choose a suitable frequency.
Yes, sir.
So what is that suitable frequency? On what parameter you will choose that frequency of operation?
We tried the simulation. We made a human wrist. So when we did that through CST microwave studio, so
Yeah,
we
that's
found
fine.
that.
So I can rephrase my question. I'm asking that, can you really use those high frequency for this kind of imaging?
Actually, in my antenna, this is working more efficiently in the from 3 gigahertz to 10 gigahertz, and that after that from 35 gigahertz it is working properly. But in the
so
mid, it is not.
then the question is, if your target frequency is still 10 gigahertz, so you could
Yes,
have
sir.
used some standard UWB antenna also. Why
Yes,
you
sir.
need to do such kind of modification and so many things?
So actually, my guide told that compare all the other antennas with this system. We tried that Vivaldi antenna and some bow tie
Yeah,
antenna.
fine. So
But
let me ask you another question. That shall we use high frequency, let's say above 20 gigahertz?
yes, sir, we can use. It is depending on the antenna, how it is like
So do
coupling
you
with
think the
the.
behavior of the electromagnetic field
Yes, sir.
inside the tissue will be similar at low frequency and high frequency also?
No, sir. It is
Then how can we
changed.
use that? And how it is going to change?
So with high frequency, actually it is covering the whole bone. Like the radiation pattern, it is like side
No,
lobes are also there.
maybe I am asking about the attenuation at high frequency, because you said that microwave can easily penetrate into the tissues.
Yes, sir.
But our body, there are a lot of water.
Yes, sir.
So how the microwave at high frequency can penetrate into water?
Yes, sir. That after 10 gigahertz, we were also not getting a good result. So it
And
might be
also you
getting
have used
absorbed.
only 2 antennas.
Yes, sir.
And how means how will actually you can really tell that what is the health of that bone by seeing your results? I think that is the similar question what he also asked.
So we did actually we have also implemented in machine learning. So what we have done, like we have taken the 6 levels of bone mineral density, like from healthy bone to osteoporotic bone, and
But
like
there
we,
is no such difference. If you
yes,
see the S21 curve, there is no such difference.
yes, sir. Because the
And
size of,
one experimental setup, which you have shown as the first one, I think,
yes, sir.
there you have considered only bone.
Yes, sir.
So that you have not simulated.
Yes,
That
sir.
is different from what you have simulated. Your simulation is with the human some tissue model.
Yes, sir. So actually, when the bone mineral density decreases, so what we have done, we have made it more porous. So that porous part, we have replaced it with that muscle part. So actually, it is becoming the permittivity is increasing. That's why the attenuation is more. So that's how we are saying that the bone density is decreasing.
Yeah, but anyway, means my suggestion is you have to go through the your experimental setup to really claim that you can tell something about the health of the bone by seeing your S21 parameter. It is not clear from the results what you have shown here.
Okay, sir.
Okay, thank you. So I will
Thank you,
ask if some other questions are there, please carry on.
Yes. Shilpi, you made phantom mimic. What are the material you used to make this phantom for
So like
different?
we have used derived this phantom from a paper. So we have made a very low end phantom. Like they have used sugar, salt, and some oils to make the phantom. So mostly in we are considering human wrist. So the uh, muscle is having more permittivity. So we have only used that muscle phantom.
So
So
my question is, did you manufacture or did you make this phantom, or you took for a simulation purpose you take the values?
So we made it in a lab. Like we chose the quantity. Like they had
Okay.
done the experiment.
Okay.
So
You made the lab. How did you measure the dielectric parameters?
that we have not measured, sir. We don't have that facility.
Then how you assume that the material that you made in your lab is the same, same as the, for example, that corresponds to the mimic phantom, for example, 2.4 or some dielectric, how you make sure this is same? Because if a small combination will change the dielectric parameters.
Actually, like we have used the same quantity what they have used in the paper, but we couldn't measure it. So we are not sure, but we are doing the experiment. Like we tried to buy a probe, but with our facility, we couldn't get a probe.
Okay. Okay. So the other one is, as the others mentioned, in your results S21,
Yes,
you
sir.
change the density, right? When you change the density, you got some results. Even
Yes,
though there is no much difference, there is no much so big difference between each category. How you make sure that your result is correct? If I am saying wrong, how can you convince me that my result is correct? Do you have any other alternative, for example, simulation or some other thing, or from the literature?
So we are trying to implement a machine learning. So what we are doing, like we have used a human race. So each like tissue, we are changing the size, and there are different levels of bone mineral density. So like everyone is having different tissue size and muscle size. So we are changing each parameter and with different level of bone density. Then actually we are getting like around 93% accuracy, and through SVM we are getting around 97% accuracy with different levels of bone mineral density.
Okay, now my question is, in your results, okay, how
Yes,
you
sir.
make sure your result is correct compared to with what you are saying your result is correct? You have some simulation results, you have the same, or you have some results available in the literature to make sure that, for example, you put your bone in a chemical, and in that chemical you assume that you change the density, right? And the value obtained, the S21 value obtained is correct. How you make sure? This is my question.
So we have done the simulation, but we are still working in this experimental part. So we will be doing that machine learning part. So we will be taking several samples of this antenna, and we will be conducting the experiment. We have done one experiment through that pulse generator and a spectrum analyzer. So we have used 3 different samples, and we have done a statistical analysis. So on that, that is given in a journal paper. So with as the bone mineral density is increasing, that we have used a T-stat in that. So our T-stat is also increasing. So with that 3 results, we are getting results like that T-stat. We have taken a statistical analysis on that.
Okay, but my suggestion is, when you make the material, I think you have to do the dielectric properties of the material. You can use some simple method of some cavity perturbation or something like this one, because it's a liquid. You can find by using that method to make sure that your material or the phantom that you manufactured is, it has the same characteristics what you means intend. Okay. Okay, then thank you very much.
Okay, sir. Thank you, sir.
So maybe we can go for the last paper in this section.
Yeah.
Application of a cylindrical dielectric resonator as an angular displacement sensor. And the others are Premsal and Praveen Kumar. So please start.
Good evening, one and all. My name is Prem Sai Regalla. I am going to present the accepted paper, which is titled as Application of a Cylindrical Dielectric Resonator as an Angular Displacement Sensor. The authors are Prem Sai Regalla and A.V. Praveen Kumar, belonging to BITS Pilani campus. The structure of the presentation is followed by these contents: objectives, introduction, sensor concept, results and discussion, conclusion, and followed by references. The objectives are to demonstrate the potential application of cylindrical dielectric
I think what happened? Dr. Ghosh, you can hear something or?
No, it's totally only I can hear you.
I think there is some problem in the speaker
Yeah,
side.
maybe some problem.
Sir, there is some technical issue. I'm just trying it again.
Okay, thank you.
Okay.
Recently, radio frequency resonator-based displacement sensors have generated wide research interest, mainly due to their high sensitivity, loci, and quasi-linear range. Metamaterial-inspired resonator elements are state-of-the-art. Basically, the general principle of resonator-based sensor is to produce a change in the resonant frequency, bandwidth, amplitude, or phase of frequency, either in transmission or reflection responses, with a corresponding change in the external stimulus coupled to the resonator. Generally, for any displacement sensor, whether it is a linear or angular, that will follow this operating principle. Let us discuss about a fixed frequency and varying amplitude sensors. Coming to the angular displacement sensors, these are useful for detecting position and alignment in various applications. Sensors based on frequency shifting principle, they produce wide dynamic range compared to fixed frequency sensors. However, frequency shifting sensors are highly sensitive to physical and environmental conditions. Moreover, these frequency shifting validation requires wideband measurement system, which is used costly vector network analyzer. To overcome all these, fixed frequency sensors are proposed for angular sensing. So now we will discuss about the dielectric resonator based angular sensor. So generally, to overcome this one, here we are proposing fixed frequency sensor. The implementation of dielectric resonator for displacement sensing application is quite recent. Compared to the metallic resonators, DR offers numerous benefits like compactness, mode selectivity, efficiency, and commercial availability. Moreover, these DRs are offering the 3 degrees of design freedom: shape, geometrical ratio, and dielectric constant. In this work, we are proposing an angular displacement sensor based on a metal strip loaded CDR coupled to microstrip lines. Here, two configurations are numerically investigated. One is reflection mode and another one is transmission mode. So initially we are starting with reflection mode angular sensor. The design of DR based reflection mode angular sensor is shown below with design parameters. Here the involved components are 50 ohm microstrip line, dielectric resonator, and metal strip line, which is loaded on a dielectric resonator. So the values of these parameters have been shown here. So we can coming to the frequency responses when theta at 0 degrees. As we can see, when theta at 0 degrees, the metal strip line is parallel to the 50 ohm impedance matched microstrip line. So actually what happens at that position, the metal strip causing the highest perturbation to the DR mode, which is HEM11 delta. So the maximum reflection occurs as we see in the diagram. So as we changing the angular position of that metal strip, including with DR, the impact of metal strip will reduce and it will allow DR mode to excite at a frequency of 3.47 gigahertz. So the frequency response of reflection coefficient magnitude spectrum we can see here. As the angle changing from 0 degree to 90 degree, the DR mode is exciting. So coming to the angular sensitivity, sensitivity curves are plotted between the magnitude of S11 value with respect to its theta at the resonant frequency, which is 3.47 gigahertz.
So as we can see here, the S11 dB curve is exponential in nature, but when we see S11 linear curve, it is quite quasi-linear nature in the range of 10 degrees to 80 degrees. We actually get a nice kind of sensitivity value here. So the calculated average sensitivity is 0.26 dB per degree for linear dB curve and 0.01 per degree for linear curve. So next we are going to discuss about transmission mode angular sensor. The previous reflection mode sensor is modified into two-port design to operate in transmission mode. We can see the diagram here, and the design parameters are same as which are involved in reflection mode sensor. Coming to the frequency responses, when at theta equal to 0 degree, actually the two-port microstrip lines are parallel with the metal strip line. So actually the highest level perturbation causes the lowest transmission. So as it increasing to 90 degrees, the DR mode will exit. So maximum transmission we will get at 3.5 gigahertz, which is almost all equal to the reflection mode sensor frequency also. So coming to sensitivity, in the same way we can see here, the S21 dB curve shows exponential nature, but S21 linear curve shows the quasi-linear nature in the range of 10 degrees to 70 degrees. We can see in the diagram. So the respective sensitivity values we get as 0.3 for dB curve and 0.01 for linear curve, which we can say actually we are able to produce a better sensitivity. So proposed measurement techniques. Initial measurement actually planned with a VNA, obviously, but here we are dealing with fixed frequency operating system. So a low cost measurement setup also we can able to plan, so that we can compensate with coming to the reflection mode sensor. With a reflectometer measurement setup, we can validate this measurement setup. So basically a reflectometer consisting of a radio frequency source, matched load, directional coupler and power meter. So for the transmission mode sensor, the combination of RF source and power meter is enough to validate the measurement setup actually. So these two combinations are less complex and less expensive also compared to the reflectometer setup. So here we compare the sensor characteristics between two modes, reflection mode and transmission mode. So as you can see here, the reflection mode is almost all single frequency system, but transmission mode is obviously it is single frequency operated design. Their operating frequency is also almost all similar, where reflection mode is 3.47 gigahertz and transmission mode is around 3.5 gigahertz. Dynamic range is same for both the modes, 0 to 90 degrees, but quasi-linear range is 10 to 80 degree for reflection mode, 10 to 70 for transmission mode. Coming to the sensitivity, for reflection mode it is 0.26 dB per degree, it is 0.3 for transmission mode. So the design complexity, the complexity and cost of measurement setup other than VNA is quite high for reflection mode, but that is low for transmission mode. Here we have analyzed the parametric analysis and sensor performances. Initially, we have seen the effect of relative permittivity of CDR by keeping the diameter and height constant. Here we can see as the dielectric constant increases, the frequency and sensitivity are decreasing, but at the cost of constant linear range. So wide dynamic range is constant irrespective of that dielectric constant. Next, we analyzed that effect of aspect ratio by keeping the diameter and relative permittivity constant. So as we see here, as the aspect ratio increases, the frequency increases and sensitivity increases. Here the wide dynamic range also increases. So here, as per the aspect ratio increases, all the three, frequency, sensitivity and range, all three parameters are increasing. So finally, we another parameter which is left is diameter. We analyzed the effect of diameter by keeping the aspect ratio and relative permittivity constant. So here we can say as the diameter increases, resonant frequency decreases, sensitivity also increases, but at the cost of decreasing the dynamic range. Okay. Coming to the conclusion, here we presented the DR as an angular displacement sensor. Using microstrip transmission lines, both the reflection mode and transmission mode topologies are numerically analyzed. Sensor performance parameters such as frequency response, sensitivity, and linearity are compared. The dynamic range of sensor is limited to 90 degree due to its structural bisymmetry actually. But this one we can improve by using some asymmetric structures. So here the advantage of DR is its performance tunability by the proper choice selection of its geometrical and material properties. So this work is supported by the DST SERP and partially by DST FIST. So these are the references. Thank you.
Okay, thank you, Prem Sai, for your very nice presentation. So first we can check, is there any question from the audience?
Okay, sir.
Any question from the audience?
I think no question.
It seems no question from the audience, so we have ask one question. So Prem Sai, you used the material 24 epsilon R.
Yes,
You
sir.
manufactured one or you made it? What is the material? What is the component?
Actually, the ceramic material dielectric resonator is already available in our lab, sir.
Oh, so you just use it.
So actually it is ready-madely available. So that is the only DR here we are having. So we are doing simulations according to those values.
But you did something with the 18 as well. I saw in the last table. Some
No,
other.
actually, sir, that 18, 20, 24 other parameters are for analyzing purpose, sir. But when it comes to prototyping or measurement section, we have only one option, sir, 24.
Okay, in your simulation results of S11,
Yes, sir.
It's very difficult to understand because you provide the same color, the black, for from 0 to 90 degree.
Yes, sir.
Why you take the same color? Why can't you take different color at least to understand the variation?
No, sir. Actually, here the variation is gradually increasing. So there is actually what here happening is at 0 degrees there is a high level of reflection. So it will be a flat curve.
That
So
means the variation is uniform.
So as the degree is increasing, so actually we can see the gradual change in the response, no, sir. So we thought like we can say by showing the 0 to 90 degree, the response is very increasing gradually. So we haven't highlighted with color, sir.
Okay, now I understand. So can you provide some application of this your work?
Sir, actually previously these displacement sensors are used in motion control systems, sir. We can use in motion control systems. Otherwise, actually there is one option like it can be used in space vehicles or rapid prototyping industry for measurement purpose, sir, actually.
Okay, thank you very much. Maybe Dr. Ghosh has something.
Thank you, sir.
Yeah, Primsai, I have some questions.
Okay, sir.
So first of all, that you have shown some dimensions of the DR in your initial slides.
Yes, sir.
So how you have come up with all those dimensions?
No, actually here we are having a ready-made DR, sir. So that one actually my senior is also worked on the same DR. So actually, so scientifically I got from him the dielectric constant, diameter and aspect ratio. So these three values I have taken, and he has published many papers also, sir. So I have taken.
Yeah, okay, fine. So my question is that you have said that it will for let's say transmission type.
Yes,
so
sir.
It will couple the energy to the DR.
Yes, sir.
Or it may not couple for your reflection type, whatever.
Yes, sir.
So how can you explain that with a microstrip feed?
Microstrip feed. Actually, here no, sir. If we take a simple DR, there is no case of coupling, sir, actually. So in terms of angular displacement.
No,
So,
you have said that it will excite the particular DR mode. So how it get excited?
okay, sir. Actually, what happened? No, when the the symmetry of the structure we tried to broke, no, sir, by the angular movement of the DR. So actually, the resonance of strip will be reduced when it changes to 0 to 90 degrees. So there will be no impact of metal strip which is aligned on DR. So that will make DR to excite. So this mechanism
So
follows.
how that mode, particular mode, will be excited? How can you ensure that other modes are not excited?
No. Actually, sir, for the mode clarification, there are some particular closed form resonant frequency equations and field patterns. So by analyzing these two things, we can define which mode is exciting and what is that mode. So there are set of some closed form frequency equations. And when we see the electric and magnetic field patterns of the DR, so with these analysis, we can see, sir, which mode is exciting.
Okay, fine. So in some of the graph you have shown S11 linear, that scale is 1.2. Why?
Scale is 1.2. So actually, why I have taken scale 1.2? No, sir, we can take 0 to 1 also actually. That is not.
No, that's what I'm asking. If it is 0 to 1, why I should show 1.2? And I have seen some of the S21 figure where
Yes,
I
sir.
think the S21 value goes beyond 0 dB because there is some discontinuity. So do you think that S21 can go beyond 0 dB?
No, sir. Actually, maybe that is a problem from the actually, when I am converting in Excel, no, sir. Maybe that is a problem from my side. But it
No,
should
you
not be.
have actually exported the data from CST or whatever simulation software you have used
Yes, sir.
to the Excel.
Yes, sir.
So I think you have to relook into your simulation.
Okay,
because
sir.
if it is going beyond 0 dB, then there must be something wrong.
Yes, sir. Yes, sir.
Okay,
Okay, sir.
thank you. So if any other questions are there? Okay, then thank you.
Yeah, one doubt I was having is that you have compared S21 linear and S21 dB scales.
Yes.
But I don't understand what is the significance there. S21 dB, it will be exponential because it is dB. You are taking log.
No, sir. Actually, there.
Significance in comparing the same result in linear and dB, but
Okay, sir. Sir, there is no difference, but actually there is a possibility to show the value. So that's why we have implemented this one, sir. They both are same only, but for a particular. No, sir. Actually, the thing is when we come to the sensor concept, so we are here highlighting about the linearity and sensitivity, sir. So if in DB curve, actually it is quite exponential nature. So we can't defend the linearity. So we can't fight with that question, no, sir. So we converted into linear curve. So compared to the DB curve, linear curve, we can say at particular region it is quite linear. Even though the overall response is quasi-linear, but I preferred compared
But
to
if your system, if your sensor is non-linear, then it will be non-linear whether you plot in linear scale or dB scale. You are showing the same result. That is what I think Professor Anandan is asking.
Yes, sir. That is just a small conversion, no, sir. Result is same actually.
No. Does it physically mean anything? That is what is the question.
Yeah.
Okay, sir. That I will take care actually.
Yeah, okay, thank you.
I will look into it.
Yeah, okay, thank you.
Thank you, sir.
Okay, thank you. So that is the end of the session.
Okay, sir. I request all panelists to turn on their camera so that we can take a snapshot with the chairs.
I've taken.
Okay. So here we come to the end of technical session about electromagnetic applications and emerging technologies. I take this opportunity to thank the chairs of the session, Dr. Basudev Ghosh and Dr. Hamsukuti V. And by this, we come to the end of day 2 of APSYM 2020. I thank all the wonderful people who spoke today and also the ones who were present here. I hope the day was enlightening to all of us. We will resume the event tomorrow at 9:30 a.m. with another technical session with about meta surfaces and meta material structures. Thank you.
Yeah,
Okay.
thank you all. Thank you.
Thank you all. Thank you, Dr. Ghosh. And also I would like to thank the organizers for inviting us for chairing this session. Thank you very much, Dr. Andasa. Yeah.
Hi.
Hi. Doctor, how are you?
Yeah, fine. Vasudev.
I'm very happy to know that it's going very nice.
Yeah.
Good. Okay, Dr. Ghosh.
Okay. Fine. Thank you, sir. Thank you.